So last year I gave a talk at CBPR, and it was also about 3D generative modeling, and kind of the four main topics that I touched upon. It was this differentiable rendering plus multi-view supervision. For example, a famous paper is EG3D, and the second category was score distillation sampling, as made famous by Dream Fusion. And the third category of 3D generative modeling methods was multi-view diffusion, followed by multi-view reconstruction. And the fourth category, SDF generation, and followed by texture generation. So I think the first two methods are kind of went down over the last year, and the last two kind of remained. But then also, I think we saw a rise of interest in generating meshes and some structured data. So I'm going to talk about these three topics this year. Let's see how it goes. And this is mainly an overview talk of recent methods. And I'll talk a bit about our own work as well. But I hope the talk gives you a good idea of the landscape of 3D generative modeling. So some comments about data structures and also their popularity and maybe suitability for urban modeling. I'm kind of familiar with meshes, can be triangle, quad, mixed, and general. And I would say, if we look at the bottom left, I would say these general meshes are very good at modeling mass models and roof structures. And I think that's also related to the challenge where you want to have a wireframe of a mass model plus the roof. The BREP structures became a bit more popular, I think, in the last year. And you see a BREP on the bottom right. You're going to have patches and you have boundaries. And then finally, CAD. I think multiple CAD generation papers, they use either just CSG operations or specialized CSG, maybe as sketch and extrude. Now, another class, I would say, of data structures are point clouds, for example, this one here. But this is hard to generate. There's no appearance information. So what became popular in reconstruction first were Gaussian particles, where you also add appearance information in the form of ellipsoids and colors and transparency to make the points look a lot nicer. And if you look at these Gaussian particles slide there, this looks really great. So I would say Gaussian particles visual quality is really fantastic. And now, maybe 2 years ago, this was kind of a lot of Gaussian particle reconstruction, but recently you saw the rise of Gaussian particles in generative modeling as well. So then you have maybe point maps. Also last year, you kind of saw the rise of point maps, lots of point map papers at CBPR this year, and lots of them on arXiv in the last half a year, where the idea is to say that we structure the point clouds as an image, and this is easier to generate. So you really have an image, RGB, but every pixel also has an XYZ coordinate in space. So a point map is basically a slightly advanced and now more popular version of an RGB image plus a depth map. And now also very recently, ideas to do point map plus Gaussian parameters. So we go from the idea of Gaussian particles everywhere in space to the idea of the Gaussian particles are restricted to a regular grid aligned with an image. And then for every pixel, you also have this spatial location plus, ellipsoid information plus transparency. And the idea is, but this cannot be quoted, but Generally, my impression is that most deep learning architectures hate the points, and this unstructured idea of point cloud and Gaussian particle just doesn't work well. And these recent methods that kind of generate these Gaussian particles in a regular grid have been a lot more successful. Now, another very cool idea made popular by Trellis is the idea to have something like an occupancy grid. So an occupancy grid is like a binary 0-1 grid that says, is this voxel in space full or not? And then you can also have an occupancy grid plus feature vectors. So it's kind of this binary grid, but every voxel in space has now some feature information attached. It's basically a feature vector that you can then process with a transformer. Now, distance field comes in multiple variations: signed distance field, unsigned distance field, truncated signed distance field. And seems like truncated signed distance field makes intuitively a lot of sense. However, also the occupancy field is very good. It's basically similar to a truncated signed distance field in practice, but it gives the network a bit more freedom how to encode an isosurface. Now, one of our recent methods is another interesting data structure that we tried to study, that is a distribution-based data structure where a single shape is basically encoded by a distribution. And so this is something that kind of mixes surface representations with some work in the diffusion literature to come up with a data structure that is robust to all sorts of geometry artifacts and can basically encode almost anything. All right, so now we discussed some data structures, and these will be used now in all these subsequent methods that I'm going to discuss. First category was multi-view diffusion plus multi-view reconstruction. So what we do is we start with some noise, we throw it into a diffusion model. Now almost everything's a transformer, and then we have multi-view images. And could be 4, could be more. Then we have reconstruction. This is a separate network that then generates a 3D model. Lots of design choices. Let's again, we have the pipeline at the bottom. How many output views do we want? 4? Do we want 6? More? All of this has been kind of tried out. Using a diffusion model versus using a video diffusion model versus image diffusion model. So should we do multi-view images, or should we do, let's say, a video going around an object? Then what is the output actually? How do these multi-view images or videos look like? Are we going to generate them images only, RGB, or are we going to do the point maps that are popular now, or also point maps or depth plus normals? So another thing is, what is the output of the reconstruction? Mesh, NeRF, Gaussian particles, what are we going to do? So these methods, I think a lot of them published within the last 1.5, 2 years. So virtually all combinations have been explored here. Let's go to some methods I want to highlight here. It's always an issue advancing the slides. All right. Not really sure why. CAD3D, very important paper, mainly because of its results. So first part here, when you look at this orange box, multi-view latent diffusion model, it takes in a set of known views. These are the blue boxes, and a set of unknown views. These are the red boxes on top. So for each view, we encode the view as Blücher coordinates, these ray coordinates, is a very popular data structure now to encode views. And we have the views for all the observed views. So we have the coordinates for all the observed views, and we have the coordinates for the new views that we are going to request. Now, imagine that this would be done for about 8 views, 3 known, 5 new ones. That's a typical setup. And you can use this many times. So let's say you want to generate an object. Maybe you start with 1 or 3 known views, and then you generate 5 more, and then you go locally and you invoke this many, many times to generate lots of views of an object. And then you go and call some 3D reconstruction method afterwards. Stable virtual camera, I want to highlight the main thing that I found interesting about it. They have some discussion in the paper. Should we start with an image generation model and teach it to generate multiple views? That's kind of one brand of work that we saw. Or should we have a video model and then teach the video model to kind of go around the object? And there are advantages and disadvantages. There's some discussion about that, which direction to go. And they come up with some idea of maybe combine the two in some way. So it's kind of does some video generation and multi-view generation. This may be the, I don't know, let's say it's one of the most important papers now called 3D. And you see, similar to CAD 3D, they start with the idea. We look at the first column here, A, set of seen and unseen views, where blue is known and red is unknown. And then we not only generate the images, but we really generate point maps now. That means for every image we have RGB, but also the XYZ coordinates. And then after we have these image plus point maps, we add another network that generates the Gaussian particle information. So now what we are left with is a lot of views that we generated, but for each view, we have the Gaussian particles that are view aligned. It's a bit weird, and it is surprising that it works as well as you can see on their websites. So it is unclear how much cherry picking and how much kind of trying many things that requires. It's not publicly available, but the results are really incredible. And I think this shows the importance of having the Gaussian particles generated view aligned, that it would say most papers you see within the last half year on arXiv, they would, if they generate some Gaussian particles, they would do them view aligned. All right, I'm going to skip that. That's some work from my collaborator. Now, we can also do multi-view video diffusion plus reconstruction. So what we do here is we take kind of the same pipeline, but if we do multi-view video, we are going from 3D generation to 4D generation. Now, CAD 3D, very good. CAD 4D, also very good. And so here the idea is to, again, have this more or less model that can request an arbitrary view from an arbitrary position and an arbitrary time step. So you basically have a grid of frames where one axis changes the camera position, the other axis the time. And this model lets you request whatever frame you want in this grid. So if you have something as shown in the first column, it's kind of regular video. You usually change the time with every frame, and you change the camera with some frames. Or you could have a static multi-view set of images, or you could have a fixed viewpoint and just change the time, or basically what we call is a 4D video. It's a complete grid of frames that vary in time and in the viewpoint. So we had my collaborator Chai Yang from Snap he developed a sequence of papers to kind of improve this 4D video generation. And this one is at CVPR. And this is for real video at CVPR, for real video V2. Was released on Archive last month. And this one basically studies the different ways to generate a grid of frames. So if you look at the first image here, the first column, we have the goal to generate a grid of frames that vary in time and in space, and every frame itself consists of many latents. So every small green box here is an image patch. So we basically have a 2D grid of grids themselves. So we have basically this XY variations for the image patches, then the time, and then the view variation. And there's 3 different architectures that have been studied. The last one is the one we advocate in this paper. The first one, you saw that a lot was in the last 2 years. It's kind of, no, it's actually the second. So the second one, let's say sequential, people said, okay, we have already this one form of attention, and maybe we'll just take an architecture that we have and we enrich it with a temporal layer. So you see maybe a spatial layer in red, and then you have a temporal layer in yellow. And what you do is you always process a column of frames or a row of frames with a pre-trained layer that you already have. And then you need to train your new layer, which kind of chain goes across time. So sequential was the first architecture that was tried. And for real video, what we did is we proposed something where you can do this in parallel, which has the big advantage that you can only use pre-trained layers. So now not only the red layer is pre-trained, but also the yellow layer that goes across time is pre-trained. And then there's some synchronization. So we significantly reduce the change to the architecture that is required to make that work, which improves the results by a lot. And then finally, for real video V2, we advocate an idea to just change the attention mask and the embedding to basically have no new parameters in the whole network, and we can generate much higher quality. So these are some examples of multi-view videos where you see different viewpoints and how the video changes over time. Some other results, modifying some known data set. All right. Now we have SDF generation plus texture generation. So like noise, then we have diffusion, sign distance fields. This is no color, so you need a second network, another diffusion, where you add texture. So this has been very popular in the last year, I would say a half a year. So a lot of the work actually is based on what Weiss Biao did during his PhD, which is an autoencoder to represent sign distance fields really well. And when you look at these top performing methods, starting with clay, these are scaled up versions of Biao's work that also added this texturing part. So clay, it's kind of last year. Yuan 3D is maybe still the best method now. And a more recent one, Step 1x 3D, that was released recently. So first part is the geometry part, where you generate this sign distance field. And then the second part, you texture it, and you get some nice results. So let's see how that looks for 3D models. I just asked my student to do different types of inputs, aerial views, street views, and this is generation from a single view. I think looks very promising, but detail quality is not that high. The rendering itself is not top quality, but it's kind of intentional, so you see maybe a bit more of how the geometry looks like. If you use a better renderer, it looks a lot nicer. So this is maybe unfairly highlighting several of the artifacts. So I tried different heights. So there's a bit taller building, some smaller building. And you see not only can you get the plausible reconstruction of the front, but a very nice completion that makes sense from the back. Now, this is now Street View, just copied from Street View images. Again, you get nice reconstruction of the front and the plausible completion of unseen parts. It works also for urban style. It's a European style urban buildings and a bit higher. This is again some high rise that was generated from other examples. Now let's look at trees. It does something, but it doesn't generate nice leaves and branches. It's more like a tree cloud, let's say. Okay, finally, I think also very cool work. The idea to do, I'm just going to show trellis, 2 steps. First, you have a diffusion model that generates a sparse structure that is just the occupancy grid. And then the second diffusion model generates the feature vectors, the appearance for each of this. So why is that so good? Because the model really struggles to generate the sparsity pattern and the content at the same time. You would have some sort of a variable length transformer, and this separation really breaks down the whole task very nicely. So now what you have is you have the ability to have output the, let's say, variable length structure, because the sparsity can be different, can be very sparse, can be very full. And then you have the content. So it's Trellis itself is not nearly as good as Huan Yuan 3D, but you can scale that up as well. So one recent one, Direct 3D version 2 that came out, that also builds on this idea of generating a sparsity pattern, has like very detailed geometry. So I didn't get to analyze this a lot. It's a fairly recent paper, but I think people were really impressed by these type of geometric details being generated. There's dynamic SDF generation, just for 2 examples. So you could, for example, generate one shape and then generate the motion, or a more recent example from CVPR here. But these methods do not have competitive training data, so it's too early to tell how good they will be. Mesh generation, this has been popular, I would say, a lot last year. This idea is to say, okay, let's go to the language models, and instead of generating tokens for words, let's generate some tokens to generate meshes. So these are several papers that I really liked. That Mesh GPT started maybe, and then several other ones. And still with meshes, the main issue is that you have these methods and you can directly generate as a mesh. That's one idea. It's maybe Mesh GPT. Or you only use these architectures to triangulate the shape that's already given. So a lot of these, they don't actually generate the shape. They take in a point cloud that defines the shape, and then they output the mesh for the shape that's more or less given. So one of the works that we had in this area is proposing an architecture built on 2 ideas. One is this UNet style transformer that reduces the tokens in the generation, and the mix of linear attention and regular attention for higher efficiency. And this gives the model that at this point in time can generate the most complex meshes. Now, the generation of meshes is a lot more difficult than the mere triangulation. So this is still not there where the SDF-based generation methods are. However, for something like urban modeling, this seems to be very interesting. All right. So with that, thanks for the attention. I may have some questions to pose. That's what a question that was discussed at yesterday's area chair workshop at CVPR. Should we provide 3D information to the 2D image or video diffusion model to teach it about 3D? That's one idea. Or should we learn 3D information from the 2D image or video diffusion model? So do we just generate the video and reconstruct, or do we need to give the video diffusion model kind of the 3D shape idea in order for it to learn 3D? Does the video image model need our help to learn about 3D, or is it going to teach us? This question was posed for physics. It's the same question. Do we need to teach the video model the physics, or does the video model teach us the physics? It's a very interesting question. Of course, you have both answers represented. And the other question I find is interesting, irregular data structures versus regular data structures. Very important for urban modeling. If you do urban modeling, you would be tempted to use CSG, B-reps, wireframes. These are the natural data structures for urban modeling. But the networks really, really like regular data structures. So let's say you want to generate a B-rep. Why not generate an SDF brute force first, and then just try to extract some reasonable boundary representation. So let's say for the challenge there that was posed, do I actually want to directly generate my wireframe, or do I generate an SDF first and then I just extract the best wireframe I can? So my answer right now is, wild guess, maybe more than an answer, is that the method to generate the SDF first, the nice regular data structure, will give you better results. So don't generate maybe the wireframe directly. First generate the SDF and then try to extract the wireframe. All right, thanks, and I leave it at that.
Very interesting that you look at yeah. It's just for the virtual attendees. Yeah. Very interesting presentation, Peter. Very nice to see how we evolving towards generation of data for multiple modalities and so on. My question is related to what are the current status when it comes to resolution that you can achieve for the different technologies that you present.
All right. So I would say that it's a bit difficult to answer. So to think about the power, I would say that meshes and the structured representation are far behind the other two versions. And I think you saw the best, let's say, more details. I don't know if that's exactly what you mean with resolution. I think you see it for the sign distance field plus texture generation. And then I would place this ahead of the other multi-view generation and reconstruction now. And this is another kind of interesting philosophical discussion. So if when I gave the talk last year and you heard all the other invited talks, it seems that people were extremely excited about video, and they were extremely excited about the idea that the video model is going to teach us everything. So we'll just generate the videos, and then the video, we do all the 3D construction from the video. I don't. So I felt, that there's just so many people arguing this. I'm still not 100% sure. So I do feel that this sign distance field generation has probably the better quality now. And I would also feel that it may have the better quality in the next year. So that kind of answers the question that I posed. I feel it is better to teach the model about 3D rather than trying to learn from the 2D model how 3D looks like. At least for the next year.
Yeah, please.
Oh. Exciting how we things very fast paced and even 2 year researchers sometimes outdated. And we deal mostly with like classical computer vision, not AI. And then and my question is more towards the addresses the times of the reconstruction. And when I use conventional methods, I can lower resolutions and do kind of manipulation, all kinds of manipulations to have a much quicker result and with a low quality. But at least from my experience, when I tried to use SDF and various kinds of AI models, and when I try to make it faster, like give it less data or some lower resolution, the results are so noisy that it's unusable. It's not like a little bit worse than the product that we can use for primary use, for first initial use, and then take the time to improve it. And other methods to make it quicker and have usable results, even if the quality is lower.
For sign distance fields.
Yeah.
So, I mean, I think one issue with the sign distance fields now is, I mean, I guess almost all of these three, a lot of the methods that you saw in this talk are slightly outside the range of academic research. So when you think about training some of these models, I think almost all of them need about, my guess is close to 10 nodes or 80 GPUs for the project. Otherwise, no chance to be competitive. And so I think that's true, unfortunately, for all these three. And so that means it becomes very difficult to do something new that doesn't start with one of these models and then tries to modify it.
Yeah, but there is, like, for example, several in NVIDIA and work, inference works, you can say in real time, but to extract like 3D data that is good for measures, for measuring the distances between points, it's still not usable.
You mean the accuracy itself, or for the reconstruction or generation?
For when you use, for example, for NERF, this is the only implementation I know that provides data that looks okay.
Mhm.
In short amount of time, but it's still not usable if you measure them. If you compare the measurements to run proof, until it works a substantial amount of time, it's still the accuracy is very low.
So I mean, the question is, if you do pure NERF, then there's an issue. Same is true for Gaussian splatting. You do not really have a surface description. So then the question is, how do you even measure the distance? And so this goes, so then there's the issue of, do you take these original methods, NERF, Gaussian splatting, that look really great, but actually they don't really decide where the surface is, or do you use some of this extended methods that force it to decide where the surface is or extract the surface and measure there, but then the quality goes down a lot.
Yeah, the question is whether there are some of these advanced methods that also work in short time, like the original nerve, which has optimization that does work.
But I think I would say that most methods published on arXiv the last half a year, they are not like that. They got the most publicity. They left the traditional Gaussian splatting and nerve. They are all about feed-forward generation with a network, and there the quality is maybe even worse. But I think that's what most people try to do now is to.
But will they still work? Will they see good results in short time?
Yeah, they're very fast, but the quality is even less probably than this. You will like the quality even less, but it's much faster than Gaussian splatting. So if you use VGGT, you get results in a few seconds and faster. You have like very large transformer-based networks. You can give 10 to 1,000 images and you get the 3D model almost instantly back. And it has mediocre quality, but it's very fast. And it's not only in reconstruction, it's also this both 3D in generation. People try to kind of do this feed forward and generate these point maps, and it's also very fast.
Small question. Thank you.
Thank you for the presentation. So my question is, you mentioned about Gaussian splatting technology. How do you think this can help to enhance the structured 3D solid model construction? For example, for urban cities, 3D city construction.
Well, I mean, I would say that the question is the traditional Gaussian splatting that was optimization based. It has like really nice results. But of course, this is kind of 1 year ago. This year is the time of the feed forward models, and there, I think the people are still trying to improve the quality. The feed forward models, they will just generate these image aligned Gaussian point clouds, and I think they will be fast and also look good, but quality may still be an issue.
Okay. The time is okay. Example 10. You I move to next one in the
520.
So I will keep my thank you very much.
Try to come back.
So that highlight about is that because have the perspective and that we make it specific applications of the planet and not that improve output. So we do this with this data set. We use some
That's it.
Oh, sorry about that. So, talk about building 3D data set and the real challenges on this data set. They are missing point structures like corners, and the distribution of wireframe models with different level of difficulties is shown on the red figure. So it's very diversified data set, and the point cloud is in balance. Some buildings are very dense and some buildings are very sparse. So we released this data set in 2023, around November. So far, we already have more than 20,000 visits, and we have registered 29 users for this data set. And this year challenges, we add another new dataset to the Building 3D, which is we use Tokyo OD2 dataset. And this dataset is publicly available on internet. They provide the mesh models and the point clouds, but unfortunately, the point clouds and the model are not aligned. So in order to for training the neural network, we use a mesh model, but we use simulated point cloud. We sample point clouds from the mesh models. So we prepare around 29, more than 29,000 buildings for training, from Tokyo OD2 dataset, and use more than 3,000 buildings for testing. Then we combine the Tokyo dataset with Building 3D together for this year's challenge. So basically, you have around maybe more than 60,000 buildings for training and around maybe 6,000 buildings for testing. I can see the Building 3D dataset and Tokyo LOD dataset. They are a little bit different. For Building 3D, the most number of edges and corners are around 70, but for Tokyo LOD dataset, there, the maximum number of the edges or corners reach 140, more complicated than the Building 3D dataset. So this is our competition, the timeline. I think we, the workshop starts, February, this year, and but the challenge is launched March 1st this year, and the completion date is June 4th, 2025. And the write-up, we're still waiting for the write-up from the authors, and for the competition submissions, each team is limited to 4 submissions per day, with a total of 40 submissions. So the evaluation metric is pretty much similar to last year. We use average corner offset, ACO, and use corner and edge precision, and record the F1 accurate. Another metric will be WED. It's is a wireframe edit distance. So the WED, the number from 0 to to a number greater than 1. If the WED equal to 1, which means we need to create a wireframe model from scratch, from empty results. If WED equal to 0, which means the perfect, the reconstructed model is identical to the ground truth. And when WED greater than 1, which means we have a lot of negative edges, which need to remove. So this year we have, the winner. We have, 5, one first place, second place, third place, and 2 honorable mention. With tech sponsor from Alibot and Water Spatial. They sponsor $10,000 for this competition. And we have 7 teams participated in this competition. And the first place is from, Yu Zhou Liu from Institute of Automation, Chinese Academy of Science. Later on, we have the winner talk for those winners. Second is from Hao Rangong from School of Software Engineering, Xi'an Jiaotong University. And the third will be Yujing Liu from Shenzhen University. Unfortunately, because of visa issue, they cannot come to present their results, but they provide the video or the Zoom link, Zoom talk. I think the first one will present on Zoom. Honorable mention, we have two, one Daniel, Sarah from University of Padua, and Wei Xiaogao from TU Delft, and Wei Xiao will present in person here. He's coming here. This is a building 3D team, the Sangfeng, my PhD student. Now is, I think it's the time for winner talk. The first talk will be, I think he will join on Zoom, right? So, let's see. Okay. Yeah. This is on Zoom, right? Yuzhou Liu.
Might have to unmute.
Unmute him. You see.
Oh, you're not in here. Okay. Not on Zoom?
I'm on this. Oh,
Why?
why? Zoom. So
What is his name?
Yuzhou Liu here. Yuzhou Liu, this one.
Okay, he's unmuted. Yuzhou, can you say something?
Yuzhou, can you share screen? Start, okay.
But we still don't have his audio, yeah?
We cannot hear you. Can you say something?
Dimitri, do you hear us?
Yes, I do hear you. And it seems that mic is not working
Okay,
in usual.
Yeah,
Okay,
we
now
hear you
it's
too,
muted.
Dimitri. So this is a problem on the other side. Yuzhou, you have a problem with your mic. Yeah,
Yuzhou?
still no sound from you. Dimitri, can you say one more thing?
1, 2, 3. Still no sound. If you open the participant thing and there is mic animation there, like now it's active for me, and
Unmute. Oh, yeah.
Unmute the person.
Hello, person.
that mic is still empty.
Okay, he's now off of mute. Yuzhou, it now says you're off mute. Can you say one more thing? Okay, we still don't hear you, so maybe we should just play the video.
Sure, yeah.
So sorry about that. We're gonna play the video.
So we'll play the video. Okay.
My name is Yuzhou Liu. I'm sorry that I could not be here in person for visa issues and can just give the talk online. It is a great honor to win the building 3D challenge and represent our team through in Jianzhu, Anqiaoye, Lianggao, Wuhanshe, and me. From the Field of Coordination and the Academy of Sciences to share our work with you here. First of all, I would like to start by expressing my heartfelt gratitude to the organizers of USM3D workshop for their great efforts. After that, let's now move on to the talk, today's presentation. There are numerous challenges in reconstructing building welfare from urban data point cloud. such as lack of stable point cloud dataset welfares. Yes, thanks to building 3D. Sparsity with viewpoints, incomplete areas, noise from trees or other buildings, and manual structures like chimneys. To solve the difficulties above with synthetic head maps, 2D to 3D corner detection with reduced search space, and holistic edge attention, DW formula predicts the final complete welfare. The motivations behind include 4 aspects. First, due to the 2.5D data characteristic of L1 reader point clouds, there is no roof air cushion, and restoring 3D roof structures from 2D input is possible. Second, for 3D corner detection, there is a large search space, and the 2D to 3D corner detection will simplify the problem. Third, with 2D and map as the input, the utilization of mature DETR-based network is possible. Last but not least, the data documentation and edge attention are specially designed for the sparser incomplete point clouds. Here is the overall architecture of DW format. With real head maps projected from point clouds and synthetic ones from simulated data scans. DW format first detects 2D corners and then initializes the 3D corner queries with 2D positions. Third, with a transformer-based network, the 3D corners are predicted. Finally, edges are classified valid or not, while valid ones form the final wavelength. In the 2D to 3D corner detection process, after the 2D corners are detected from the head map, 3D corner coordinates are explicitly represented by 3D corner coordinates. In this way, 3D corners with the same 2D positions are different heights to be distinguished. With 2D corners detected, the first 2 dimensions, x and y, are initialized with them, while the height dimension z is randomly initialized. In the decoder, reference points are the 2D positions. Header offsets and corner labels are predicted with 2 MLPs from the component coordinates. And the final 3D corners are obtained with the corner label predicted and valid. Well, for edge detection, a candidate edge can be represented by 2 candidate 3D corners. Due to the sparsity, incompleteness, and noise of the L1 leader point cloud, it is challenging to determine whether a line connecting 2 corners is an edge or not. A vanilla deformable attention in edge detection. The reference points are placed at the middle points of edges, attending to only areas nearby. However, it may fall short of a holistic understanding of edges. And it is necessary to pay attention to the whole edge and extract local details from different positions. To this end, we propose the edge attention mechanism to enhance the holistic perception of edges. We uniformly sample M reference points along the edge. Then the edge content queries are replicated M times. The focus on the corresponding areas to the sample points. In the end, a max pooling operation is performed to aggregate information from all positions, and the edge feature is extracted holistically while the local details are also preserved. The synthetic process includes the LiDAR scanning simulation process, the head map synthesis process. The LiDAR scanning simulation process is based on a conditional generation process. Taking the building footprint as the condition, a latent diffuse model generates the latest sampling locations accordingly. Third, we will mix the synthetic data with the real data and train them together. Experiments demonstrate the effectiveness of our method compared to other social methods, especially on top. As showcase the superior adaptation of BW format to sparse 3D point cloud with more complete reconstruction results. Here are some qualitative evaluations of our methods. And the BW format can reconstruct the complicated loop structures precisely. However, our method also suffers from missing the accurate corner and the edge detection. And here are some examples. Red box and red line mark the errors. For more details, BW format has been accepted in CPR 2025 and selected as highlight. Now code are available at top. You can scan this QR code to access it. If you have any question, you can contact me for further discussion and cooperation. Thank you all for your attention and support.
So there's no question because it's video recording. So let's move to next panel talk. So it's
If anyone does have questions and missed the QR code, find us later and we can connect you.
yeah. Oh. Yes. Very slow. No. What's one? This one. The PPT is huge, so oh. Oof. What's one? Oh, this one. I think yes. What? Very slow.
Hello everyone. It's a great honor to be invited to present our runner-up solution for the CVPR using 3D challenge. We are from the 3D CO lab at the School of Software Engineering, San Jose.
You have it on your laptop? That's just like a regular file?
Yes, yes.
Okay, can you play that
From
and change the screen sharing?
Chrome.
Hello everyone. It's a great honor to be invited to present our runner-up solution for the CVPR using 3D challenge. We are from the 3D CO lab at the School of
Maybe.
Hello everyone.
Yeah.
It's a great honor to be invited to present our runner-up solution for the CVPR using 3D challenge. We are from the 3D CO lab at the School of Software Engineering, San Jose University. My name is Paul Gong, and I'm currently a first-year graduate student. We achieved the second place in the Building 3D challenge with a WAD score of 0.371. We addressed the challenging problem of building rooftop reference reconstruction by decomposing it into several sequential subtasks. Our approach leverages a multi-stage pipeline that integrates handcrafted geometric descriptors with advanced structural modeling, pushing precise and robust reconstruction. Our process unfolds as follows. We first extract FPFH in our normal multi-scale lift geometry descriptors, MRGB, from the input roof point flow. These descriptors are crucial for encoding both local and contextual geometric properties. These descriptors are then fixed via a hypergraph attention fusion module, yielding a compact representation that is concatenated with the original XYZ RGB attributes. Subsequently, point-wise features are extracted and processed through a binary classification network. This network distinguishes candidate corner points from non-corner points, while simultaneously learns offsets to shift these candidates toward their nearest two corners. The resulting candidate corners are grouped into clusters, each representing a potential corner, and their essentials are determined using an unsupervised clustering algorithm, serving as initial corners. A refinement network then learns individual offsets to shift these initial corners toward true corner positions, generating highly refined corners. Finally, an edge classification network inserts the topological relationships between points to classify edges, completing the wireframe reconstruction. This is the detail of our network architecture. Now let's dive into the main techniques that significantly improve our performance. The first one is segmentation of complex lift geometries. Through observing the characteristics of the Tokyo dataset, we discovered that complex buildings often contain multiple individual roofs. Analyzing the topological relationships between different roof segments introduces additional computational overhead and increases training difficulty. To address this, we designed an enhanced Euclidean clustering method that effectively incorporates both spatial proximity and height differences to group points belonging to the same individual roof. This pre-segmentation simplifies the subsequent reconstruction task. The second one is learning rich rooftop point cloud features. Multi-scale roof geometry descriptors is specially designed to employ a multi-scale neighborhood strategy to capture both local and contextual geometric information. For each point, we construct two sets of nearest neighborhood using the keying algorithm to form a small-scale neighborhood and a large-scale neighborhood. We then compute curvature, age variance, and spectral features within both neighborhoods and calculate their differences using a Gaussian kernel function. This captures a comprehensive geometric understanding. Effective feature fusion is crucial for roof reference reconstruction from point clouds, especially when local geometric details and multi-scale structural patterns must be seamlessly integrated despite noise and sparsity. To this end, we propose the hypergraph attention fusion module to combine FPFH and MRGD into a robust representation. HAF addresses this by constructing hypergraphs to model neighborhood connectivity and employs a double attention mechanism. Intra-feature attention refines each descriptor by focusing on its most relevant neighbors, while cross-feature attention facilitates mutual enhancement between FPFH and MRGD, bridging local and structural domains. The third one is incorporating long-range dependencies and contextual relationships. We integrate the edge-com operation, which enables the network to learn edge-specific domain patterns by capturing both the spatial relationships and feature differences between connected points, thereby enhancing the discriminative power of the learning representations. To model these long-range dependencies effectively, we further integrate a transformer-based layer utilizing its self-attention mechanism to capture interaction across all refined color pairs. This enables the network to contextualize local edge predictions within the local structure of the building, enhancing the overall accuracy and the coherence of the reconstructed module. Finally, a multi-scale fusion module integrates multi-scale features by progressively combining input representations through a series of linear transformations. It concatenates features across scales, significantly enhancing the geometric expressiveness for robust point cloud processing. Thank you for your time. If you have any questions, feel free to contact me.
Okay, let's move to next video talk. Let's see.
Hello everyone, my name is Yujun Liu from Shenzhen University. I'm very sorry to attend in person today, but it's truly an honor to have this chance to share our solution with you. This change focuses on reconstructing accurate 3D wireframe models from area lidar point clouds. Compared to last year, this time a new test data set from Tokyo City was introduced. It brings some challenges such as missing key points like corners, multiple building styles, and highly imbalanced point distributions. To tackle this change, our motivation is to explore a new generative way for wireframe reconstruction. Inspired by recent success in diffusion model, we asked, what if we could generate clean wireframes directly from random noise? So our core idea is to reformulate wireframe reconstruction as a noise to wireframe process. The goal is to learn a mapping from random edge noise to high quality wireframes guided by point cloud. So the overall input and output of our method are the point cloud and the wireframe, respectively. During training, we first add Gaussian noise to the ground truth wireframes. This teaches the model how to reverse the computation process to recover clean edges. We also pad wireframe to a fixed number by repeating edges, length, and noise. This produces a batch of noise edges length represents different noise levels at inference with skip ground truth wireframe and just sample from noise, turning the task into wireframe denoise. To guide this process, we use the input point cloud as a condition. We could use a transformer-based point encoder, detecting both local and global geometry features. But not all points are equally important. So we introduce an edge attention generation module to assign weight to points. This highlights key geometry clues like edge and corners. These point-wise weights are then used to enhance the point cloud features. This helps the network focus more on important edge structures. Next, the noise edges are transformed into high-dimensional vectors, use linear layers and self-attention. This serves as queries in the noisy edge. We perform cross-attention between noise edges and the conditioning point cloud features. The cross-attention helps align noise edges with geometry things from the input. We use 3 hairs to predict the edge's midpoint, its offset vector, and a confidence score, are necessary to reconstruct accurate edges. This entire pipeline is repeated through a DGIM-based denoising loop. Over several steps, the noise edges are refined into manifold structures. We call this edge-aware denoising module. Finally, we apply the post-processing, non-maximum suppression, reverse database, and the DB scan cluster endpoints to ensure clean and connected wireframes. To sum up, we propose a noise to wireframe project based on a conditional diffusion model. Along with edge-aware guidance to enhance structural learning, we hope these explorations can contribute to advising wireframe reconstruction. Here are some visual results on Tallinn and Tokyo dataset. You can see that our reconstructed wireframe close to follow the building structure, even for irregular shapes. This demonstrates the effectiveness of our method. That's all. Thank you again to the organizers for this great challenge. I also appreciate the opportunity to present here. If you are interested in our method, feel free to reach out to me. Thank you.
Okay, so let's move to next speaker. We do have an in-person talk for this winner talk. This one. So Zoom link. I will share. Oh. Oh. So here's a share screen. This one. Okay. So where's share screen? Let's see.
Yes.
Oh, this one.
Oh, yes. Okay. Good morning, everyone. My name is Vishal Gao. I'm a postdoc in TUW at 3D Geoinformation Group. Today, I will present our approach, the roof fit. So it's an unsupervised approach to reconstruct the roof wireframe from every point clouds. So my first question is why I didn't win the Building 3D challenge. So this is our position. We are at 5. So we have a WED with 0.5 more or less. But if we look at the CF1, the F1 score of the corner and the edge F1 score, we are at the first and second place actually. This is the input and this is our output, but actually the ground truth is look at this. So given this comparison, we think that the ground truth is hugely deviate from the input point cloud. So which was indicating that the ground truth might creating using the other sources like the error image. So you can really know there is not it's not a gap, it should be filled. And second thing is we think that fixing this issue, I mean, like the gap or occlusion, compared with the reconstructing a roof wireframes are different tasks. So the second question is, how is our method working? So giving the input roof point clouds, we first extract connected components, and then we build the alpha shape mesh in order to extract the borders of the roofs. And then we get the border points. With the border, we can interpolate them to the vertical and ground because we want a solid model reconstruction. That's why we need a complete point clouds. So we use the border to do the interpolation. And then we do the classical region growing to extract planar structures. And then we apply the polyfit and also we apply the polyfit on each roof components. And then we apply the mesh pooling operations to merge all these roofs. And then we extract the roof surfaces, and then we extract the roof wireframes based on the roof surfaces. So we kind of from the 3D to the wireframe, the 3D models to the roof wireframes. And here's our visualized results. This is the results of the tiling. And this is the visualized results of the Tokyo. As you can see, the Tokyo is more complex, but we kind of can recover these complex structures. The next question is, what are the unique advantages of our method? So the first need to highlight, we don't use any training data or the building footprints. The second is we ensure the two manifold topologies and no missing edges at all. And we can achieve a higher fidelity and fitting quality. And we can actually direct generate the watertight building models like here. We also compare with similar approaches like Polyfit, City3D, KSR, and CoLoad. So we perform better. And the next question is, what are the disadvantages of our method? We think that we cannot recover the missing structure or handle sparse point clouds. We can also not, we need also rely on the quality of the over segmentation, such as the region growing. Then how should we better evaluate these results? We think we need to focus on the usability, not the re-editing of the wireframes. For example, giving the input point cloud, the middle one is the ground, one type of the ground truth. The right one is another kind. We think the middle one is better because it follows the original structure of the input point clouds. Unless we give other data sources, otherwise we think the middle ground truth is better. The second thing is giving this 3 kind of structures. We think the first and second are good. The first with wrong edge connections. The second with duplicate or let's say redundant edge points. But all of these are topological correct. We can directly use them to reconstruct 3D building models. But the last, either with one missing edge or a wrong connection of the edge, which is non-manifold, which we cannot get directly get a 3D building models without taking more efforts. So we think the ground truth should align with the row point clouds and the topological correctness is mattered. So the last question is deep learning is really necessary for this task? Well, I don't know, but I think there are at least 3 challenges it needs to solve. One is the generalization capability in case of sensors, regions, flight altitude, building types, such diversity, and also it struggles with complex geometry and no topological guarantees. So the future work is to reconstruct the urban scale loss 3D city models. And to achieve this, we need a data set. So here, I also want to do advertisement of our work, so which is the sum parts. So we build a semantic 3D city meshes models. And if you are interested, you can go to our post session on Sunday. Thank you very much.
Thank you for talk. I think it's our time. Now it's a poster session, but we really don't know where is posters. So please go out and find out the posters.
It is my absolute pleasure to introduce Despionia from NVIDIA and her talk, Leveraging Structured Generative Models Towards Compositional Intelligence. So let's thank the speaker and then get started.
Hi, everyone. Thanks a lot for having me today. It's such a bummer that I'm joining from California. I would have loved to be there with you guys. So can everybody hear me?
Yes,
we can.
Okay, amazing. Okay, let's start ahead. Okay, so okay, great. So I think I don't have to convince this audience that in the recent years, generative models have made impressive progress in synthesizing everything from text to images, 3D geometry, scenes, videos. And I think it comes without a question that although existing, in particular, 3D generative models can produce very nice pixels, very beautiful meshes. Sometimes they still treat scenes and objects as monolithic outputs. So what does this really mean? It means that when they generate a scene or a single object, they treat the entire thing as a single entity. So they generate everything in one go with little understanding of their internal structure or dynamics. However, in real world environments, we don't just have pretty pixels, right? We have scenes are composed of semantically meaningful parts that interacting with one another. There are also rules that govern motion, physics, and affordances. And I think that to be able to actually build and truly understand and also reason about these models, we need to move towards more structured generative models that reflect this compositionality, controllability, and interactivity. So these capabilities are not only more aligned with the human reasoning, but critical also for applications like simulation, robotics, AR, VR, as well as, of course, autonomous systems. So all the work that I have done, both during my PhD and postdoc at MPI and Stanford, and now a bit at NVIDIA, actually tries to explore how to inject this kind of structure from scene layout to part-aware object generation to agent behaviors directly into the generative process. I think diffusion-based generative models have enabled unprecedented capabilities when it comes to generating objects and scenes, both in 2D and 3D. Namely, we're able to create high-quality assets with or without texture directly from prompts or images. Here you can see like some of the methods that completely transformed the 3D generation. And once a scene is generated, although it might look very nice, it's very hard to modify, refine, or even make sense of its components. So there is actually no easy way to isolate an object within a scene or isolate an part within an object, change its position, adjust its relationship with the rest of the scene. So these models absolutely excel at realism, but I think they fall short in terms of controller structure, which is a very critical ingredient to be able to actually make interactive applications that keep the humans in the loop. Let's talk about the editing, because I think it's one of the most obvious cases where structure and compositionality can shine. So as we said before, generative models can generate impressive assets. This could be full scenes or objects, but once you want to make a change, you hit a wall. The problem is that there is no object abstraction, there is no part abstraction. So everything is baked into a single mesh or a single volumetric field or just an implicit function. So you cannot just say, you know what, I just want to change the color of the hair of this girl, because actually it's very hard to identify what is the hair. And of course, these days you can use LLMs to say, okay, you know what, the VLM can guide you and say, this is probably the hair of the girl. But we don't have so good VLMs that can also reason in 3D, technically 3D grounded VLMs. So the alternative that we have, at least when it comes to modeling 3D object geometry, is compositional representations, where objects and objects parts are separate and controllable. And this makes a huge difference, not just for editing, but all sorts of reasoning, simulation, and interaction. So, the need for compositional representation becomes even more apparent when we try to think in the case of entire scenes. Like think for example that you somehow generated a 3D room and you just want to move one object within a scene closer to another object. In most generative pipelines, there is no easy way to do it. You'd either have to rerun the model, tweak your prompting, manually edit the raw mess, re-render a couple of views, and compute Gaussian splats as soon as you completed your editing. And I think this is definitely not optimal. And one important aspect that these generative models could bake into their representation is compositionality. And why is this? Because compositionality let us break the scene into meaningful edited units, each with its own geometry, semantics, and relationship to others. This enables us to easily select and interact with individual entities in the scene without having to worry about stuff that we actually don't care about interacting with. This is something that would definitely open up even more interactive applications when it comes to design, simulation, robotics, and more. So in the rest of the talk, I will talk through how we bring compositionality into 3D generative modeling, from scene layout to object parts, as well as a few things about dynamic interactive agents. Now that we've seen why compositionality is important, let's talk about what makes 3D editing and 3D interacting in generally hard, and what do we want to get from our models ideally. So first, we want structural control, right? What is structural control? Structural control means that you can change a part of the object, let's say a handle or a backrest, without breaking its identity, without also breaking its physical properties. There are a lot of people that are actually working in this direction. And this was kind of the idea that motivates models like PASTA, where we explicitly learn part-aware disentangled representations of objects, hence enabling controlled recombination and editing of 3D parts and 3D objects. And then there is also the question of appearance versus geometry. So in a lot of generative models, these two are deeply entangled. Namely, you cannot change one without affecting the other. To address this in partner, what we try to do is we suggested learning compositional neural fields where the appearance and shape of parts can be controlled separately. This is a key step towards realistic but editable 3D assets. And finally, although these are nice when it comes to editing simple shapes, both Pasta and Partner lack fidelity and scalability. So in CAD, what we tried to do is we said, there is like 2D diffusion models are becoming a powerhouse and we should totally use them. So in this work, we explored distilling the power of 2D diffusion models like StyleGAN and Stable Diffusion into compact, mesh-compatible 3D generators, which allowed us to compute realistic shapes with explicit geometry. So in the next few slides, I'll want to show you how Pasta, Partner, and CAD each address different facets of these challenges that we discussed and how they point toward more general controllable 3D editing systems. For partner, what we did is we represented each object using M parts, where every part is locally defined and parameterized as an F. What does it mean, locally defined part? It means that it is associated with an affine transformation, which controls its location in the scene and orientation. It also is equipped with a scale vector, meaning its spatial extent, what part of the entire scene will this part occupy. And it's also associated with the shape and the texture vector that control the shape and the appearance of each part. And our idea here, because this is a CVPR 2023 paper, was to associate a part with a color network and an occupancy network in order to predict the color and the occupancy values respectively. So we wanted to make sure that each part will occupy continuous regions of the object. And we did a standard trick that many people do in compositional representation. So we bounded each part by an ellipsoid. And as a result, the occupancy function of an axis-aligned 3D ellipsoid was combined with the occupancy function of the mth part parameterized as an F. And what we did that was a bit unorthodox was, instead of predicting volume densities, we predicted occupancy values. And we ended up having this rendering equation for each part where technically every individual entity is parameterized with an occupancy value and its color. I think the major contribution of this work was the idea that we had that you need to disentangle geometry for appearance. So what we did here is we thought about it and we said, you know what, it's not only that we want appearance and geometry to be disentangled, we also want to be able to interact with individual parts of the object without actually messing up with others. And to do that, we introduced a hard assignment between rays and parts. And this unlocked several editing capabilities, as you can see, as we will see in a bit. And the most important thing is that it simplified a lot the rendering equation. So technically, rendering the equation of the entire object is simply a combination of rendering its individual part. How does the entire object generation looks like? So we start from a set of pairs of posed 2D images and object masks. Unfortunately, in this work, we are also using object masks. And it's not only that, we also use posed images and object masks of a specific semantic class, meaning that this can be cars, chairs, animals, but they all have to be part of a specific semantic class. And what we did is we implemented our generative model as an autodecoder. So the autodecoder exists of three core subnetworks. The first one being the decomposition network. Here, what we do is we map the latent codes that control the per part shape and texture. And then we have a structure network that predicts the pose and the scale of each part. And in the end, we use a neural rendering network that renders a 2D image using M locally defined nerves. The final rendered image is simply the composition of the per part renderings. So let's see how well it works, right? So first, I want to motivate a bit better the importance of hard ray part assignment. So why hard ray part assignment is important is because it allows you to actually interact with individual parts of the object without having to mess up or even worry about what's going on in the rest of the object. So for example, here you can see that we rotate the bucket of the tractor. Here we just cut the cockpit and just put it like on the floor. We can scale, or we can even change the color. So let me show you how things would look like if we didn't have the hard ray part assignment. If we were to do the same editing operations, you will see that also the rest of the object would be affected. And this is because everything is entangled into a single representation, both geometry and appearance. So I think this is a very nice toy experiment that clearly shows the importance of compositionality and structure when it comes to object and, of course, in the scene editing, as we will see in a bit. Okay, let me show you some of the shape synthesis results. So partner is a generative model, meaning that we trained this autodecoder on motorbikes, on airplanes, and chairs, tables, and ShapeNet cars. And you can see that, of course, the quality is not like super high photorealistic, as you can see, but still it's able to produce consistently meaningful objects of different semantic classes. Another cool thing, as you can do with all generative models, is that you can do shape interpolation. What I love about this paper is that although we interpolate across shapes, you see that across all interpolations, the geometry remains meaningful. So you always consistently have a meaningful 3D bike, as well as the part decomposition. So you can see that consistently the same part is used for the tires or the back of the motorbike, and you can even go from a scooter to a bicycle and this geometry remains the same, which I think is a very cool feature. Here are some more shape interpolations where you can see that, for example, the part of the car becomes, like the back of the car becomes bigger, the tires become larger. And also for the case of airplanes, we can interpolate between different airplane types, such as starting from a stealth and going to like a more like traditional airplane that we use for traveling. Another cool thing about PartNerf is that you can also do part interpolations, meaning that you can select two parts from two different objects and actually interpolate between these two. And here you can see many different examples, right? We started from this part and this part, and then we do shape code interpolation. So while keeping the geometry and the appearance of this motorbike fixed and the remaining geometry fixed, we only interpolate the back, this single component. And we can also do these things when it comes to texture code interpolation. So in this case, we took the texture code from this motorbike and the geometry of the first one, and we interpolate that part such that the texture changes. I think although the visual quality of these results is not as amazing as Bolt 3D or Edify or all these great 3D generative models, I see a lot of value in this work because it unlocks amazing capabilities that were not possible before. And the amount of control that you have through structure and compositionality is actually very nice. So here are also some more things that you can do with PartNerf. You can do shape mixing, such as, for example, select the upper part of the chair and the bottom part and just combine them together and do all sorts of things where, for example, you select and keep the texture of the second chair while changing also the texture codes between these chairs, which I think is cool. So I think PartNerf was a very nice and very cool idea because it was the first to introduce like this concept of part-aware generative models that actually parameterize parts as nerves, and it enables intuitive part-level control through the heart assignment that I just showed you. And one thing that I find very cool is that it can be trained without any explicit 3D supervision. One issue, of course, is that the quality is not there yet. I think we can probably easily solve this by using GAN losses or triplane representations. We never ended up doing this, but I'm sure that if someone combines this concept that we introduced here with any of the fancy 3D generative models, the interactive capabilities that people could achieve would be brilliant. And last but not least, the generated parts are not always semantically meaningful. You can kind of see this here where I was showing the part decomposition. And this probably makes sense because the signal that we have is not that strong. There is also no supervision when it comes to part decomposition, so the model does what it's the most convenient thing for it to do. I think this is another important topic that could greatly benefit if we were to use language and LLMs efficiently. Technically, we can use LLMs as a guide towards what is the desired level of granularity, what is the desired level of decomposition that we want to achieve. And I think this is a very exciting thing to think about. Okay, so moving forward, what we did next is said, okay, you know what, PartNerf is cool, but you can, of course, edit the individual components, but what about if we want to have even more versatile user input, such as, for example, saying, you know what, I have like this box, and I want within this box you to feel me like a chair, or like make a really tiny chair, or for example, do image-guided shape generation, or for example, text-guided, or create part variations, or complete shapes from partial input. So the idea of unlocking even more capabilities when it comes to versatile user input control inspired the pasta. What we did here is that we introduced a model that comprises of two components that are trained independently. The first component consists of an object generator. This part autoregressively generates objects as unordered sequences of labeled parts. And then we have a blending network that composes these part sequences in a meaningful way and synthesize high quality implicit shapes. And the first component is trained using annotated cuboidal parts, meaning that we have the supervision in terms of the decomposition of the object, and the blending network is trained with 3D supervision in the form of occupancy pairs. So in comparison to partner, you see that for this pipeline to make it work, we really had to increase the amount of supervision that we used. But we can also do cool things with this one. Starting from partial inputs, we can complete shapes in a meaningful way. We can also do stuff, we can do the same thing also for tables, not only chairs. And you can, of course, also do text-guided generation, right? So this model was never actually trained with text. We just use clip features as a guidance. But because the image and the clip is in the same space, you can actually do stuff like a chair with 4 legs, a central support, and sofa-style arms. And it looks like this, which I think is very cool. And you can also do image-guided shape generation, exactly because we were using clip features. And you can get realistic objects that match the input image. So I think pasta is another example that shows that compositionality and structure unlocks a lot of editing operations. We again use the idea of autoregressive transformers, and I think this is something that the community should definitely explore even more, because what I like a lot about autoregressive transformers is that it's very easy to know when to stop. So when it comes to generating these structural objects, one of the main challenges we have is, what is the desired level of granularity? How many parts should I even generate? And I think autoregressive transformers can be very helpful here, in a sense that they can just say, okay, this is the end token, you absolutely have to stop generating. And of course, there are a couple of limitations also in this work, which is related to the fact that we assume a lot of supervision in terms of 3D supervision, as well as part level annotations. So I think partner and pasta are very good first steps towards compositionality and how structural representations can enable a lot of cool editing capabilities. However, they are lacking in terms of appearance. So in this work, what we wanted to do is we said, okay, you know what, we really need to try to be able to generate photorealistic 3D assets. So the idea here is that we can leverage the capabilities of diffusion models to do all sorts of things, such as like diversified 3D generation, go from single image to 3D, try to do text-guided 3D generation, as well as 3D interpolation. So the input to this model is a text prompt and a single image. And we proposed CAD, which is this pipeline that enables generating 3D objects conditioned both on text and image. And our idea here, unlike Prolific Dreamer and all sorts of like SDS based approaches, is that instead of like trying to we were also trying to optimize a single nerf through a score function, but the idea is to train a nerf generator that directly models the conditional distribution of a pre-trained diffusion model through adversarial distillation. And if you look at the results, I think the quality in compared to Dream Fusion 0, 1, 2, 3 is much higher. For example, I really like these burger result where you can actually see how good the quality of the model is. And here I want to show you a couple of examples where we do 3D object generation of shoes. In the case of this example where we have like a green chair, and this image you can see here, the model is able to generate diverse objects that are physically plausible, and we can also do similar things for objects with thin structures. I really like the drum example as well as the plant that actually show that this idea of adversarial distillation can be very, very useful for all sorts of applications. Okay, so I think CAD it was another important step towards generating high quality and photorealistic 3D objects, but it also suffers from this issue that when it comes to control, control cannot be intuitive. So it is not that easy to actually interact and say, for example, I want to take Plato's head and make it bigger, or I want to chair this armrest and make it bigger. However, we had to sacrifice this aspect to be able to achieve high fidelity and photorealism. I don't think this is necessary moving forward. I think we should totally be able to combine both and unlock even cooler capabilities. So far, we only talked about objects, but we live in a 3D world where we have 3D scenes with multiple objects, and we want to be able to understand and recreate these worlds. For example, in this beautiful living room from Neural Architect, just by showing to you, you can easily identify that this is a living room. And how can you do this? Because you see, this is a chair, there is another chair, there is a table, there are two cabinets, there is this thing that kind of looks like a fireplace that was covered by these rocks or whatever. So another thing that you see that also us as humans, we perceive the world by identifying individual components that make this scene a living room as opposed to a kitchen. So in the next um, image that I wanted to show you, you can see that, it might be different. Like this living room is very different from this one and extremely yellow and bright. However, some core components are the same. For example, again, we have chairs, we have tables, and I think this concept of understanding the key elements in a scene is what helps us a lot. And it should also be like an important aspect when it comes to generative models. So in this work, I want to show you a pipeline that we built a couple of years ago for scene synthesis. Technically, starting from an empty room, we were able to compose, populate rooms in a meaningful way. We were also able to do to complete a room from a partial scene, as well as do cool things such as do object suggestions, and also like fix scenes that don't look as plausible as they should. In the input to this model, ATIS is a collection of scenes, and each scene comprises of an unordered set of objects and its floor layout. And the floor layout is parameterized as a top-down orthographic projection of its floor, and we represent objects in a scene as labeled 3D bounded boxes, and we model them with 4 random variables that describe their category. What is it? Is it a chair? Is it a table? Is it a bed? Is it a wardrobe? Its size, orientation, and location. And during generation, the object attributes are predicted in an autoregressive manner. And I think autoregressively predicting these properties makes a lot of sense because, you want to be able to know what is the type of the object that you will be adding in a scene before reasoning about its size and location. And in our setup, we first predict like the object category, followed by location, orientation, and size. And we compute the likelihood of generating a scene as an unordered set of objects. And to do that, we need to accumulate the likelihoods of generating each object with any possible ordering. Therefore, we propose to maximize the likelihood of generating a scene with all possible orderings. Namely, we want to be able to generate scenes with any sorts of orderings. It doesn't matter whether the transformer first predicts the bed, then the wardrobe, then the chair, then the table. And To do that, we maximize the likelihood of generating a scene with all possible orderings by replacing this summation here with the product over all possible permutation of objects. So the input to our model is a set of 3D labeled bounding boxes and the top-down orthographic projection of the floor plan, as I told you. And our pipeline consists of like 4 key components. The first one is the layout that simply extracts some features based on the input layout. Then we also have the structure network that maps the attributes of the current object into per object context embedding. Subsequently, we use a transformer encoder that takes the context embeddings and the floor shape feature representation, as well as a learnable object query vector, and predicts the output features that are used for generating the next object in the scene. And using the object query features, we can then autoregressively predict its object attributes using the attribute extractor. Once a new object is generated, it is appended to the objects already in the scene and is used in the next step of the generation process. So this is continued until we have the end symbol predicted. So let's have a look at how well does it work. We evaluate the performance both qualitatively and quantitatively. Here I'm going to show you only qualitative results. You can see that even this even though we try to generate different scenes, living rooms, bedrooms, dining rooms, the model can consistently generate valid objects that contain diverse object arrangements with multiple objects. And then what we do is, as a kind of like mentioned in the beginning, we want to see whether the model can do even cooler things, such as, for example, suggest objects. You know, I don't have any background when it comes to interior design, and I would love to have a model that could tell me, you know what, with your couch, I recommend you buying this coffee table. So this is kind of what inspired this experiment, where a user specifies a region of acceptable positions to place an object. You can see this marked as a red box. And then our model suggests suitable objects to be placed at this location. To perform this task, we have to do something very simple, which is compute the likelihood of an object conditioned on the rest of the scene. And we observe that the suggestions are always meaningful, and we can place objects that don't overlap with other objects in the scene, and they are still valid. The final scene is still a valid object arrangement. Lastly, another exciting use case of this interactive tool for scene synthesis was to correct unnatural object arrangements in a room. So, for example, you see here we artificially generated the scenes and we asked the model to fix this scene. We have cases such as overlapping objects, objects outside the room boundaries, objects in the unnatural positions. And what happens here is that ATIS identifies successfully these problematic objects. So we don't give as input the problematic object, ATIS does it on its own. And not only that, it also rearranges it. How does it happen? What happens here is we identify the problematic objects in the scene by computing the likelihood of each object conditioned on the other objects in the scene. And then the location and orientation of this object, it is sampled again and again and again until it looks plausible. So I think ATIS was one of the very cool works because it introduces this concept of unordered set formulation for the case of scene synthesis. And it's very fast, it's very simple, easy to train, has fewer parameters compared to more complicated pipelines. However, ATIS parameterizes the scene as a collection of bounding boxes that are not actual objects. So it would be nice if we could achieve this kind of thing without having to rely on object annotations. And we kind of achieved this goal in the next work that I'm going to talk about, where here the motivation was to generate models of 3D scenes without requiring any 3D bounding box annotations. So what was the input to our model was this semantic 2D layouts. And starting from a 2D semantic map that looks like this, we were able to generate 3D scenes and corresponding depth maps from different views. And in this case, because we don't have conditioning on bounding boxes, we can actually generate diverse 3D layouts, which I think is very nice. How does this model work? So the input to this model is a semantic floor plan, projection of the scene, and a noise vector. And our idea was to use a style gun backbone to generate a 2D feature field, which is queried using trilinear interpolation, and then it is decoded into color and density using a very small MLP. And what we do, which is a very standard trick, we use a super resolution model to upsample volume rendered images to target resolution, and we train this whole thing using a style gun discriminator. Let me show you how this model actually works. We're given a collection of single view 2D RGB images and a set of top-down semantic layouts. The semantic layout, I don't know if it was obvious from the previous slides, but let me clarify this, contains information about the scene structure, the object labels, their size, location, etc. And then we have a neural field generator that takes as input these 2D layout and a randomly sampled Latin code and generates a 3D neural feature field. And then we use standard neural rendering that, given the feature and the camera viewpoint, it maps 3D points to density and color values and renders a low resolution image from this viewpoint. Then, using the upsampling module, we take a low resolution to the image and generate its higher resolution counterpart. And in the end, we train the whole thing using a discriminator that takes real and fake images and predicts their labels. It also predicts a semantic segmentation from a subset of generated features that is also used as an additional loss to encourage consistency. So I've already showed you a bit how well this works. The quality is nice. Here you can also see where the camera are placed. So you can actually see that for this work, we actually have control also of where is the camera position so that you can have camera control. You can also do some things related to editing, such as change the object of, move the object to the left or the right. And the reason why we can do this is because we can perform the editing by changing the conditioning. So again, the 3D representations is entangled, but here we can achieve more fine-grained control by changing the input conditioning. Here are some other examples. In this case, we try to do removal. Again, we have to modify the conditional signal to be able to get these edits. And to sum up, I think this showed that actually we can generate scenes trained only on 2D images, and our model exhibits control also when it comes to more fine-grained objects as well as 2D semantic maps. Did we solve it? Is it done? Absolutely not. So the editing capabilities of this model are kind of limited when it comes to outdoor scenes. So in the paper, we have some results on Kitty, where you can see that the CC3D still struggles a bit to achieve that. And as I mentioned before, because everything is entangled into a single representation, we can do editing stuff only by changing the input to the layout. Okay, that was great. We showed some works, but I just want to motivate a bit the importance of thinking big and trying to do cool things. So I did my internship at NVIDIA in 2019, and our motivation and goal for ATIS was Promethean AI, which was a startup back then that was able to generate these type of scenes using programs. And I want to highlight that even now, even today, we cannot get these scenes with any of the narrative models that we have. And the reason why I think we cannot get this is because, yes, of course, if you use Sora, Cosmos, One, you can probably generate videos that look like this, like beautiful pixels, but I don't think it's possible to actually interact. Let's say select this a box and move it on the table or clean it. And if we go to more exciting scenarios where we have like scenes that look like a jungle, I don't think there are any generative models that can actually produce these scenes and enable users to interact with them. Like for example, change the shape of the leaves or make these trees bigger or make them look a bit more gloomier by reducing the amount of light that enters the forest. So I think that this technically highlights the importance of, thinking big. And I think this is, at least to me, still an encouragement against all these people that says, 3D computer vision is solved, graphics is solved. In my humble opinion, absolutely nothing is solved. And there is a big difference when it comes, to publishing a paper and actually making something really work for everything. Okay, so we don't live in static worlds. We live in scenes where we have interactions, and ideally, we want to be able to create digital twins where we have a scene, we can relive our memories, our experience in our VR headset, and kind of that was the motivation of this work that we did with Boscia at Stanford, where technically what you want to be able to do is just from 2D images, you want to be able to do more complex tasks such as localization, collision avoidance, and stuff like that. And I don't want to go into the details of this model, but what I want to show you is, for example, we are able to do collision avoidance, not hit walls, interact with objects in the scene without having to actually have supervision in terms of this is where the table is, this is where the door is, which I think is kind of cool. Okay, moving to my some of the works that I most recently did, I'm very proud to be part of this amazing effort at NVIDIA, which is Cosmos. Cosmos is NVIDIA's video foundation model, or world model as we like to call it, for physical AI. The code is open source and you can already use it. So personally, I was involved in the data curation pipeline and did a lot of work when it came to data cleaning and stuff like that. And here you can see different examples, different videos that were generated by Cosmos. And the reason why I think this is actually very nice is because we can the hope is that we will be able to have more tailored generative models for AV, robotics applications, and all sorts of physical agents. Okay, so to slowly wrap up, because I think I'm going over time, I want to reiterate who needs compositional 3D models. In my opinion, I think everybody does, because they will unlock a lot of capabilities. For example, when it comes to construction and architecture, structure scene representations enable easier simulation and interactive design. When it comes to film and VFX industry, modular assets allow for rapid prototyping and controllable editing in 3D scenes. Robotics and embodied AI, of course, having object-centric world models will allow easier manipulation and planning. The same applies also for autonomous driving. Game development is very similar, because we really want to be able to interact with individual assets when editing 3D environments. And of course, augmented virtual reality, it goes without questions that we really need to be able to have real-time scene interaction where the user can actually interact in a real-time way with a scene, with objects in a scene. And of course, physics and scientific simulation is another field where I think compositionality is very crucial, because it would allow us to make more controlled and interpretable simulations. And with that, I would like to thank everybody for your attention. Hopefully I didn't go too much over time. I'm happy to take any questions you guys might have. Oh, I cannot hear you.
Okay, so now we are going to move on to the next challenge. So I'm going to introduce it briefly, but please, challenge winners, be ready. Sorry, just one moment. This is the wrong deck. Okie dokie. Where is the, here it is. Wonderful. Okay, so for the S2 3DR challenge, our goal is we invite participants to produce semantically meaningful measurements or a representation from which we can easily read off the measurements that we care about from ground level imagery. And this imagery is captured by regular people on cell phones. So it has some, it's not as nice as if one of you were to do the capture. And we think this is an important part of the challenge that makes it realistic and applicable to, real world use cases. So last year's data set consisted of 5,000 scenes from single family homes mostly, with 15,000 images across all the scenes. For each camera viewpoint, we provided an 80/20K segmentation, an internal model from our sponsor Hover called Gestalt, which is this second row of images here, as well as monocular depth from Metric 3D, plus semi-dense SFM point clouds with the camera poses. And we invite the participants to produce sparse structured wireframe models of these houses. This year, we have substantially increased the size of the data set up to 25,000 scenes with 150,000 frames, so 10 times more total images. And we've upgraded from Metric 3D V1 to Metric 3D V2, which gives much more detailed and precise metric depth maps. So there's a couple challenges here. I think the speaker from the Building 3D challenge also highlighted the noisiness. We view this actually as a feature of the challenge. Plus, we have this mono depth that isn't necessarily well aligned to the point cloud. And we have no color images, and this is due to privacy reasons. And there's this geometric problem where often the people capturing are too close to the house and it's too big to be able to get very good views of the roof. So this requires either operating from priors or doing something else to be able to reconstruct the roof from sparse observations. Last year, we used this wireframe edit distance metric. We discovered some issues with this metric. We published a tech report going into the details there. I won't spend too much time going into it, but basically we showed the competition solutions plus a bunch of synthetically generated solutions to the same 3D modelers who generated the ground truth and asked them to judge the relative quality of the solutions in a pairwise interface as shown in the bottom right here. And then, did a bunch of stuff. You can check our tech report to match automated metrics to those expert preferences. And we ended up concluding that this combination harmonic mean of corner F1 score and edge Jacquard score was the best correlated to these human expert preferences. We call this the hybrid structure score, and we use that for this year's competition. Once again, we thank our sponsor for providing the $25,000 prize fund. These are the dates, and without any further ado, here are the challenge winners, and we're going to go to Jan's talk first, and then the other ones to hear about what they did. But just before we do that, I would like all of you to keep this question in your mind. We're going to come back to it later, which is what else could we do with this challenge to spur more of you to compete and to compete earlier? So please give this some thought. And with that, we'll go to Jan. Jan, are you here? Excellent.
So hello everyone, my name is Jan Šperna. Here is my supervisor Lukáš Neumann, and I'm going to present the winning solution of the challenge this year. So before we, you're very tall. How do I change the yeah. So before we start, I would like to, we started with the looking through the data set, and we found several problems. So the first one, that is probably the biggest challenge, is that because of the images are taken by normal human people, they are not captured optimally, and the call map sometimes fail to reconstruct the whole point cloud of the house. And if you don't have the point cloud, it becomes quite hard to estimate the wireframe because the metric accepts or wants you to predict even the unseen part of the house. The second challenge is that the camera intrinsics and the parameters are just estimated from the call map. So as you can see in those images, when you take the ground truth vertices and you project them as the black crosses, you can see they don't actually align that much with the Gestalt segmentation, which is provided in the dataset. So that means that just taking the 2D masks and reprojecting them into 3D doesn't work that well because, again, we are going to be penalized by the metric. And third one, which I find kind of funny, is how the people actually did the ground truth, because in those examples, for example, my favorite is the left bottom one. You can see like 12 points, which depicts the chimney. So it's kind of impossible to predict the chimney. And it has 12 points for unknown reason. But usually for single frame, you have, for example, 40, 50 vertices. And if those 12 you don't predict, you're basically losing 25% of the whole score for that house. I will also describe the baseline method because our method is kind of based on that. So you iterate over all the images. You start with the Gestalt segmentation. You identify 2D clusters of the classes that can be the vertices. Then you take the center of them. You get the 2D point of each vertice. Then you connect again based on the Gestalt segmentation with the edges, you predict the edges based on the Gestalt segmentation, and then you lift the vertices and edges into 3D. And then you do some post-processing. The problem what we see is that you are doing most of the work in the 2D, and you are representing the vertices as a single 2D point. And then if you want to lift them into 3D, you are losing a lot of information. So instead of that, we want to try, or what we did is we want to do most of the work in the 3D directly, and use some deep learning because it works and it's kind of fun. So we start with the vertex candidate generation. So we iterate again as the baseline solution. We find the 2D clusters same as they do, but instead we don't use a single point, but we use the whole masks to classify or create 3D clusters from the call map. So we take the 3D call map point clouds, we basically project them into the image, and then based on the masks from the Gestalt, we segment them and we create some kind of clusters in 3D. We don't do edge prediction at this stage at all. And then because we can generate like a lot of candidates for all views, we somehow need to merge them. So we merge them by that if the clusters share at least 50% of the same point, then we think it's the same vertex. And this works quite well, but the problem is that it's quite noisy. So Then we use which we call something like extended point net that we use to classify and regress the vertices. For that, we extract the patches. So we choose 4x4x4 meter cube around the cluster. We extract all the points and we create 11 dimensions representation, which serves as an input to the extended point net. Then I show the model. So it takes the 11 dimensions as the input, and it has 3 tasks to do. First is to classify if the cluster is actually a vertex or not, because there are many outliers and we want to filter those out. The second one is because now we think, or like what we estimate the vertex as the mean of the cluster points, we want the network to predict the offset to the center of the cluster as to directly regress the vertices, and also error score, which is nice, but we don't actually use that. And because as mentioned, the data set is quite large, and each frame, or like in each instance has, for example, like 40 vertices, then you can generate like a really big data set of like 600,000 patches. Once we have generated all the vertex candidates and we have classified them with our point net, we do something similar to find if any of those points are connected with the edge. We do something similar. We take all pairs of the vertex candidates. We create patches, but not the cubes now, but we create cylinders in 3D again. And we again feed it to the point net, which now serves only as a classification model. So for each pair of 2 vertices, we want to know if there is an edge between them or not. This point net is a little bit smaller because it has to be run because if you have, for example, 40 vertices candidates, then it's 40 times 40. You need to run this model because you do it for all the pairs. And the solution, the conclusion is that it works quite well. So I have the evaluation on the validation set. What you can see that if you take the baseline method, it performs kind of poorly. Then if you tune the hyperparameters, you get a significant improvement. And then what we used is our method, which doesn't use the deep learning at all. So we take all the clusters as the clusters and the edges from the baseline method. It works at this moment it works works better than the baseline. And then if we add the vertex classification model, we gain some performance. And then if we use the edge classification model, again, we gain some performance. And this is how we won the competition. I have 2 ablations. Time is good. So this is the ablation on the threshold for the vertex classification model. I don't think there's much important thing to see, but I think this is much more interesting. So what we saw in the last slide is that the vertex classification model is not that much. It doesn't depend that much on the parameter, but the edge classification model does a lot. So you can see that to find a sweet spot, you have to iterate over many hyperparameters to get the perfect performance. And I show a few qualitative analysis examples here. The blue dots are the vertices, the ground truth vertices. The green are the ground truth edges, and red is our proposed solution. It looks quite noisy, but this solution is the best for the metric. So that's our conclusion. And thank you for the attention. If you want to look on my personal website, there is the QR code. There's also the public repository on Hugging Face that you can run at your computer. And the third, if you are looking for a PhD or postdoc position in Prague, you can contact my supervisor if looking for some good people. Thank you.
Does anyone want to do one question before we go to the next one? Going once, going twice? Okay, thank you. All right, Antonio, are you here? Online on the Zoom? Where are you? Okay, we need to unmute Antonio.
Hello, hello.
Try again.
Hello, hello. Can you hear me?
We can hear you.
Excellent.
So you can go ahead and share screen, or I can operate the slides for you.
Okay, I can share the screen. That will be probably easier. Can you see it?
Yep, that's great.
Awesome. Okay, hello everyone. I'm Antonio from Zagreb. I'm part-time PhD student at University of Zagreb. First of all, thanks for everyone for organizing this challenge. I congratulate all the competitors, and right now I will present my second place solution. So I actually joined pretty late to the party, just a couple of days before the deadline, and then figured out that I will not have time to do proper learning, to try proper learning methods. So I decided to go for exploring and pushing the limits of handcrafted solution to see what can be achieved just by optimizing handcrafted solution. My key enhancements are hyperparameter tuning, multi-view consistency filtering, expanded vertex and edge classes, and improved handling of various input sizes. And this gave me 39% of hybrid structure score on private test set. This is the original baseline. It's already described by Jan. So in short, for each view, you detect vertices and detect lines by using the connected components algorithm. And then you lift them to 3D by utilizing the depth information, both dense and sparse depth. And then after all those views are processed, you need to obviously merge those 3D vertices. Merging is based on proximity and the type. And then afterwards, you clean the wireframe by removing unconnected and distant vertices. So first thing I tried obviously was tuning hyperparameters. There are a couple of them. First, two hyperparameters are related to mostly, they are related to 2D information. On the left table, hyperparameters is edge threshold, which means the pixel distance to the edges, which is actually if points are within the edge threshold to the estimated line of the edge, they are considered connected. The default value was 10. The optimal value turned out to be 25, and this gave quite a boost. Second, hyperparameter search radius, which is actually the pixel radius around the vertex in which to look for sparse depth values. Both those thresholds are in pixel values. The default value 10 and 25 gave the best results. Next set of hyperparameters now related to 3D information. First one on the left side is threshold in the merging method, which determines the 3D distance for merging vertices. If they are within this threshold, they are merged. Optimal value turned out to be 0.3. This is in meters. Then the next threshold, also in meters, which actually filters vertices based on the distance to the closest sparse point cloud. So if this closest sparse point from the sparse point cloud is further than this, then this vertex is rejected. Optimal value turned out to be half meter. I turned other hyperparameters, but in my case, they didn't help. Next stuff. So far, I only was tuning hyperparameters. Next stuff, I was now trying with some newer methods. And this is a thing which actually didn't work out.
I was trying to do the next thing. While processing each view, instead of executing connected components algorithm, I was projecting 3D points to the image and then trying to cluster them with dbScan based on Gestalt segmentation for vertex classes. But this didn't help, as I said. Was it a bug in code, or is it just impossible by design? Didn't have time to investigate that much. Next thing was figuring out that the original baseline only uses two classes for vertices, apex and eve endpoint, while in the Gestalt segmentation, you also have additional vertex class, which is flashing endpoint. Same things goes for the edges. Edges only used four classes, eve, ridge, rake, and valley, while there are additional four edge classes. When I turned that in, it also gave a bump of 1 percentage point. Next thing, which is kind of similar to the 3D projection in view, is this. So when you are done with all the views and you try to merge them, before merging, you actually reproject 3D vertices into overlapping views of scene. You need to pre-calculate which views of the scene are overlapping, and then you keep only the vertices which have consistent semantic class in a minimum number of views. That method has multiple hyperparameters. Most important one was projection patch size, which determines the area around the projected point, the size of the area of the projected point. Instead of using the projection patch size 1, which basically means looking at only at the place where you projected, you look at the neighborhood, obviously. Optimal value was 30. This gives quite a boost, I would say. And what's also important here is that I needed to execute the edge calculation again, because after some vertices were rejected, the edges, some edges were missing, so I needed to recalculate them. And when I submitted this for some small amount of time, this solution was first on the leaderboard, but then Jan submitted obviously something better. And just as when I was about to give up, I saw some other competitors approaching close, and then figured out that the original baseline has a problem with images which are not of the same size. So what happens, for one scene, you could have obviously images with different sizes. Those scenes would get rejected, and the wireframe produced would be empty one. This obviously degrades the hybrid structure score. By enabling variable input sizes, you will also get quite a bump on the performance. You can check the report and the code for the details. It's pretty simple modification, I would say. So to sum up, these are all the improvements which I achieved by parameter tuning, expanding classes, multi-view filtering, and enabling different input sizes. This gave me 39% on private test set score. Good thing about this method is CPU only. On the image below, on the left side, you see the output of original baseline, and on the right side, you see the output of optimized baseline. You see that the wrong edges and vertices are rejected on the left side, and on the right side, you see two new added edges and newly detected vertices. Something about failures. This obviously will not work when edges are not visible. In this case, on the right side, you have clearly missing edge. That's because in the input images of Gestalt segmentation, this edge is totally not visible. And another problem is if some vertices are too close in segmentation, their segmentation mask would connect, and the connected components would produce, for example, one vertex instead of maybe multiple one. This is highly sensitive to the perspective of the camera. And obviously, what's to do is to try to apply learning approach. I have some ideas, and hopefully I will be able to try it and share it soon. That's everything from me. Thank you for listening.
All right, thank you very much. And we're going to move right along to Yulia. So let me, yes, I will. Okay, can you go ahead and unmute and share your screen? Wonderful. Okay, take it away.
Okay, great. Yes. Hi, everyone. I'm Yulia Mulyasha from Ukrainian Catholic University. Today, I will detail my solution for a structured semantic 3D reconstruction challenge, which secured third place. First, I will quickly recap the motivation and the problem. The motivation for this work addresses a key limitation in 3D reconstruction. While point clouds are accurate, they lack explicit structure. This challenge targets this problem directly to take post images and reconstruct a measurable semantic 3D wireframe. Our approach builds upon a crafted baseline, kindly provided by the organizers. It is completely handcrafted with no learning-based solution. The baseline first processes each image individually. It finds 2D vertex and edge proposals in the semantic maps, and then lifts those proposals into 3D using provided depth information. After processing all images, it aggregates the results, it merges 3D vertices that are close to each other, and then prunes the vertices that are disconnected or considered outliers. But this pipeline has several limitations that we tried to overcome with our proposed enhancements. Let's move to them. Let's first overview expand the semantic feature detection. The first stage of our pipeline focuses on generating a comprehensive set of initial proposals. The goal here is to simply maximize recall, ensuring that no correct edges are missed before they can be evaluated by our 3D filter. We achieve this by expanding the semantic vocabulary and by relaxing the 2D edge association threshold. The next is geometric edge validation. This approach provided the most prominent improvements to the baseline. It acts as a 3D filter. When exploring the results of the baseline, we spotted the appearance of so-called phantom edges that appear valid in 2D projection, but are geometrically implausible in 3D. The principle of this approach is that any legitimate wireframe edge must be physically supported by the scene geometry, for which we use the colmap point cloud as a proxy. We sample points across each candidate edge and check their proximity to the cloud, which edges without sufficient support are pruned. And the next is robust merging and 3D refinement tuning. We also replace baseline's grouping logic with a standard disjoint set union algorithm. This is a more principled approach that correctly handles transitive merging, ensuring that if a vertex from one hue is close to the second and the second is close to the third, all these are grouped together. This prevents both duplicate vertices and incorrect splits in the final model. And also to enforce precision in the 3D refinement stage, we tightened the vertex merge radius and reduced the final outlier pruning distance. The stricter 3D thresholds produce a clean and precise final wireframe. Our method achieved a mean hybrid structure score of 0.38, which is a 45% relative improvement over the baseline. The results show relatively good gains in both vertex and edge prediction accuracy. For the qualitative results, the baseline shown in the left has a geometrically inaccurate edge. Our method shown on the right removes this error. This is direct result of our geometric validation model. And overall, the final wireframe has higher geometric accuracy and structural coherence. Thank you for your attention. I would like to extend a big thanks to the organizers for this excellent competition and their hard work, and kudos to other teams as well for their excellent work and insightful presentations. Thank you.
All right, thank you. And any questions for Yulia? All right, so now I hope you all thought about the question I asked you in the 2 minutes we have remaining. Any requests, anything that we could do better on this challenge to get more participation and earlier participation? Please. Sure. Yes, let's include the virtual people.
I feel if you would put like larger description of the data set,
Mhm.
how the data come into, like, how was it created? What is the purpose?
Mhm.
To give it like
Little more
more
detailed
like
write
a
up.
meaning and like what is the purpose of this task?
Okay.
So it's like we have some data and we have some output, but you have to kind of think about why it was prepared. And I think the talk you gave in the beginning was super nice. And maybe if you would just like
Write this down
and
and
just put it there on the website, it would make a little bit difference.
okay, at least this is easy, so we can do this. Okay, nice suggestion. Any others, and then we'll all go to lunch? Please. You don't need to raise your hand, just come right up.
I think it's a script competition, right? We need to upload a script.
Correct.
Yeah, actually compared to USM3D, I think it's more easier to upload results.
It's definitely easier.
Because you
Yeah.
know that well, Python is the only tool that can listen. There are other programming languages or solutions. Maybe we need combination of other solutions to generate final results.
Well, not only Python, you can call other things from Python. You just have to make your
It might make work a bit
little
harder.
difficult.
It's a result target.
Yes.
It might be easier.
Yeah, I think this makes a lot of sense. The challenge we have, and I wonder if you have a thought about this, is because the prize money is kind of big, if we don't make it a script challenge, we're a little bit worried about cheating. So,
Maybe
yeah.
more people gravitate to the solution.
Yeah. Well, but cheating is in like manually labeling the test set and then fine tuning on this. Yeah, okay. Yeah. We can discuss this more. I think this is a valid concern, and making people's, like, certainly a lot of people struggle with this script competition, and if we could reduce the friction, this would definitely be good. Okay, cool. Okay, one more. Yes, please.
On this contrary, I go with it, like, given that this is a script competition, you have limited resources. And you're putting like a lot, which like a lot of GPUs, and like none of the students that might be competing from like graduate student, they have the GPUs, right?
Yeah, this is a good point.
Kind of fair. And I have another one. If you would provide like a better explanation of the handcuff solution, or just don't put it there, because it's like, I maybe think that before you want to start with a competition, you spend like 1 or 2 days just, like examining data set and what is the handcrafted solution. And if you're too lazy to do this, you're not going to start. But once you start, once you get yourself going pretty fast with the pipeline and submit something, then I think you'll get caught up and you will continue that.
Yeah, makes sense. Yeah. So again, starting friction. Okay. Well, thank all of you. Really appreciate you here, and I hope we see you after lunch.
Us all day on Zoom. Thanks on Zoom, on X, on every platform. He is the other organizer that is not here, but he is with us. Anyway, welcome to the afternoon session of USM3D. We are starting with a super duper keynote. Professor Daniel Aliaga is associate professor of Purdue University. And his work in his research interests encompass urban modeling, reconstruction, and procedural and parametric modeling techniques. He's a pioneer in inverse procedural modeling for urban spaces, aiming to facilitate semi-automatic and controllable content creation and editing of large-scale geometric models. And today we will hear about the generative US scale urban green and gray modeling. Stage is yours. Thank you.
Thank you, Ilke. So as Ilke mentioned, I've been doing urban modeling for a while. In fact, I started around 2007 and been doing a variety of forms of urban modeling, procedural modeling, and of course, generative AI is a current buzzword. So we've been doing some of that also. So this is work that's really a mixture of people and collaborators. And I'm going to focus only on the last few years of work, but there's a bunch of stuff behind this which won't be so obvious because we only have so much time. So very quickly, talk about a city. Maybe given this context, we know what a city is, but more or less a city is a complex system. There's countless individual and collective human and social decisions, which is kind of why the city becomes what it is. It's not a random process. There's actually logic behind it. And this is important as a founding motivation of many things that we do. And here's just a few fun cities. So here are some things that we wish we can do and we wish we could do. So these are some pictures of current and prior results to give some motivation, but we work with people in these areas actively, and I have recent publications also, but they're the ones other people lead these. I won't really talk about this in any detail, but we try to enable different forms of meteorological modeling and simulation of urban spaces. We look at air quality modeling within urban spaces, and they have information they need to know about the urban environment. So we also try to provide that information. We look at the vegetation, climate, or the vegetation weather feedback. Again, there's other type of information needed about the cities, and also urban heat island mitigation, and then various types of disasters. By disasters, we mean things like flooding, extreme weather, heavy rainfall, and things like that. We also deal with people who address these issues. Now, to enable these things, which we have and wish to do, a significant challenge is missing data, particularly that 80% of the people living in cities are not actually living in the big cities. So I'm sure you've heard of Paris, New York, Beijing, right? And everybody studies the big city, lots of data, but most of the cities in the world are not metropolises. So therefore, they're not actively studied. So how can we do that? And that's why I say that perhaps 80% of the people living in cities are not in these big ones. And the issue is that these large cities are data rich, but the other ones are not. So what can we do? And what do I mean by missing data? So on the left, we have Planet Labs. I don't know how I'm familiar with remote sensing. Planet Labs scans the whole world every day at 3-meter resolution. So that's great, all cities, but there's only a certain amount of information. You can see there the level of detail. Worldview is or now called Maxar, is another satellite, also acquires information kind of daily. It's much more difficult to get to. And even it has limitations. There is, of course, aerial data, which is great, but that's not everywhere. And you might argue it's, of course, Google Maps works, Google Earth works, but then how often do you want the data to be captured, right? So then do you want daily, weekly, monthly? What's your update rate? So again, maybe it's not the data you need. Then there is crowdsourced information. OpenStreetMap is one of those, right? So this is wonderful, but if it's not crowdsourced, it's not there. So that also has missing information. And then there is survey data, which is a very old way of obtaining information, and it's great, but it's only sampling, only done sometimes. So this is what I mean about what's around and what's missing. So I'm going to divide my kind of presentation into 3 parts: trees, layouts, and a little bit of future work. So let me first talk about trees. So this is a project we've been doing for a few years together with different entities at Purdue University. And so far, we've done a system, kind of a live system to acquire tree locations around the world. So we've done about 300 US cities and captured that number of trees and over that many acres of urban space, individual tree locations, and more information as we continue expanding upon this project. And to give you some context, this is kind of the question, where are the trees, right? So raise your hand if you can tell me how many trees there are, right? It's not easy, right? So we figure out that here's where they are because we use, 12 months of data, 12 samples, so 12 one-month days to figure out where the trees are and see a pattern and so forth. So to give you some explanation, we use time and motion. So time means that trees change over a year. So here you see over 12 months for some city, maybe for 4 different cities, how the NDVI is a very simple metric in satellite images which somehow relates to vegetation. And you can see how these curves go up and down. So in some sense, that determines as a pattern. And therefore, when you go back here, we can actually find out that over 12 months, there's a cycle of information happening here in each one of these different pixels, and it can tell us where trees very likely are. Another thing we exploit is motion. So if we look at trees like here, and we move over trees, right? 1, trees move, 2, there's an occlusion change. This also tells information about where tree boundaries exist. So these are 2 things we've exploited in 2 different ways of doing the problem. The top one we use for national scale, the bottom one we use for forests. So I just mentioned this one. And so, so the greenness varies over time. Another thing in cities that is the case is that city vegetation follows systematic rules. We call these procedural rules. Now, you might not know exactly what the rules are, but there is a set of rules. So in a city, you put trees next to the roads in a backyard and parks, and they are in straight lines, and there's a few number of trees in a backyard, and in certain areas in a dense downtown, there'll be little parks, right? So that there are trees in urban environments are not there because of Mother Nature decided, I'm going to put a tree there, right? Rather because humans put the trees there. It's different than in a forest. In a forest, Mother Nature competition for resources dictates how trees develop, and that's fine, and there's a logic to that, but that's different than in a city. So we know in a city there are management rules. We don't know exactly what they are, but that's what we try and discover. Some background. One of the traditional ways in which trees are found in cities is through surveys. So like Chicago, which we work closely with, they did a survey to determine how many trees are there in the city of Chicago. And I'm not trying to criticize, I'm trying to say this is what they do. So what do? They sample 260 lots or plots of land, and then they extrapolate using the marvels of statistics. And that's great, right? But that gives them, of course, some approximate information. There's a tree census methodology. So this is something New York did, New York City. They had 2,000 plus volunteers using 30,000 human hours, go around and go 1, 2, 3, and write down with an app or whatever they had, right? And this works, right? It's expensive. This is also methodology. Yes, there are some satellite-based methodology other people do, but they're usually what's called coverage-oriented, meaning determining how much green is there versus non-green, and then you maybe do a density fill to estimate trees. But you don't get information like individual tree locations, species, and other parameters called DBH, like the trunk width and other things. So our approach here, so this is a traditional approach, right? Survey, extrapolation, right? Slow, expensive. So we use a different approach where we use a very small amount of labeling, and then we do a first step of something like segmentation, rather straightforward. And then we use some generative AI, in fact, a bunch of trained GANs to figure out what the rules are, and then use these rules to then plant trees, position the trees where they most likely are based on these 48 channels of data we get, right? 12 images, 4 channels, 48 channels. And that gives us information like position, canopy cover, density, where the trees are, what type of tree are, backyard, roadside, and so forth. So here's a pipeline. The input are these images. The first step is a segmentation step, UNet, pretty traditional, get green coverage. And then I'll talk about the second part, the tree location estimation. So here, this is kind of the input, and then the output are these trees. And the coloring means what type of tree it is, roadside, backyard, industrial, park, etc. And so roughly, we say there's about 20 types of procedural rule sets in different categories: universal, cluster, and city specific. So universal things that we say, like trees don't overlap, and what's the typical distance between trees when they are dense. So we have some guidance on this. And then based on whether it's roadside, backyard, park, etc., there's some set of rules. And then there sometimes are some city specific rules, which we might know, like, what happens, and particularly if the climate is different, like Phoenix planting is very different than Boston planting. So these is ingested into a GAN, and through a process of, training with some small amount of data, we kind of calibrate these rules, the parameters of these rules. We end up with, we have the universal rules, we train cluster-specific rules as well as city-specific rules. And this just tells us something about relative placement and density of trees. Then we have a calibration process where we actually calibrate it to the data that we have, and that gives us a more precise estimate. And then at the end, then the process is something like we use synthetic data to train this. So we place trees at these circles, and then using the universal rules and the cluster rules, we form types of trees, and then we synthetically place trees in here, right? And then this becomes a new input, and that becomes the output. So now, given these blobs of input that are contextualized by roads, buildings, and so forth, we can position where the trees are, and we do this in training for many number of trainings, and some amount of training data, and summarizing this very quickly. But in fact, this was about 100 GPUs or 1 month of computing to be able to do this for 300 cities and so forth. To find the right hyperparameter tuning, which I'm sure you know is very important, to be able to generate things at a precision of roughly 85 to 95% average position and count accuracy. I'll skip over that. So here is kind of a recap. So given these 12 months, 48 channels, we do a first segmentation that's trained. Then we cluster these here into regions, and then we use our GANs to take in these clustered areas and produce individual trees, and then we get that here. And as I mentioned, the accuracy is 85 to 95, and also how do we know that? So there's a few efforts to localize trees. One is called the Google Auto Arborist project. They did about 26 cities, and they use aerial plus ground view images, and then human verification to get a ground data set of about 20-something cities in the US, somewhere not in the US. And so we use that as one verification to get our numbers. Then for about 70-something other cities, we found partial truth information. So a couple of university data sets, a couple of city-gathered, plot-based, survey-based estimates. So using all this together is how we have roughly about 100 up to 300 cities. We have some guess of what the ground truth is, and we can report we're at like the 85-95% accuracy range. For the other 200 cities, you hope, right? Because there's no information. Yeah, so for instance, Chicago, which is, again, is near us, so it's very important. This is kind of what they're able to say of the canopy cover, and on the other hand, we can give them very precise information about where the trees are, which they can use for their tree planting efforts. So I'm not sure, I've become very familiar with tree planting, so I forget what you guys know or don't know, but greening is an important thing in cities these days, and people spend lots of money. And the simplistic answer people think is more trees equals more better, right? But that's not necessarily the case, that more trees equals more better, right? You have to vary on where the trees are. There's a cost associated with them, give you some idea. it costs about $500 to grow a tree a few years. So you say to like New York City went through a million tree planting campaign, 2017 to 2020 or so. 1 million times 500 is a big number, right? And they did spend lots of money planting that. So this is a big endeavor, right? So if half the trees die, this is not good, right? And the mortality of urban trees is much higher than in forests, because again, trees in urban environments are not natural, right? They're put there on purpose, so you have to plan where they go. So the trees have to be well planned. Second, what's the benefit? So the benefit, of course, is it looks nice, and I'll talk a little bit more about that in a moment. Other benefits are air quality. Other benefits are a variety of benefits, and these are called the ecosystem services. So there's money associated with having trees, putting trees. So this is why it's a very well-studied topic. A very exciting topic to study that people want it to be well-studied. So some cities in Chicago, Indianapolis. So as I mentioned, we did this at national scale so that we can get some very interesting statistics, and this is just a hodgepodge of a few things that we can estimate. Like we give you some errors, we give you number of residential trees, street trees, park trees, other trees, public trees, private trees. So people say, oh, you know, the city usually only knows about public trees because there aren't many private trees. Well, turns out, yes, there is less private trees than public trees, but it's not like the number of private trees is a lot less, right? It's roughly half-half or 60-40%. So private trees are really important. So so the city wants to know how many private trees do I have, because beforehand they have no idea, right? They only know about public trees. So this is some information. And then we can divide it up into densities and which cities have more trees, less trees, more park trees, residential trees, roadside trees, etc. Another angle of this, what I'm not showing you, is species. So also from this information, satellite information, we want to determine tree species. This is ongoing work. My team has a first publication out and working on more things. Determining species is hard. From ground level imagery, it's doable. Still not trivial, but doable. From way up there in the sky, it's even more difficult to determine tree species. But we're trying to carve away at that task. So more statistics. Some interesting things we could do correlation-wise is figure out things like how do trees correlate to different census data. So we look at the census data, the last census data, 20-something, whatever it was, 2020, I forget when it was. Then we looked at maybe correlation between income and trees. So you can see things like that medium income seems to correlate positively with trees. So more trees means you make more money. This is kind of not unexpected, right? But we can quantize it and tell you where it's true, where it's not true, and so forth. And other socioeconomical as well as weather-related phenomena, like whether there's more flooding, whether there's more heat, how does that affect the placement of trees? Again, we can do this at an almost fully national scale. We picked 330 cities because that's all cities with 100,000 people or more. But you know, we can pick others. We also can go back into history. So Planet Labs, which is our main data source for now, has imagery since 2010. So we're able to look at trees before and after disasters. So fires and tree planting efforts. The bottom here is the New York tree planting effort. Top one is a wildfire in California. So, you know, California has wildfires. So we can give information before and after different events, which is also important. And again, all this takes just, you know, an hour to compute. Right? We go to satellite, we press a button, we munge around the data automatically, boom, we get an answer. As I mentioned, forests are not left behind. So the other method we used, I figure out, and this is several papers that have been published at CVPR and other places you've heard of. So this one is a more recent work trying to do forest segmentation. So I talk a lot. How am I doing? Halfway through? Yeah, I got plenty more to go. Okay. So we did forest segmentation as well, and you know, and did a great job here. And our numbers are better than other numbers, so that must mean it's a good job. That's the way CVPR works, right? But anyway, so we've also worked with dense forests, and it seems to work well. And this is exciting work as well. But I'm going to just go over a little bit quickly. Now let me go to some layouts. So layouts is a word we've been using to determine kind of 2D or 2.5D urban configurations. So again, for these same 330 cities, we've also generated them synthetically. So what does this mean? It means that given only a small percentage of a city, 1 to 5%, we can generate the rest of the city. So this is kind of cool because if we don't have all the information, we can generate a pretty plausible answer. Now, again, for New York City, you know everything, you know, it's not that interesting. But for smaller cities in the outskirts of Nashville, there is not probably a large scientific corpus of studying, but yet we can generate variety of urban layout information, which I'm going to show you. But just to give you some examples, these are a few places in the US, mostly, I guess Vancouver is not, where you just give us a few percent and we generate everything, the rest is generated. And this is actually graph-based neural networks. So these are not pixel, these are actually discrete structures, buildings, houses, building footprints, roads, and so forth. So what does this hinge on? First, are cities really that different? So probably a group of people will say, yes, every city is different and unique and none of them are the same. And that is true. But also, there is a logic to them. They're not random structures, right? There's actually a reason why it happens. An example I'd like to explain is if you're in some city and a little old lady is crossing the road and crosses slowly because she cannot walk very fast, and the car stops, and then the next car stops, and then a block away, the other car cannot pass the intersection. Suddenly you have a traffic jam, right? And the traffic jam was not random. It was because something happened, and the resulting set of events was complex, but there's a reason to it. So that's an observation. Another observation is that while 3D is wonderful, and I've worked many years in 3D reconstruction, 2.5D is also plenty for a lot of things. Particularly these things here, which I mentioned at the very beginning, are interesting applications. So this is also various approaches put together, and basically as a graph-based neural network, recently become a great fan of graph-based neural networks. I think Peter Wonk at the beginning was using the term of regular and irregular meshes. So I'm thinking irregular meshes is really cool. And graphs will help support that. But this is just a thought. So using input, we're able to train a graph neural network. We've tried several of them and have a best set that seems to work, and then generate realistic building masses. So first we kind of categorize all buildings into 1 of 5 parameterized building footprint shapes, and they're roughly like the shape of an I, T, L, U, and X, but these are parameterized, so it's not like they're all exactly the same, but they just have parameters. And that covers about, and we assume city blocks have 4 by 30 building structures. And we've verified for the 300 cities, this is about true in 98% of the cases. We can cover buildings with very high accuracy, like 98% accuracy, by having these canonical building shapes and block sizes with 4 by 30, so 120 buildings at most per city block. So anyway, we train this hierarchical system going from buildings to city blocks to communities to cities. And this is a hierarchical graph network that's trained and set up and works, and it's wonderful. And here's another picture from block, the census tract to region to the whole city. And it can train quite well, and training with a whole bunch of GPUs. And then we do some comparisons to other methods, and it seems to capture quite well the structure. This means, therefore, that given less than 5% of the building data, we can generate the rest at very high accuracy. So like here, probably the bottom is, I think the bottom is ground truth, the top is synthetic. So it's generated, can you tell a difference? Probably not. And here's a close-up. So call it a layout foundation model, if you want to call it, right? Because it was and that's a popular word everybody uses, right? So we can call this the Urban Layout Foundation Model version 0.9. You can generate a city block at some city, just giving it a small context of information. And here's a bunch of cities you can do that. And so if you're not on this list, you can probably do it. And well, so why we can, since ultimately we have a latent space, right? Everything gets compressed down to a little 512 dimensional vector. We can do style interpolate from one city to another. So we can take New York City, we can take Norfolk, and we can, do the typical style GAN related, this is not style GAN, but related types of style interpolation, and go in between city styles if we want to do urban planning. So I'm not sure if you're familiar with urban planning, but urban planning people trying to find out configurations of cities that satisfy certain properties. We've also used this for weather forecasting. So I get into those applications. So to do a urban weather forecast, normally you have to set up a bunch of information beyond just the buildings. So we can ingest into the layout other features. It's just a feature vector for every single building. And then we can generate those values, even though we didn't have them for some cities. And then we can run your latest weather forecasting. One of them is called WRF, Weather Regional Forecasting System. This is the one that's probably used in the news when you see the weather forecast. I'm not going to argue the accuracy of weather forecasting, but people do this. And so we have some work where we actually compared our approach to the state-of-the-art, to ground truth, and using our completion, if you want, approach. We're just going from 5%, we generate the rest of the city, all the information we need for weather forecasting. We actually run the weather forecasting. We're equal or better than other methods, state-of-the-art. So that's happy. That makes us happy, and got papers out of that. Another thing is, this is interesting, is socioeconomical indicators. So some background here. What does this mean? So coincidentally, years ago, somebody named Ilke Demir had a paper where she threw out that if you were at a corner and you look around the four corners, you could find out where you are in the world. You remember that? Yeah, it was a small thing of some paper, and anyway, nothing much happened to that. So this is related to that, but here it is the case. If you look at a piece of a city, an urban layout, I can tell you socioeconomical features like income. I can tell you, is this a rich or poor neighborhood? And how can you do that? Well, a human can do that, right? If you go outside and look at a layout, you're like, this looks like a wealthy neighborhood, or this looks like a not wealthy neighborhood. You can do that, right? You use a variety of features. So in some sense, we having the neural network do that for us. And in fact, we took from the census about 150 different parameters, 150 different metrics. About half of them worked well. And here's the top reporting ones, tells us some correlation between the indicator and the urban layout. So just by looking at the layout, we can tell you things like income, life expectancy, diesel particulate matter exposure, things you see here. Not 100% accuracy, right? But 80s and 90s. That's pretty interesting, right? So that's another thing that we're able to do. We've looked at air quality. This is work for a collaborator, Yang Zhang, and she was using some of our outputs to do air quality simulation. And it seems to work well. And we're doing more things along this line, but I'm just giving you some glimpse. 8 minutes. Okay. And also we're doing this for archaeology. So cities of the past are still cities. And in fact, this year we have a paper here in CVPR that's doing some of this for archaeology. Ao Chen is sitting here. He'll be talking about that later this week. So also some of these ideas apply to archaeology. In this case is for LiDAR point completion, but same thing in the same spirit of urban modeling. Oh, this one here, yeah. So that's cool stuff. So we also have this relatively new project called U-Tree, which means Urban Tree Resilience and Environmental Effort. This is an NSF project. It's about $5 million. We're in year 0.75 of 5 years. So this is a tool online for most cities in the US. Again, the same 330 set will be the initial group. and it's not available totally to the public yet, but it will be soon. And it gives you information about trees and some gray information. So buildings to enable many of the things I showed you previously, but they'll be online. So it's a big project, lots of players, lots more information is coming, but this is, again, slowly online. Well, it is online, but it's not released yet, but it will be. And this ingests satellite information, does weather, will do air quality, will enable generative AI for green and gray modeling of cities and so forth. So this is how, if you want to know more about this, please see me afterwards. I can keep in the loop and give you more information as it becomes more publicly available. And then to conclude, so layouts are powerful mechanisms for planning, I think. So 2.5D things are quite useful. So I'm not saying 3D is not, and I still have papers in the 3D world, and I have many in the past, but 2.5D is pretty cool. Going forward, maybe we want to touch about sketching in computational archaeology. This is a drawing that I put together several years ago to try and go from my archaeological remains to a magically inspired 3D reconstruction. So how do we do that? Don't know. Our chain is going to figure it out in the next 2 months, maybe. So we're still working on that and other aspects of it. Then LLMs, also here at CVPR, we have some papers, video generation LLMs. Please come see it. It's cool stuff. But also we want to play with LLMs in the urban generation environment. So we have some project on the way to try and use LLMs to help us with this whole urban generation. So this is an exciting next step in progress. And as I mentioned at the very beginning, it's not just me. There's a bunch of co-investigators and co-authors and many of these projects that I list here, and some graduate students. And if I forgot anybody, please, I apologize, but I try to be comprehensive. And the many undergraduates also work on some of these things. I've about 22 total, about half of them worked in urban-related things. So we have a bunch of people, and we're still actively moving forward. And then there's, of course, people who give us money, and I thank you very much for your attention. I think I have a few minutes for questions, if anybody has any.
We have about 5 minutes. Yeah, please approach the microphone. Don't raise your hand. Just walk right up to the microphone.
What's the resolution of the cell page? Because it's
So
a little blurry.
So Planet Labs gives two major products. The one we use the most is 3 meters per pixel and daily capture. And then they also have a something called on demand, and there's some archive, which is at roughly 0.5 meters per pixel. Worldview is 0.33, so they're almost as good as Worldview. That's what we've been playing with. As a context, the other satellites around there is European Sentinel, that's like 1 meter per pixel. Landsat is 30 meters per pixel. So a spacer satellite is kind of 30 meters per pixel, 1 meter per pixel, 30 meters, 3 meters, 1 meter, 0.5 meter. Those are kind of the options out there. As you go down in resolution, you go up in price and less accessibility.
Daniel, I have a question. So the generative way, how can you use generative way to do reconstruction? Because the generative method will create a random, stuff, right? But sometimes we don't want random stuff, we want reconstruction, which is exactly same as the real world. How can we use generative way to do reconstruction?
So let's see. Maybe the difference is just in the rule set that you're using for the generation, right? So yes, if you're generating Brownian motion, that's different than generating discrete hard corners and boxes, right? So probably we've been playing more with generating things in that spectrum close to the Brownian motion, like tree locations. But for layouts, we actually generate explicit structures that are reconstructions, attempts at reconstruction of the real world. Probably maybe what you mean. So okay, maybe it could be where you're on a spectrum of like Brownian motion to discrete motion. The other is your accuracy level, right? So
Yeah, yeah.
if you want to be a 99% accuracy level to reality, that's different than 95. So for air quality, weather, urban planning, do you need 99? I don't think so. Neither do my collaborators. 50% is too low, but 95 might be fine. So I would ask you, why do you want to do exactly
urban modeling, right? Urban modeling, we want to build the digital twins, which is exactly digital
Why?
version of the real world.
Why?
Why for management, right? For you can do in the the digital twin, you can manage planning, in the computer for the real scenario, right?
So I'm not saying it's a bad thing, but I'm going to repeat my question. Why?
Right. There are many demands for that from
Yeah,
civil
but so
engineering.
what
From
accuracy do they need? The actual
the more the better. The more accurate the better. In the surveying, in geomatics, in civil engineering, they want very accurate city models, which exactly.
So I work with a bunch of with her former
Yeah.
advisor, for instance, and I would say that what is the accuracy level that we need?
Yeah,
And you want to answer that first, right? As
Right,
getting
right.
more is of course good, but it might be like we talk about again air quality, weather, right? The accuracy of getting those answers is some value, and you maybe don't need 99%.
Right, depending on the applications.
Depending on the application,
Yeah,
yeah.
yes, yeah.
So maybe that is the first aspect, and then the second one is how many rules you incorporate beforehand, I guess. Maybe
Okay.
that's a bushwashing answer.
Okay, thanks.
Yes,
Two questions.
yes.
Yes, so for various applications, you looked at trees, you looked at buildings. What is next? Like, is there any interest from all these real world applications and real world rulers, let's say, about, I don't know, traffic or pedestrians or I don't know, other urban things that is not in those census information correctly. And the second question is, especially when you don't need maybe exact visualization or geometry or some like real representation of that information. Would it be possible to actually go to another representation that is not instance-based, but more like volume-based, or maybe even like, there's large-scale Gaussian splatting approaches that are trying to visualize the cities, etc. Would there be some representation that actually encapsulates that census information or that counting or like that like species information, etc., a little bit more, less maybe geometric, but more volume-based or like parameter-based?
Okay, great. So the first question was, what is there beyond building and trees? So I would say there is the world of kind of the physical structures, exactly gray and green, and that's one interest. So maybe there's buildings, roads, bridges, things like that. And of course, the green is plants, lawns, bushes, trees. But there's also the people side of things. So when you mentioned traffic and pedestrians, so that's the social side of the urban modeling, which is very important. And I have not done a bunch in that side. I see people or meet with people who do worry a lot more on the people, social side of urban environments. And that's true. So that's another aspect, which is a big can of worms also to be investigated. The second one about the other representations. So yes, in fact, I like the term fit for purpose models. So in fact, I didn't detail it, but for the different applications, to use your word, of whether it's weather, air quality, ecosystem services, carbon storage, there is parameters that are needed that are beyond straightforward geometry. So those are often things that we incorporate in our fit for purpose models. So like if you want to do, like we're working on a fire proposal now. So to do, fires, assessment, prevention, configurations, what matters for a fire, right? So certain fuels around the city matter for a fire. So knowing that is important. And that's beyond just building and trees. There's other things like materials and things that are stored elsewhere, in liquids and things like that If you look at air quality, then certain parameters you need to know about the emissions, man-made emissions and the tree emissions and absorptions. And there are other stomatic parameters of vegetation that need to be known. So there's other things beyond geometry, so that we kind of tie those in with our collaborations and trying to infer those as well. I think that is more than volume. Volume is still very geometric thinking, right? So these are other more specific parameters, which are very hard to measure. So those we're trying to do through generative modeling, so like this tree approach, right? We infer a lot of parameters, which are things you just don't see in a satellite, and the only way to see them is to go up to the tree and look at it, and that doesn't scale. So then how can we do it otherwise? I'm being pushed off the stage.
I'm so sorry, but the next part is really tight.
Okay.
Okay.
Thank you very much.
That's all. Thank Daniel again. Great talk, great questions, and definitely follow up. I'm so sorry.
Okay. Is how to obtain such nadir shape. We call nadir shape this footprint of the layout. We start having an attention mask in order to remove the clutter, and then we predict using the gravity aligned feature to compress this structure in order to obtain a depth of the uncluttered layout. This is not enough, of course, because as you can see, the depth is not easily to be converted in a structured way. So we introduce a native transform. It is a particular geometrical transform described in the paper, and then we obtain a projection of the layout represented that is not the real layout of the room, but just a partial representation only from the visible point of view. Whoops. Okay. Then, once we have enjoined every nadir representation for each room, you use a deformable transformer network in order to join and to segment and complete some part of the room that are not visible from only one point of view in order to obtain a complete of the room. Okay, here we have some results. As you can see, even if you are working with a large number of rooms, we are able to reconstruct every room, even with the height of the floor, because at the same time we are able to segment not only the floor, but even the ceiling level as 8 maps in order to reproduce the height of the ceilings, even the shape, if the shape is different from a typical Atlanta Manhattan world structure. That's all. Thank you for your attention. See you at the poster session.
Thank you very much. I think unfortunately we don't have time for questions, so this next one.
Maybe the poster, perhaps.
Yes, of course, of course. Please do follow up if you have questions with him. We definitely want to inspire collaboration.
Okay.
And Yuanbo, if you would please come and sit up here for the next one, that would be really great.
Okay. Hello everyone, my name is Jay, and I'm very happy here to present our work called CityGen, and it's for infinite and controllable city layout generation. So to begin with, our motivation for this work is to fit the growing demand of city layout generation, and we see some current limitations in existing methods. So we propose this framework. So our framework can be split into 4 stages. So in the first stage, we do local block generation, which is a local semantic map, which that represents a local region of a urban region. In the second stage, and we also expand the semantic layout to user design scale in the first stage. In the second stage, we perform refinement on the global semantic field. In the third stage, we synthesize a height field for the semantic field, and in the final stage, we combine the semantic field and height field into a 3D layout. So we represent a urban layout, a local urban layout as a semantic image, which is H by W by C, and C is a number of classes we cover. So we in total have 7 classes, and they are shown at the bottom. So our base model for generating a local semantic layout is a diffusion model. It's just a diffusion model trained in the one hot image space, and it has 7 channels. And we have a pixel to meter ratio of 0.5 meters. So here we show some results between our base diffusion models and other methods. So why we have 3 models, and I'll explain this later. And this is just some comparison FID and KID between other generation methods. Besides the base generation methods, the first thing we did is to expand the local semantic layout into a infinite user design scale. So how we did this is we leveraged the augmenting ability of diffusion models. Basically, our base model has C channels, and we just added extra C+1 channels, and train the augmenting models. So such that during inference, we can pass the original local region as a condition and expand the region into user design scales. Basically, we just use sliding windows in all directions until we reach the design scale. And these are some results for the global generation. Okay. So thank you. Our second stage is called multi-scale refinement. So since our block generation models are all trained with images downsampled to the lowest resolution, the generated images must be upsampled to their original resolution through nearest interpolation. And this downsampling during the training will lead to some loss of details. And we observe that these artifacts mainly fall into two categories. First, there are some unclear object boundaries, and second, we saw some isolated irregular pixels, like a single water pixel or a single vegetation pixel. So what we did is that we designed filters to detect these edges and the irregular points, and then we masked these irregular regions as unknown, and then used the refined models to repaint the raw samples. So our refined models are just in-painting models, and these are the two other base models. These are developed from the two other base models, and they are trained using a similar objective as the augmenting models. So the core idea behind this is that during training, all images were downsampled to the lowest resolution, but the less the images were downsampled, the more details we kept, such that we can use model trained with lower scale images to fix details sampled from the larger model. Okay, so this shows a comparison between generation plus direct upsample and the generation plus refinement. And as you can see, the edges become smoother, and we were able to fix the irregular points. And the in-painting models can also be used for control generation. So given the user sketches, we can just feed these sketches to the in-painting models, and we can generate these semantic fields according to user controls. The final stage is to synthesize a height field for the semantic field. So basically, we observed that for types like terrain and vegetation and water, we just used simplex noise to to simulate the elevations of these types. And for a road, footpath, and the rails, we just use fixed heights. For buildings, we just sampled random, each building we sampled random building types and random heights. And finally, we just combine the semantic map and height map to construct the 3D layouts. And we have also created a data set which contains semantic maps of all scales. Okay, so in summary, we trained one-hot diffusion models for realistic and diversity layout generation. So our base models, all models are only size 128, but we could generate city layouts up to the size of 248. We also developed augmenting and in-painting models for infinite expansion and the local refinement. Finally, we converted the 2D layouts into 3D by using a rule-based height field generation, and we also contributed a data set of city semantic layouts. Okay, thank you.
Yeah. And what we're going to do for questions is at the end, we'll do questions for all the speakers. So remember your questions for the end.
Yeah. But each speaker has 5 minutes.
Yeah.
Yeah.
Okay.
Can just use it.
And Wei-Heng, you would come up and
you can use it only.
I need to have splits, so I'm maybe going to do it side by side.
You want to switch completely?
Can I?
Yeah, but it's complicated. We only copy your slides here. It seems.
But I need to use the script.
Okay.
This one doesn't use script.
But do you have the link, Zoom link for
Zoom link.
Zoom link? Yeah, because it's on Zoom.
Just use this computer and I'll hold this for you.
I can do it actually. Just move it a little bit. Yeah. Sorry.
Huh?
I can do this. It's fine. Oh my God. Thank you. Yeah, hi, everyone. My name is Yuanbo Xiangli, and today, on behalf of all the authors, I'm going to present our work, which is ProcGS. Which stands for Procedural Building Generation for City Assembly with 3D Gaussians. Yeah, city scene modeling is pretty pervasive in various applications, including VR, AR, and films and games, etc. And to also give user immersive experience, high quality 3D city assets are essential. So recent methods like Infinite City and City Dreamer leverage generation method to scale up 3D city generation. However, the rendered visual quality and geometric accuracy remain subpar, and buildings central to urban environment pose a major challenge due to their complex geometries and also diverse appearances. And existing 3D object generation approaches like HyperDreamer and Hunyuan 3D often produce implausible results. And upon closer inspection on such results, we notice that these artifacts usually come from distorted windows and doors and also unnatural geometry or layout. So, in contrast, industries have a long history using procedural generation to create high-quality 3D buildings and cities, like, for example, city engine projects on UE5. And typically, this procedure involves first create a set of base assets, like windows and corners and pillars, etc. And second, design procedural rules and configurations, and finally, assemble these assets accordingly. In this way, artists can construct scenes in a scalable fashion, reusing assets as demand. So we kind of gain inspiration from this framework. Well, how much work goes into creating base assets? Let's look at this example. It's called Habitat 67. So to bring this unfinished vision to life in UE5, the team starts from scanning the real building to get the raw 3D mesh. But because the mesh itself lacks details and is not easy to manipulate for content creation, artists need to redesign every component using the mesh as the reference. Well, recently, 3D Gaussian splatting has gained significant attention for its photorealistic visual quality and flexibility at usage. So we propose this framework that integrates procedure modeling with 3D Gaussian splatting to enhance city generation at scale and also with high visual fidelity. So to simplify the problem, we first assume the ground truth procedural code is provided. We created the matrix city building dataset which contains 17 buildings from the city sample project. And each scene includes dense multi-view images, ground truth camera poses, and ground truth procedure code. And this is an example of the building procedure code. So different levels here are distinguished by colors, each represented by a string of characters indicating the instantiation of assets. And base assets like C, E, and W1 for level 1 and 2 are manually created by artists. And our framework basically consists of two stages. First is asset acquisition. So given the procedure code, we acquire these base assets in the training process of 3DGS. The idea is that shared base assets should be optimized together. So supervision signal from different instantiations will be aggregated to update the base asset. And to accommodate subtle appearance difference between different instantiations, we add variance assets, which is another set of Gaussians for each instantiation. So these assets are then assembled according to the procedure code and add variance assets to create a complete building supervised by view synthesis laws. And the second stage is asset assembly. So here the building generator assembles base assets into complete buildings following some procedure code and building parameters from user inputs or generated by system. Then the city layout generator will assemble these buildings based on urban spatial regulations. So as shown in this table, using shared base assets, our method achieves comparable novel synthesis quality while significantly reducing the model size by a factor of 4 on synthetic data. For real-world scenes, our method achieves on-par performance with 3D-GS while using a smaller amount of Gaussian primitives. And furthermore, by simply manipulating the procedure code, we can flexibly edit the building geometry and also create novel architectures. Oh, I don't have permission to that file. Okay, here I want to show 2 demos, which first one is building alternation. What should I do?
Whose file is this? Is it, do you have it in this one?
Yeah, I have this here.
Just move this. It's fine.
Okay, great.
Just verbally describe what's happening.
Yeah, so this, okay. This is a demo showing building editing. And for that ancient building, we first acquire assets using manually labeled procedural code. So we can kind of partition the entire building into several base blocks. And then we can reconfigure the building using a newly generated procedural code. So you can see basically the building is enlarged to some factor. And the quality is still like realistic. Yeah. And next is also a demo, like we create a city using ProcGS, using our method. And we put the model in UE and have a free camera controlled by users to kind of navigate through the entire city. You can feel the quality is very realistic. Yeah, and this is our project page, and you can always find more technical details and demos on that one. Thank you.
Yeah, remember your question for again, you take out. Speak. Okay. Right.
Okay. Okay. So hi everyone. This is Wei Han Li. I'm very happy to present our work texture to LD3, enabling LD3 building reconstruction with panorama images. So our project the input is the geolocation. So here our input is the latitude and the longitude, and then we also get the street view level images. So from this, we can build the LD3 reconstruction on the existing LD2 building models. So here from left to the right, we have the accurate auto texturing, also very accurate semantic segmentation, and also finally the facade-rich level of detail reconstruction. And so what is LD3 building reconstruction? Here is an illustration. So from the left to the right, it describes a different level of the detail for the buildings. So here you can see different things on the facade. So why do we need that? So here, because it has various downstream applications. So here you can see a lot of applications relied on the very accurate LDC. So state-of-the-art methods doing this LD3 building reconstruction requires additional information. For example, first, many methods leverage the sensor-based method, for example, the mobile laser scanning or UAVs. So for example, Scan-to-Load3 uses priors for LD3 reconstruction, but they depend on costly LiDAR inputs. And the second one, they need a manual or semi-automatic projection that involves very labor-intensive work. So this is also limits the scale of our data set and the application. So then considering we have a worldwide 3D semantic building, for example, the LD2 building models here, can we leverage the ubiquitous LD2 model and also the panorama images to enable our LD3 reconstruction? And here's our thinking. So our idea is very simple. So given the LD2 model and the geolocation, we find where the building's located at, and we also can easily extract the panorama images from the Google Street View by just given the longitude and latitude. And then we do the auto rectification and then associates the panorama images with the building. And then we get the segmented facade, and then we do the texture projection onto the LD2 building. By doing so, we can then get a texture mesh on the on-hand LD2 building. Building on the top of that, we can do the semantic segmentation on our texture 2D buildings to enable our facade element segmentation, so to say the LD3 reconstruction. So we conducted our experiment on the twin-to-twin dataset, which is a very comprehensive benchmark for the urban digital twin that collected annotated point cloud LD3 geometry and as well as the texture LD2 geometry. So here are some examples on different kind of buildings. So regardless of the width of the facade, we demonstrated our method perform consistent performance on different facades compared to our baseline 4-point manual twin-to-twin dataset and with our service rectification and our method. And quantitatively, our method achieves very great results compared to all the baseline. And also note that our method only requires the knowledge of the geolocation, while the other methods, they require, for example, additional input or manual label for the data set. So here's some experiment on different kind of closed set and open set semantic segmentation method. So in conclusion, our texture load 3 enable automatic LD3 reconstruction from only the panorama images. And then we also outperform our standard projection by 11% of IOU. And our method is robust to perspective distortions. And this also unlocks the scalable and global LD3 construction using widely available LD2 model and the panorama images. And lastly, we also preserve georeferencing and water tidiness and low poly requirements. And so also many thanks to the mentors, Olaf Rudowski, and in this project until we get here. So also interested people can also check out the webpage here for his new group from the Technical University of Munich to the University of Cambridge. Okay.
Thank you.
Please do. Okay. Yeah, no, thank you.
Hello everyone, I'm Luca Barco, and today I'm glad to present our work USM3D evaluating adaptation strategies under labor scarcity in urban LiDAR segmentation with semi-supervised techniques. Sorry for my voice, but I'm a bit cold. The main contribution of this work, as the name suggests, is the presentation of a new dataset. This dataset covers a very interesting area in the Turin city, located in Italy. It is interesting because, as you can see, there is a residential area, then there is a very huge park crossed by a river, and then there is an hillside area where there are a lot of villas and pools and stuff like that. This dataset was acquired by using airborne laser scanning sensor, and it was divided in a grid. And here you can see that the blue boxes represent the the train split, the orange, the validation split, and the test, the green split. The only problem is that due to the high cost for manually labeling the points, only validation and test set were actually manually labeled by us, by 4 human annotators. Instead, the train set was totally unlabeled. For this reason, in the name of the paper, there is the word label scarcity. Furthermore, we collected other datasets from literature, and we also try to harmonize all the classes taxonomies, resulting in these 6 classes. So the dataset, as you can see in this video, provides soil, terrain, vegetation, buildings, element, and water, and we choose validation and test boxes in order to have a class distribution that is similar between test and validation set. Once we have manually allocated the dataset, we try to face the challenge of the scarcity of labels. We first of all tried the classic transfer learning approach. So we get all the literature datasets that we saw on the last slide, train several models. We tried 3 different architectures: random-net, point transformer, and sparse-conv, and then see if these models were able to generalize well on Turing 3D test that was manually labeled. And these are the results reported in this graph. We can see that actually random-net was the best performing model, resulting in a mean intersectional union of almost 40. Then we tried to do something more interesting. We tried to exploit also the Turing 3D train set, even if it was unlabeled, trying to get the best performing model from the transfer learning experiments, and to generate pseudo labels on Turing 3D train set, along with confidences, and try to filter these confidences and take only the classes for each point when the model is more confident. And we then retrained again a new instance of the same architecture of the same model, only on Turing 3D train, and see if this could be beneficial for Turing case specifically. And so we can see that almost in all classes we have a significant performance gain using this approach. Then we did one step further. We tried to repeat this step iteratively using 2 iterations. At each iteration, we tried to recompute the pseudo labels by recomputing the threshold that we use to filter the confidence scores coming from the model predictions. And we have compared this approach with the classical approach using fixed confidences 3 times, and we saw that using this adaptive confidence thresholding, both F1 score and intersectional union actually increase. So that's all. Thanks you for your attention. See you at the poster.
Thank you. So our next speaker will be this one.
Hello, everybody. I'm Giacomo D'Amicantonio from the University of Eindhoven. I will present this work, Near Incident Detection in Railroad Environments. This was conducted by my student, Yilei Wang, who couldn't be here to present it. So last year, Arriva, a company in the Netherlands that handles safety and security for rail tracks, asked us to provide or to design a framework to detect near-miss incidents in this railroad environments. So when a pedestrian is passing too close to a train, or maybe a vehicle stops on the tracks, situations like that. So they define a near-miss as a situation where anything is within 70 centimeters from a moving train. But this is not really straightforward, because every conductor has a different interpretation, and in the split second where they have to make a decision if to classify something as a near miss or not. Every conductor has a different decision process, so they cannot have a unified definition, basically, or unified data set of near misses. So what we did was we designed a near miss detector, which is a framework that leverages state-of-the-art models to provide an accurate and precise lateral measurement of people and objects from the tracks. This pipeline comprises of 3 streams. The first stream handles the objects or the agents that are near the train. In the first step, we detect the bounding boxes using yellow word, and then we obtain the semantic masks using EdgeSAM, which is a very fast SAM style model, basically. And so we obtain the semantic masks of each person on the platforms of a train station. Then we detect the pixels belonging to the track where the train is moving. So we want to create a semantic mask also for the track. And for doing this, we used a dedicated model that was already published a couple of years ago. That's called the TAPNet. And finally, we need to unify or to make match all the pixels in the image because they belong to different heights. The platform is higher than the track, so we need a depth estimation model, and we use depth anything to obtain where in the space or in the third dimension of the space each pixel is located. Further on, ELA developed this algorithm to calibrate the depth map because with depth anything, the calibration accuracy, the depth accuracy declines very fast after a certain threshold, about 20 meters. So we leverage this spacing of the sleepers. So the sleepers are the wooden pieces that are between the tracks. Which is always the same, is constant everywhere, and also the gauge of the track, which is also the same everywhere, obtaining a map that's more representative and more accurate of the actual 3D scene. Finally, we combine all these 3 streams into one single measurement or one single scene representation, and we identify the points belonging to the people or the objects on the platform and the points belonging to the track. We identify the ones that are at the same depth, so at the same distance from the camera, and we using the width of the track as a reference point, we use it to estimate or to compute how distant from the track each person is. We validate this approach using a dataset that ELA collected by traveling by train from Eindhoven, which is where our university is located, to Schiphol. So he got off the train every station and measured everything in the train station, basically, which was pretty funny. But this resulted in 700 images and about 2,000 pedestrian rotations. So a pretty extensive dataset. And these are the results that we obtained. We found that 90% of the predictions of NMD or of our framework were below the mark of 50 centimeter error. So it means that for every measurement that NMD was doing, the error was below half a meter, which is very impressive because you have to think about the fact that the measurements very close to the camera could be very accurate, but the ones that are very far from the camera tend to be very wrong. So if you come upstairs at the posters later, I can show you the results also for without a depth calibration, for example. You will see that the maximum error that the model was doing was actually of above 50 meters of error. So not great. This is an example of what happens. You can see that we have 2 regions of the train station that are labeled because those are fixed measurement that every train station in the Netherlands has to have. And we are able to use that as a validation for the lateral distance that our framework was estimating. So that's all for now. Questions? We don't have time for questions, but you are welcome upstairs at the poster and we can talk more about this. Thank you.
Okay, and then one of our, the last spotlight, unfortunately due to time differences in visas is not able to present, so we have a video, but maybe let's do, because they won't be able to answer questions, let's now do questions for all of the other spotlights. So if you have questions for any of the spotlights, please approach the microphone now. Let's get at least one question. How was the train ride?
I had a question that I already forgot, but I think it's coming back to me. I have a question for yes. Hi, yes. Can't you, but I will, or microphone, I don't. I can do this, wow, okay. The rotation, sometimes we forget about. So for the buildings, is it mostly facades, or do you also go to the modeling of the geometry as a lighting in the Japanese looking building? It was like super detailed. There were like Manhattan building elements in it. But in the city example that you showed, like the top parts were maybe just textured and no geometry. So what is it just based on like what is defined as input as the grammar units, or can you actually extract them from the existing 3D model in a defined granularity?
Then it goes like first we run 3GIS optimization. So that's a 3D modeling technique. So on this building, so we have dense capture of the building, and then we train 3GS. So we have the Gaussian splatter representation, and then based on the procedural code, we'll extract the base assets from the 3D Gaussian splatting model. So eventually we will get the 3D assets instead of just the facades.
So the asset granularity comes from the procedural representation.
Yeah.
And that is predefined?
So for synthetic data, that's usually predefined by artists, but we also try to manually annotate on the building. So that actually depends on the user. If you want cross partition on the facade of the building, you can get cross assets. If you want fine grain, you can get fine grain.
All right, any other questions before we go to the last spotlight? Okay.
Good afternoon. Today I will present our work, schematic 3D reconstruction from point cloud with sparse annotations. Well, imagine you want a fully labeled 3D.
Is it? Let's just go to Jonathan Lee and then we'll come back to this.
Sure.
You have it on disk here?
Yeah.
Okay, we're gonna swap the order. We're gonna do a different video first and we'll come back to this.
From where is
For 3D model of this block, mainly on every point with its class of building and tree is simply too slow and expensive. Yeah, the capital dense geometry is easy. Data scans.
Thank you for your patience. You have Jonathan on the disk?
Yeah.
Yeah, play it.
Right,
play it
from
first,
here.
yeah.
Yes, yeah. Here. I need to share the stop share.
No, it's okay.
Huh?
Yeah, no. It's good how it is now. You don't need to stop sharing. It's already good. See?
Yeah. Okay.
Hello, everyone.
Oh,
The topic of this talk is transformer-based.
Yeah.
Here we go. Here. Right?
Yeah, sure.
Okay.
Yeah, our last keynote speaker is Jonathan Lee. He is a professor from University of Waterloo. He's from a geography department and urban planning. Because of personal issue, he couldn't come here, so he recorded a video for his speech.
For cloud processing, and analysis for LiDAR remote sensing. Hello everyone, the topic of this talk is transformer-based point cloud processing and analysis for LiDAR remote sensing. This talk consists of 6 parts. In part 1, we are going to introduce some background knowledge of point cloud processing and transformer. In the field of remote sensing, 3D point clouds have significant advantages over traditional 2D imaging. Specifically, compared to 2D images, 3D point cloud data captured by LiDAR sensors contains rich spatial information. It's also not dependent on viewports and less affected by the environment. These advantages make LiDAR point clouds more suitable for remote sensing applications, such as forest mapping, topographic survey, urban modeling, and planning. In LiDAR point cloud processing, there are 5 main challenges: global context modeling, data imbalance, uneven density, occlusions, noise, and outliers. Deep learning is mainstream for point cloud processing, which can be divided into 3 main categories: voxel-based, projection-based, and point-based methods. Firstly, for the voxel-based method, is to partition the 3D space into uniform voxels, then use mature 3D CN for feature extraction. Its limitation is geometric information loss caused by voxelization. This kind of method cannot handle challenges of global modeling and uneven density. Secondly, for the projection-based methods, is to project 3D point clouds onto 2D planes, then use mature 2D CN for processing. Its limitation is geometric information loss caused by projection, and also it's challenging to choose the optimal projection views for complex LiDAR scenarios. This kind of method cannot handle challenges of global modeling, uneven density, occlusions, and noise, especially for dense prediction tasks, such as point cloud segmentation. Thirdly, for the point cloud-based method, is to directly process sparse point clouds, keeping the geometric details. It can be further divided into MLP or CN-based and transformer-based methods. The main limitations of MLP or CN-based methods are challenging to learn global information and also introducing the inductive bias of locality, such as bonnet++. So this kind of method cannot handle challenges of global modeling and noise, especially for MLP-based methods. Lastly, transformer-based methods overcome all the challenges we discussed before and adapt to with the unordered LiDAR point clouds. Specifically, we showed structure of the transformer block where the main component is the self-tension mechanism. The self-tension measures the correlation of any 2 input points by calculating the similarity matrix. After that, how the feature is generated by computing a weighted sum of all input features. The weights are from the similarity matrix. So it's able to establish connections with all input features for global context modeling, and not limited by the disorder of point clouds. Here we summarize the advantages of transformers. Firstly, compared to voxel and projection-based methods, transformers deal with sparse point clouds directly. Secondly, compared to CM, transformers are better at long-range dependency modeling without inductive bias or locality. And lastly, compared to MLPs, subtension is dynamically depending on the input, which is more effective than MLPs. So this is why we choose transformers for 0.5%. More interestingly, we counted 2 linear rewards of 3D transformers: point cloud transformer (PCT) and point transformer (PT). Both of them were published in 2021. We can see that their annual citations continue to increase from 2021 to 2024, which also illustrates the rapid development of transformers in point cloud. However, transformers also have some challenges. Firstly, imbalance in local and global feature extraction. This is because some early pure transformers focus on either the local or the global features, without considering their combination. So for this challenge, our objective is to propose a 3D local transformer network, 3D GTN, combining both local and global features for comprehensive representation of point clouds, which forms our part 3. Secondly, limited exploration in fast transformer design. This is because most hierarchical transformers, including 3D GTN, still have the traditional point sampling and grouping methods, which are very time-consuming and limit the network's inference speed. So for this challenge, our objective is to design a fast transformer by optimizing these time-consuming blocks, which forms our part 4. Thirdly, high computational complexity and memory consumption. These are from the parallel self-tension calculation. The computational complexity of the self-tension is quadratic to input size. So for this challenge, our objective is to propose a novel dynamic supertoken clustering block, which can dynamically simplify the input points to reduce the model complexity, which forms our part 5. So in the second part, we will present a brief overview of 3D transformers. Firstly, the earlier 3D transformers can be divided into global and local transformers. The global transformer, taking PCT as an example, it feeds all input points into transformer blocks for global feature extraction. And the local transformer, taking PT as an example, is only operated on local neighborhoods for local feature extraction. As we discussed before, these early pure transformers failed to consider both local and global features. Therefore, our first objective is to propose a 3D local transform. Secondly, most transformer methods for large-scale photographic processing use hierarchical structure. However, the common horizontally and grouping blocks in them are very time-consuming, limiting the model's inference. Therefore, our second objective is fast transformer design by optimizing these time-consuming blocks. Thirdly, many efficient transformers were proposed to reduce the model complexity by using superpoint clustering. The traditional superpoint method only uses initial geometric features, generating geometric homogeneous clusters to simplify the forms. However, it cannot adaptively serve the semantic features at different levels of the deep network, limiting their performance. Therefore, our third objective is to further develop the efficient transformer by dynamic superform clustering and optimization. In the next 3 parts, we will present our main works. The first part is 3D local transformer network, 3D GTO. Based on the challenges we discussed before, this part is to propose a 3D GTO framework that combines both local and global information. For the contributions, firstly, to learn local information well, we propose the graph convolution-based local feature aggregation block, LFA. Secondly, to learn global information well, we propose the dual attention transformer-based global feature learning block, GFL. And thirdly, the local module, including LFA and GFL blocks, are stacked to construct a new hierarchical framework in the 3D GTO. For the LFA block, it first downsamples into points by fathers point sampling FPS to ensure the diversity of the receptive files of each sampling point. LFA has 3 different scales of neighborhoods achieved by the k-nearest neighborhood searching method, PN. In each neighborhood, graph convolution and max coding are performed for local feature aggregation. And finally, 3 local features from different scales are concatenated as the final local feature of each sampling point. After LFA, we propose a GFL block for global feature learning. It contains 2 kinds of self-attention, point-wise PSA and channel-wise self-attention, CSA. The PSA is to build spatial correlation between points, achieving long-range context modeling. And CSA is used to measure the correlation among different feature channels. So by combining PSA and CSA, GFL can capture global features from multiple perspectives. The LFA and GFL blocks constitute a local module, which is the main contribution in this part. As shown in the left figure, the input points pass through the LFA and GFL blocks. And finally, after feature information, we get the final local features. As we can see, the local modules constitute the main body of the 3D GTO. Taking the point cloud segmentation network as an example, for each input point cloud, 3D GTM first uses a MLP layer for feature projection. Then it includes a series of local modules for hierarchical feature extraction, which constitutes the encoder structure. There is also a decoder structure offset for the point cloud hierarchical. Generating a semantic feature for each point. Finally, an MLP-based head layer is used to output the category prediction for each point. So this is the overall structure of the 3D GTM framework. For the experiments, we use the 3 datasets for model testing. The first 2 datasets are synthetic, which are used to verify the effectiveness of the proposed network and blocks. But due to time constraints, we won't detail. For the LiDAR semantic segmentation, we use an airborne multispectral LiDAR dataset. This dataset has 13 areas, with 10 for training and 3 for testing. Each area covers 15,000 square meters and have an average point density of about 3.6 points per square meter. Every point has 6 attributes X, Y, Z, and 3 wavelength channels. And finally, the OA, MLU, average F1 score, and model latency are used for evaluation. For the results, we show the comparison result in the left table. The comparison model includes MLP or CM-based and also transformer-based methods. We show the comparison in bar charts for clear visualization. The middle charts show that 3D GTM outperforms benchmark MLP or CM-based methods with highest values of all 3 metrics. And the right charts show that 3D GTM is also better than other transformer-based methods of the same period. As a summary, this part proposes a 3D local transformer network, 3D GTM. It achieves higher accuracy than other transformer-based methods of the same period. And for the limitation, the downsampling and grouping blocks of 3D GTM are time-consuming, limiting the model efficiency. The fourth part is fast form transform with ambient revision. Three, 4, yeah, and two, 3, and the meek. For the first contribution in this part, the LTS block. After feature embedding, it generates the level decision score for each point. Then we select the top S points with the highest scores as the sampling points. As shown in the right chart, as measured by the model latency, LTS is about 60 times faster than FPS. The latency represents the running time of the model for each input sample. The larger the value, the slower network. After token sampling, DTA block is proposed for feature clustering and aggregation. replacing the KM method, which is the second contribution in this part. So firstly, we do the feature embedding for the specified tokens and rule tokens. Secondly, a cross-attention calculation is performed to explore the correlation between specified tokens and rule tokens in the global view. We show the attention map in the bottom figure. Size is S by N. S means the specified tokens, N means the rule tokens. This attention map shows the similarity of H rule token and H specified. The darker the color, higher correlation. Therefore, we achieve feature revision for H specified points by calculating the weighted average of all input points. For the advantages of DTA, as shown in the right charts, the DTA block is 2 times faster than here. For the experiments, we still use the multispectral LiDAR dataset. As shown on the left, we show the F1 score comparison between the DTA forward and 3D GTN in each class. The DTA forward achieves competitive accuracy with 3D GTN, where the purple bar is 3D GTN and the green bar is DTA forward. And for the inference speed, the entire DTA forward network is over 5 times faster than 3D GTN. As shown in the right chart, the local feature aggregation process in the DTA forward colored in green is over 18 times faster than that in the 3D GTN colored in purple. So finally, it achieves the goal of fast transform design. As a summary, this part proposes a fast DTA forward with efficient learnable token specification and dynamic aggregation flows. However, it still has a limitation of a higher space complexity, which is caused by the learning-based sampling and grouping processes. The fifth part is 3D learnable supertoken transformer, 3D LST. As we discussed before, the local feature aggregation in the DTA former contains LTS and DTA blocks, which improves the inference speed, but also they increase the space capacity of the model, taking more GPU memory. As shown in the left, this part is to further reduce the space and time capacity of the model by optimizing LTS and DTA blocks. So we further developed the efficient transformer named the 3D LST. For the contribution, we propose the DSO block. Board name is dynamic supertoken optimization to reduce the space and time capacity of the model. Specifically, the pipeline of the DSO is shown as left, which is the main contribution of this part. The supertokens are randomly initialized and gradually optimized during the network training. In each optimization, the cross tension is calculated between the supertokens and the row tokens. In the bottom figure, the size of the attention map is S by N. It's a hard assignment, which means each row token only belongs to one supertoken. So the attention map is discrete. And the red points in each row represent a supertoken cluster, which is a semantic homogeneous cluster. Finally, the supertokens can be updated by averaging all the row tokens in the same cluster. And as network training, these learnable supertokens can be gradually optimized. and achieve more and more accurate semantic clustering results. For the advantages of the DSO block, firstly, as shown in the left chart, the number of supertokens is only half of that of the sampling points in the previous methods, which leads to lower space complexity. And also, as shown in the right chart, the DSO is over 40 times faster than the LFA in the 3D GTN and over 2 times faster than DTA in the fast DTA form, which means a lower time complexity of the DSO block. For the results, on the multispectral LiDAR dataset, 3D LST achieves better accuracy in most categories compared to the previous 3D GTN and DTA form. The left charts shows the F1 score comparison of these three methods in each category. As we can see, the 3D LST colored in blue achieves the highest accuracy in 4 categories and competitive accuracy in the rest 2 categories. And the right figures show the visualization results of comparison. Actually, we compare 3D LST with other transformer methods, including the current SOTA methods. 3D LST achieves excellent performance similar to the SOTA model PTV3 or Transformer V3 published in CVPR 2024. As shown in the left chart, 3D LST has the highest segmentation MLU on the LiDAR dataset. And in terms of model efficiency, as shown in the right chart, 3D LST is over 18 times faster than 3D GTN and over 6 times faster than DTA forward, and also over 3 times faster than the most recent PTV3 model. So in conclusion, 3D LST finally achieves excellent performance in both model accuracy and efficiency. Finally, we show a complete semantic segmentation process of 3D LST, including data preprocessing, model inference, and sample merging. This area covers 500 meters by 500 meters with over 10 million points. The entire process can be completed by 3D LST in less than 1 minute and a half in the case of single CPU and single GPU. Lastly, I'd like to provide
I think it might be in the base out here for now. I'm just gonna skip forward a little.
that be for the limited exploration of fast transformer design. We developed a fast DTA form to optimize time-consuming blocks in 3D GTN. And lastly, to address the limitation of high model complexity of the DTA forward, we proposed a 3D LST with dynamic supertoken optimization, further reducing the space and time complexity of the model. For discussions in terms of model efficiency, the right top figure shows the continuous efficiency improvement of the proposed methods on multispectral LiDAR dataset from 3D GTN in 2022, DTA forward in 2023, and finally 3D LST in 2024. The left figure shows the efficiency and accuracy comparison of existing methods. The red star represents 3D LST. In this chart, the horizontal axis represents latency and the vertical axis represents accuracy. The closer method is to the upper left corner, the better its performance. So it shows that the 3D LST has excellent performance in LiDAR data processing in both accuracy and efficiency. And for the future research, the first direction is to explore more efficient attention mechanisms for LiDAR point cloud processing, such as MANDA and flash attention. And secondly, unsupervised learning techniques have been verified to outperform traditional supervised methods, such as PONET and PONET++. Therefore, this is also one of our future directions in LiDAR point cloud processing. Here are some references used in our presentation. Thank you for listening.
Okay. Thank you to those. Thank you to those who stayed. We really appreciate it. Yes, it's definitely unfortunate that Jonathan had an important family issue that he had to attend to. So now I will play a 4-minute video from the last spotlight, and then we'll go to the poster session. And when we come back, it'll be Fede and then Bjorn Omer, and then our collaboration and discussion session. So please make sure to be back here for that. That's going to be awesome. And with that, I'll play this last 4-minute video.
Good afternoon. Today I will present our work, schematic 3D reconstruction from point clouds with sparse annotations. Well, imagine you want a fully labeled 3D model for city block, manually marking every point with its class around building a tree. This is simply too slow and expensive. Yet capturing dense geometry is easy. LiDAR scan give us millions of points, so we asked, can we leverage this plentiful schematic to dramatically cut down on schematic labeling? Previous methods often append schematics onto geometry were costly, differentiable rendering, rely on extra 2D image annotations. So we want a fully 3D solution, no rendering, no extra 2D levels. To some observation led us to assign distance fields as the ideal bridge between geometry and semantics. Was the first geometry and semantic correlation. Similar geometric patterns often correspond to the similar semantic labels. While the second, two samples on the same object surface tend to carry identical semantics, while the labels flow smoothly along a surface. While digging deeper, we see that semantics equal to pattern of primitives. A long plan could be a wall or a floor, but combined with the plan with a set of pillars, you have a table or a chair. Well, semantic consistency aligns with surface approximately like the point A and B have different labels. B and C share the same labels. They reinforce why accurate UDF is crucial for semantic. Well, next, we face two technical challenges. First, previous UDF methods compress the nearby geometry into scalar weights. Well, our solution is displacement aware interpretation, which is explicitly use neighbor offsets. Second, semantics live or only on surface where distance fields fill all space. So we introduce surface-oriented interpretation, giving off surface points the label of the nearest surface to align with them. With those ideas, we propose a framework like above picture with same backbone for two branches. We invest these two branches with mentioned neural interpolations and balance the two losses with uncertain loss. Well, let's look at the numbers. In surface reconstruction, we see 20% boost over the idea of baseline, evidence that all interpolation truly capture neighborhood geometry. On semantics, we stress test from 4 labels all the way down to 0.001%, even at just 0.1% or accuracy budgets. And the quality of reconstructed geometry remains rock steady, no matter how few levels we use. Well, finally, some visual proofs at 0.1% level, we still distinguish a small trash can beside a dresser. And we reconstruct entire semantic surface directly, no pure point pairs need. Then all input demands are minimum, just a sparse label scan plus sparse labels. And as all geometry gets richer, the steps drop in label dependence shifts from 1% down to 0.1%, showing that better geometric understanding buys your big gains in label efficiency. Well, that's all. If you have any concerns, feel free to contact me at this email address. Thank you.
Okay. Thank you again, everyone. We hope to see you back here at 4. The posters are on the 3rd floor. It's numbers, I think, 400 to 430, something like this. But thank you again very much, and hope to see you at 4 for FEDE's talk. Okay, I will pause the Zoom now until 4 o'clock.
Maybe. Of course. Our next keynote speaker is Frederick. He is a musician actually for the 3PR band. But if you work on the podcast process, you must know the short distributor, which is from his work. So today we are very glad to have Frederick for this keynote speech.
Thank you. It's a pleasure to be here. Thanks for the invitation and the nice introduction as well. And so today I'm going to talk a little bit about some of our recent work in the area of generating, capturing, and understanding 3D scenes. I'll just give you like a short introduction about what I'm going to present, if we can actually make this work. Okay, so there's 3 computer vision tasks that we are particularly interested to develop and for bringing, let's say, new technology in the area of augmented and mixed reality. And the 3D tasks that I'm talking about, they're all related to 3D scenes, and they are aimed to generate, to capture, and to understand 3D scenes. And so maybe you already understood what the tasks are. So it's generative models, in particular 3D scene generation, knowledge synthesis, and 3D scene understanding. So the first thing I'm going to say is why are these tasks so important for augmented and mixed reality? And so this is actually a launch that we made recently with Maps in a feature that's called Immersive View. And for a selected number of restaurants on Maps, you can actually enter a new special 3D viewer that lets you navigate in 3D restaurants. So you can freely drag and, let's say, go back and forth, look around, and have this all done on your mobile phone, right? So it's a novel view synthesis, let's say, capability on mobile devices. Now we only have, unfortunately, around 2,000 of these restaurants available, but we plan to scale this preliminary feature up in the future. But it showcases, let's say, the usefulness of this type of, let's say, novel view synthesis capabilities for 3D scenes. Of course, it works for any indoor scenes. That's just, let's say, the particular use cases that we were interested to develop together with the Maps team. Now, it's important to capture and render scenes. It's also important to understand scenes. This is a mock-up from Apple, right, from their ARKit room plan API, where you can just move your phone in real time, again, on device, understand the scene and its parts. And finally, the third one, the generative part, I picked World Labs as an example. It's, let's say, a startup, as many others that are now coming up in this area that aims to develop this type of, let's say, 3D fully generated environments. They need to be realistic, they need to be navigable, they need to be immersive. And so all these tools, let's say, are very important for augmented reality applications. We live in a very exciting time because we've been just witnessed three main step changes in computer vision, or let's say in AI and machine learning, that highly influence 3D computer vision and this task, in particular, the development and diffusion models. They're now kind of like the way to go to develop generative models for 3D scenes. The use of neural representations, in particular, starting from radiance fields. There's been like a huge leap forward in novel view synthesis accuracy and performance. And finally, foundation models, in particular, behind scene understanding. So I'm gonna, let's say, present one work for each of these tasks, in particular about the first two, so the novel view synthesis and 3D scene generation, and then we see if I can also cover the third one. Just a very quick mention about why we want to bring this technology to augmented reality and mixed reality. There's an emerging landscape of devices and OEMs and apps and developers who are now interested to develop technology, computer vision driven, for this type of devices. Did I say something wrong? Okay. And so actually, now we have a large spectrum, like a whole range of devices, from those that are very immersive, with this kind of like immersive display, stereoscopic, episodic, so you only use them a few hours a day, like those on the left-hand side, down to the glasses from factory, so-called smart glasses. They're as light as a pair of glasses. They really look like glasses. You can wear them on. Of course, it's very limited in compute and immersiveness. And then there's a whole set of products in the middle. And what we're now developing, and we announced recently, is Android XR, which is the extension of the Android platform to XR devices. So one single platform for powering this large variety of products or devices. And so this is part of this objective, let's say. Great. Let's start with the first task and component and work. I'm going to talk about 3D scene generation. I'm going to talk in particular about our recent work, CubeDiff. And so you're probably already very familiar with generative models for images and videos. This is Imagen3 and VO2. Very high quality of the results from simple text prompts, because there's actually a lot of data that we can train these models on, right? So the large availability of data makes this model particularly powerful. Now, the goal here is to be able to use generative Gen AI, let's say, not to generate images and videos, but to generate something like that. So immersive panorama, highly detailed, fully generated, that we can start navigating. And so to generate something like that, we start from something as simple as a spatial image format. So we're not starting from the standard image format, but we're starting from like a panoramic image, which is simply like an image, high res, with a larger field of view. We're talking about either 180 degrees or 360 degrees. With specific projections, you say you can make this navigable, we can make this immersive, and we can, let's say, apply them in this type of mixed reality contexts. Panorama generation, there's several methods, but again, most of them are really limited on the limited availability of panoramic images. So we can't really train a large model. And so we can try to, for example, take let's say, standard images and apply, let's say, distort them, but then we have distortions around certain areas, for example, the poles. We have issues in terms of generalizability. For example, there's methods that try to learn a generative model trained on images taken from a specific context where we can capture this type of panoramic image, but then the model will not generalize to other image domains, and so on and so forth. And so we try to find a way to overcome this limitation and reuse the power of large-scale generative models. The idea is actually very simple, and we started from cube and the definition of cube as a volume. In particular, if we find a mapping between an unfolded cube in space and a panoramic image, then we're kind of able to solve the problem of reusing large-scale models, because every single face of the 6 faces of this cube can actually be used as an input for a large-scale model trained on images. So it becomes, again, compatible with this type of models. In particular, our ideas comes from the so-called multi-view diffusion model literature. In multi-view diffusion, the idea is that we want to generate novel viewpoints, right? Novel images taken from novel viewpoints, given one or more images of an object. And so in order to do this, we use this type of, let's say, multi-view diffusion models, where we provide a set of images that are either input or masked, if you want the model to generate them. One of the key ideas here is to use these so-called inflated attention layers. Now, the very important thing is that for the model to be able to cross-attend different viewpoints, so that once you start generating a new viewpoint, it will be consistent with everything else, right? So that's kind of like the key idea. And so for this, there's this idea of inflated attention layer that I'm going to present briefly. And so that's also the starting point from our model. We want to kind of use this type of cross-attention across cube faces in order to be able to have this type of consistency. So again, this is the basic idea. Treat each face of the cube as a frame in this multi-view context, and use a multi-view diffusion model. Now note that if you just apply this idea straight away, you will naturally have discontinuities around the edges of the faces, so you need to take care of that, as I'm going to show you in a bit. This is the model that we use. Again, it's a stable diffusion-based approach. We have a unit that gets encoded versions of the input images. We can start from, we can condition the model simply with a single view, or simply with a text prompt. We can provide a text prompt for the entire cube faces. We can take one prompt for each of the faces. And so just one note here, I want to, let's say, zoom in on this part. I don't have like a pointer, but let's say we want to look in these extra inputs, right? Positional encoding and masks. In particular, we need the mask in order to be able to say which of these 6 faces are actually provided as input and which ones the model needs to instead diffuse. That's the first thing. And then the positional encoding. Also for multi-view diffusion, it has been showed that providing positional encoding is particularly useful to increase the accuracy of the results. In particular here, we use a positional encoding that is derived from the specific 3D geometry of the cube. So practically, we store the UV coordinates on the cube for each of the pixel of the associated cube face. And that's it. That's everything that you need to do, let's say. So again, you start your diffusion process in the latent space. Now, in the diffusion process from stable diffusion, there's this residual block, let's say, where each image is, let's say, flattened, right, across the batch. And then you compute this cross attention around the full image. In order to apply this attention layer inflation for the cubes, what we do is practically to extend this, not just to, let's say, the image height and width, but across the 6 faces, right? So we kind of let the network cross-attend across all the faces. And that's all that you need to do. Then after cross-attention step, you go back practically, you revert this step, and you continue iterating. So you also need to take care a little bit of other processes. In particular, there's the so-called group normalization. You kind of need to make sure that there's at each, let's say, batch iteration, you need to have a synchronized group normalization in order to register tonally the different faces of the cube. And also, you need to make sure that there's no discontinuity across the edges of the faces. And for this, it's a very simple idea. Instead of having like a field of view of 90 degrees, you have a slightly larger field of view, 95 degrees, and then you just crop out everything after the diffusion process. Once you train this model for inference, again, you can condition in different ways, text prompt, one or more images, you encode everything with your VAE, you run your diffusion process around 50 steps, and then you decode everything back, and you get back your panorama. Now, the very interesting thing is that the model that we're using, and we also compared on the paper, is trained on only 40,000 panoramas. Most of them are synthetically generated, and most of them are also domain specific. So we don't really provide, let's say, high generalizability of the images that you use for fine tuning. During the ablation, we actually showed that you don't really need to have that many panoramic images. You can get pretty good results already with 700 panoramic images. And so that's another quite remarkable property, that once you have a large model, pre-trained, you don't really need a lot of images to fine tune, or a lot of additional data to fine tune to your specific task or domain. Wanted to show you some results. Here's the text prompt built into the bookshelves. It's a cozy fireplace with a crackling fire. And so this is the image. Let's say this is the image that I had in mind. But of course, in this case, I also want to apply some editing. And so with many approaches in this kind of like generative area or field, by regenerating with a new prompt, you will completely change the characteristic of the whole image. Well, here we just want to change a small detail, right? Like, just want to do some small image editing task. So you can go back to the prompt, add the detail that you had in mind. For example, we want to fill in this space on top of the fireplace with an antique globe. And then you can see that we can get an image that really looks similar to the previous one, but with the detail that has been correctly incorporated. So it kind of provides also this flexibility around editing. So just to show you some results, this is a breathtaking vista of snow-capped mountains. This is what we got, starting from the prompt. Again, as I said, you can also start from an image rather than a prompt. And so we take this low-resolution image from the web that's kind of related to like a snow-capped mountain, kind of like landscape. And then the image increases the resolution and extrapolates nicely the content around it. And so you see that once you pan slowly towards the right, you get your small alpine house in the middle. Now, just to show generalizability across image domains, this is a result that we got for an image, let's say real image domain, image that makes you feel calm. So you see, like, it's very detailed. We start from the prompt, we generate with Gemini a standard image, and then with our CubeDiff approach, we get a panorama. And then a completely different domain, which is more fantasy related, Alice in Wonderland. Again, we never used any Alice in Wonderland panoramic images to fine tune the model, but the model kind of picks up this nicely from images that probably it saw during pre-training, right? These are some other examples. Render environments. We also had fun, mostly due to the rebuttal process that we went through during our submission. There was a request from some reviewers, try out with also some paintings. And so we also had fun with some of the paintings that probably you all know. This is Starry Night from Vincent van Gogh. And you see that it kind of extrapolates nicely the stylistic properties of the painting, right? This is the Tower of Babel. Again, it's pretty interesting how the model kind of like extrapolates and nicely the style, but also interprets what should be, for example, in this case, around the Tower of Babel. In this case, it looks like some sort of like a small town with workers and maybe a market. And this is Nighthawks from Edward Hopper. Again, it's like this kind of like bar from a Northern American city of around the century ago. And the model extrapolates the streets around it. We also have a qualitative comparison, again, against some of the state-of-the-art approaches, and the quantitative results. In this case, I kind of skip through them because I feel like for generative models, it's always hard to compare or assess specifically with quantitative results. But if you're interested, these are all part of the paper. Great, so that was the first work I wanted to present on generative models. Now let's move on to capture, instead of generating 3D scenes, we want to capture and render 3D scenes, and I'm going to talk a little bit about novel view synthesis. So with novel view synthesis, we now achieved like an unprecedented level of details when navigating and exploring environments. In particular, this is ZipNerf. The problem with ZipNerf is that it kind of requires 8 powerful GPUs to render at 0.25 frames per second, right? And so one of the very important characteristics when trying to use this type of technology for augmented and mixed reality applications is actually to make this much faster, also on mobile devices. And so what we proposed and presented this year at 3DV is a method called RADSplat that tries to take the best out of the two worlds, Gaussian splatting and neural regions fields. In particular, it tries to, let's say, increase the speed of NeRF rendering so to match and surpass that of 3D Gaussian splatting while keeping the same level of accuracy of neural regions fields. How do we do this? The idea is to use NeRF as a supervisory signal for 3D Gaussian splatting. And so the first thing that we do is to train our, let's say, teacher model, which is a NeRF model, and then you can pick the one that you want. We, for example, here show that we use ZipNerf just because it's a very nice model. It's also particularly slow, right? You can also train faster models if you want. And then the idea is that you initialize your 3D points for the Gaussian splatting optimization using the density of your radiance field MLP, right? So you go and probe your radiance field MLP for the density that's then turned into depth values, which is then turned into 3D coordinates for the 3D Gaussian splatting optimization. During Gaussian splatting optimization, what you actually run is standard optimization with the difference that instead of taking the input images, you actually use the images rendered from that viewpoint from your NeRF model. And the idea is that you can increase notably the accuracy. If you see, for example, the difference in terms of photometric conditions, left is input images, right is the NeRF images, you can see that you get much better photometric condition, especially when it comes to undersaturated or oversaturated conditions of your scene. And so what we demonstrated is that at the end of the 3D Gaussian splatting optimization process, by using the images rendered from your NeRF model, you can get much better quality embedded in your Gaussians. This is to practically make sure that the 3D Gaussians, they kind of have the same quality as the NeRF model that you use as supervisory signal. You still need to improve the quality and the speed of 3D Gaussians as well. And for this, we actually propose this ray contribution-based pruning. The idea is to check for each Gaussian about the contribution for each of the input training images. So you take your input image, and then for each ray, you go and check whether a Gaussian contributes to at least one image in your training set. If that is not the case, then you can safely discard this Gaussian. Now, you might think that there should be not many Gaussians during the optimization process that end up contributing not even to a frame, right? But this is not the case. We were actually also a little bit surprised when we found out that for some of these benchmark data sets that we used, only as little as 10% of the Gaussians that are generated during the optimization process, they actually end up having a significant contribution even to a single ray. So there's really a lot of Gaussians that can be safely eliminated. This is a summary of the results. We practically get similar, if not faster, twice as fast than vanilla 3D GS speed, rendering speed, but with a significant increase in the accuracy measured by SSIM or PSNR. And against instead NeRF, we get similar quality to ZipNerf, while we get 3 order of magnitude faster speed. We also get roughly 1 order of magnitude memory footprint smaller with respect to NeRF and 3D GS. So this is a pretty nice tool that we can use in order to build up our pipeline for both indoor and outdoor scenes. But since we're also talking here about urban environments, I wanted to show you another big limitation that happens when we move towards outdoor scenes, right? So even if you use RADSplat or this type of approaches that try to filter out Gaussians in a smart way while preserving the accuracy, Outdoor environments still pose large challenges also to this type of methods. This is what happens, for example, in a large-scale environment, right? So what we are highlighting here is the number of Gaussians that contribute to each pixel, rendered pixel. And you can see that the further away that you go, the number of Gaussians the more it kind of explodes, right? And so at the same time, you don't really need that many Gaussians to render a high-quality pixel, even if the part of the scene is particularly far away. And so if you want to, let's say, look at this plot, right, where we have the number of visible Gaussians and the number of pixels, we practically want to kind of like cut the tail of this distribution, which means increasing the frame per second, so the speed, without sacrificing the rendering accuracy. We want to keep the PSNR kind of the same. So if you look at the other representation, so where we put, let's say, speed versus rendering accuracy, you kind of want to get on the top right corner, which is what our method managed to achieve. So it's practically getting a Pareto on this kind of like trade-off. The starting point is, here is the so-called level of details technique. For those who've been either playing video games or working with computer graphics, you are probably very familiar with this approach. It's an old technique. I found out that it was actually something that dated back to 1976, actually quite a long time ago. It's been used in gaming a lot. And the idea is really that you have different versions, different resolutions of your 3D asset. It could be an object, it could be a scene. And then you can use the lower resolution for things that are far away. And then you tend to increase the resolution the closer you move, the closer you go towards the 3D asset, right? So this is really the very simple use of this kind of like level of details concept. So this is a very powerful idea for outdoor Gaussian splatting and outdoor null view synthesis. We're not the first one that looked into this. There's actually three methods, actually more, let's say three methods are actually summarized here. But let's say most of the state of the art is still limited in the fact that they still need to kind of like select the level of details and the Gaussians that need to be rendered for each new frame. And so this kind of represents a bottleneck for both time and memory when rendering, especially on mobile devices. And so we try to overcome this limitation. And this is kind of like the basic idea behind Lodge. We subdivide it into multiple levels. And so we have many fine-grained Gaussians for level 0. That kind of represents up to a certain portion of the scene. And then from a certain distance further, we get another set of, let's say, larger and coarser Gaussians, and so on and so forth for the new additional levels. Now, as you can see from this representation, one very important characteristic is how to pick the depth. So practically, the depth is really this kind of like discrete set of levels that kind of like, if not picked accurately, will provide a lot of distortions in the final representation. Okay, so what do? We practically select a certain number of levels. We select the depth, so the width of each of these levels. And then to build these lower detail representations, we apply this smoothing 3D filter. It's an idea that was proposed within MIPS splatting that kind of, let's say, smoothens out and increases the size of the Gaussians. And then we also remove redundant Gaussians. In particular, we use the same filter, the same idea that I presented before in RadSplat to get rid of Gaussians that do not contribute to any ray. How to determine the depth thresholds? To simplify the idea, we practically want to minimize the time to rasterize the union of the Gaussians, so all the Gaussians that belongs to all the level within a certain 16 times 16 tile. So you take a small tiny tile in your image, and then you map out the time that it takes for every set of depth, so for every set of sizes of your levels, to rasterize this. And as you can see, for example, in this case, we take 2 depth levels, so 3 level of details, and as you can see, there's practically like a global minimum that we can pick for a certain number of pairs, D1 and D2, that minimizes this rasterization time. And interestingly, this is, let's say, every parameter that you take that kind of ends up in this kind of like global minimum will provide you like a minimum time for rasterization without sacrificing the details of your rendering. Now, we still need to load all the Gaussians in memory and continuously recompute the active Gaussians. So how to actually overcome this limitation, this is kind of like the starting point of the work, right? And so for this, the idea is to build different chunks. So we cluster training cameras together. And then for each chunk, we compute the level details. This is something that you can pre-compute offline. So all the active Gaussians across all the levels for each chunk can be pre-computed. And then the idea will be that once you move from one chunk to another, you can just swap the active Gaussians from one chunk, from the active chunk to the chunk that's becoming active next. Now, an important thing is also to not rely just on the active Gaussians associated to one chunk. And so for this, we actually select two closest chunks, and then we pre-compute the active Gaussians for both of the chunks. In order to avoid additional visual artifacts, we apply a specific procedure which is called opacity blending that kind of blends together the Gaussians from the two active chunks. So because of this approach, we don't need to recompute the list or dynamically select the Gaussians. We have everything pre-computed. We just need to quickly swap the active Gaussians from one chunk to the other. This really speeds up the rendering at test time. Again, just to mention very briefly about this idea of the opacity blending, the idea is that if you have two chunks and you don't mix together the Gaussians, then at some point you're going to see, once you switch from one chunk to the other, in order to blend things together, we act on the opacity of each Gaussian. So practically, we found a formula that changes the opacity of each Gaussian so that it gets, let's say, more opaque the more you get closer to the chunk, and more transparent the more you're further away. Let's see if the internet connection will help us now. Yeah, it's not really too bad, although it's a small detail. So practically, if you see here this card, that's when you move from one chunk to another. So you see this kind of like artifact. And once you use instead this opacity blending, it becomes way smoother. So you can see now that you can't really notice any artifact anymore once you switch from one chunk to the other, because you kind of blend their opacity very gradually. I just wanted to show you some of the results, starting from this map that kind of showcases the active Gaussians per pixel. Again, if internet helps us. So you see that with the full representation, you have all these active Gaussians far away, and you get like 66 frames per second, but you can get 258 with this LOD-based approach that we presented. We tried and tested on two data sets, in particular the ZipNerf data set and the hierarchical 3D-GS data set. These are the results from the hierarchical 3D-GS data sets, in particular from two scenes, small city and campus. The TLDR is that we can get significantly, say, faster rendering, also with respect to other LOD-based approaches, while getting an accuracy that's on par, if not better, than the other methods. We have a bunch of other results. This is, for example, a test that we've done specifically on on-device rendering. So we also tested directly on mobile phones and mobile devices like MacBooks and iPhones. And again, we got mostly the fastest rendering results on mobile devices with respect to the other approaches. These are some qualitative results. I mean, this is again ZipNerf, mostly to show that we don't really see a notable difference with respect to ZipNerf, while being much, much faster, of course. And other comparison against, for example, Oct3GS, which is one of these LOD-based approaches I introduced initially. So you see it's roughly twice as fast. This is from the ZipNerf dataset and against H3D-GS, another LOD-based approach. And this is also another scene from ZipNerf outdoor, and the comparison is against a vanilla 3D-GS approach. I'm going to conclude Lodge, and I'm going to also conclude my talk with this. So we proposed a method that kind of provides this like a simple but very effective approach to do outdoor splatting by leveraging this LOD representation and by, let's say, smartly using together, let's say, clustering camera poses into chunks and to blend them together across the trajectory that we expect the motion to take over. Then we can also have this kind of like seamless transition from one chunk to another that increases the quality overall of the splatting. Now, this all relies on the idea that we have the possibility to quickly swap active Gaussians whenever a new chunk, let's say, becomes active, right? Which is something that's actually quite doable on even on mobile phones or mobile computers. It might be limited, for example, by bandwidth connection whenever we try to apply this, for example, for streaming approaches, when we want to stream a high quality content on a mobile phone from a server. And so the idea of using particular effective compression protocols or different approaches that are more designed for this type of streaming approaches is an interesting future work that we want to now start exploring. That's it. Thank you for your attention, and maybe we have a couple of minutes for questions.
I had a question about the large figure that you showed. You showed a lot of examples in which the camera was moving and the scene was static. What happens, or what is your intuition if it's the opposite? If we have a static camera and a lot of dynamic objects in the scene?
Yeah, that's a good question. So this approach is mostly designed to, let's say, have a static reconstruction of a scene and have the possibility to then explore the scene within this type of application that I showed you before, right? For example, imagine that instead of a restaurant, you want to start exploring like a street of a city. Typically, when you have dynamic objects in this type of reconstructions, you need to filter them out, right? Because you're not really able to handle dynamic components of the scene. Extending this type of representation to dynamic object, which means you have also like a 3D representation for dynamic objects in the scene, is a very, very interesting direction. It's not something compatible with the current representations that we have. And it's a very open, let's say, aspect in overview synthesis.
So you just mainly show qualitative results here, and I want to ask you, maybe in the paper you also have quantitative results, but for you, when you're looking at if it's working good or not, are you mainly looking at examples or numbers?
Which work are you talking about?
I only catch the last part. Sorry, specifically you were showing that you are faster than other methods, and you are also having blending this thing leads to less glitches in the video, and especially there, I was thinking metrics will not capture that kind of thing.
Right. Yes, I actually have a ablation slide if you want to see it, or maybe we can also skip it. And I mean, it's probably over here, hidden somewhere. And so more details are, of course, available in the paper. Let's say, picking the right set of levels, the right depth for each level is something that, let's say, it's practically hyperparameter tuning, right? And so again, we did some studies about how to minimize the time, rasterization time, in order to pick the right parameters. We do show ablation studies. Very frequently, there's not like a large difference. The opacity blending, I think, is not something that you can really measure quantitatively, right? The improvements that you get, but it is something that, let's say, really catches the eye. When you see certain videos, you immediately notice when you have this kind of like switch from one, let's say, LOD to another, simply because it's something that, let's say, we seem to be particularly very good at picking that up. Yes. And so I think for making this also, with the idea of bringing this actually to real products, it's also important to correct this beyond the fact that this is, let's say, measured by quantitative results or not.
Makes sense.
Yeah.
Thank you.
Yeah.
One more time.
Yeah.
And please bring that question back up in the discussion session. I think the
So good? Perfect. Okay, we want to do urban scene modeling. And the question is really how we now can utilize machine learning-based approaches to actually do an inductive and a data-driven modeling of the world. So when we're talking about machine learning-based approaches, we're typically talking about inductive approaches that take a bunch of data, be it images or whatever that is there on the input side, taking some machine learning method, and ideally I just took this quote here from workshop website, come up with a high level, ideally parametric 3D model of the world that we then have inductively gathered from all of that data. That sounds all nice, but the question still remains like what quality this final representation there actually has. And for that, I've briefly contrasted for you this empirical approach that we're here following against deductive, really reasoning approaches. And if you look at what we are actually getting out in such an inductive modeling, data-driven modeling approach, the things that we're actually fitting at the data are not first order principles, no first order physics models and so on, because it's a bunch of basis function that you're fitting. The origin, like the motivation of these functions that you're fitting there, is pretty much a design choice. It's not irreducible or founded on some kind of theory. It's not necessary to go for these principles there, but it's basically a convenience argument. And lastly, and that follows out of all of that, what you're getting is something which is only from a statistical point of view having a certain meaning, but there's no clear physical meaning to that. With that, I want to transition to generative models to actually address that task. With generative models, now we're turning things around, right? We're building a model so that we can draw samples from this model, draw samples that ideally reflect the underlying data distribution, reproduce that, and which allow us with that, and that's the benefit of these generative models, they provide us with an estimate of the uncertainty of the world out there. They allow us to do some counterfactual reasoning, kind of probe the world that's out there. But whatever it is, this inductive approach there to tackling the problem of urban scene modeling in that particular case, it requires data and models of a certain quality and a certain size. Let me say that again, because it is data-driven. The data needs to be of a certain quality, evidently, but in particular also of a certain size. And that goes hand in hand with the models becoming ever larger. Models becoming ever larger, when we're talking about generative modeling, we've over the last 5 years seen an increase by a factor of 15,000-fold increase of model size. Here it's judged that we are talking about roughly like 4x per year. Sounds okay, but if you contrast this against what we have in supply in terms of compute supply, we see an issue, right? Because the supply of compute is growing pretty much at like 1.3x as opposed to the model size there. And whenever you have such a discrepancy, I guess an alarm bell should start to ring. You see that the model size runs away from the compute. And this gap here means it's starting to cost you something. The cost of foundation models, especially frontier model, has been significantly increasing over the years. We're talking about like 2.5x per year. And the solution to all of that was just throwing more money at this game, meaning like the models that eventually allow us this inductive reasoning about the 3D world as we want to do it here. We've just been buying ourselves time because the models just get ever more expensive. On this exponential curve, we've been moving towards the right by just throwing in more money. Last time I looked, our money that we're typically gaining is not exponentially growing with time. And with that, you're set up for a problem. There's like projections that if things continue that way, we will very soon see foundation models that cost $1 billion for training. But what it definitely takes is with the models getting larger, the training data sets also need to get larger. And finding that much more uncorrelated training data is definitely an issue, and at least it's going to have a certain price tag. And lastly, buying ourselves out. Well, if you look at what's happening on the bond market quite recently, things starting to flip there. It seems like there's a bit of an issue coming ahead. Speaking about issues, what we've essentially been doing is, if you compare this to where the shipping industry, transatlantic shipping business was 100 years ago, we've essentially been building ever bigger and bigger ships, right? Essentially making the models that we have, scaling them up and making them larger and larger, which is somewhat consistent to the bitter lesson of Rich Sutton, who said that breakthroughs typically these days come about by simply scaling up computation, making the models larger. And that's kind of what we've been doing for a long time, right? But if you look back at the shipping business, what was the end of the transatlantic shipping business? That wasn't an iceberg, that wasn't a war, it was that, right? The jet engine in that case. Essentially a new technological revolution which superseded everything that we've been doing in the shipping business. With that, I'd like to propose to you something that I call here bitter lesson 2.0. Saying or observing that what Rich Sutton said is right, but only under certain assumptions. And the assumption in that case being that the commodities that all of this scaling are based on, that these commodities are scalable and you can scale them cheaply. But as we've seen, that's not necessarily true with the model sizes that we're presently talking about. And with that comes the question, what's the way out? And when you look at the GPUs that you're having these days, it's not that there are electron tubes on steroids, right? I mean, we've had paradigm shifts in between, from relays over to electron tubes to transistors to integrated circuits and so on. Much like we're not having bigger and bigger ships, but we've made the transition over to the jet engine. And these paradigm shifts, although we first see an exponential growth and then we see a flattening of the curve, the paradigm shift essentially resets this curve and gets us starting again, and it continues that way. And we've been doing that in the machine learning community as well, right? And in machine learning, we've seen transitions from good old kernel methods over to deep learning, from MLPs over to CNNs. We've had transformers or latent diffusion models and the like. Now, the second part of this bitter lesson 2.0, for that I'd like to quote somebody else, and that's Vladimir Wapnick, who said that whenever you have a problem of interest that you want to solve, you need to make sure that the tasks that you're solving on the way towards this final problem are not more complex. I'm bending it a bit here, but I guess that's what it means for our matters here, more complex than your ultimate goal. Let me say that again. For whatever task you're going for, make sure that the intermediate tasks are not more complicated. Well, how do we get these two things there together? I added here, well, make sure that the intermediate tasks are not more complex unless the bitter lesson that we've seen above applies, meaning for these intermediate problems, although they're more complex, for instance, learning a foundation model, you have much better scalable data available. And let's say you're up for urban scene modeling. And in that case, you have sort of limited data at your disposal. But if you have a foundation model where you have significantly more data there, and I guess that's what I've been asked to talk about today a bit, you can utilize that as an inductive bias to ramp up the model that you're having. So again, intermediate problems can actually be more complicated, but only if you have significantly better scaling there of their data, whatever commodities that you're going for. And that's been true when it comes down to pre-training foundation models. That's not necessarily true, for instance, when we're talking about 3D. Because last time I looked, YouTube is growing at a massive scale when we're talking about videos. 3D commonly available data is probably not growing at this rate. I have other keynotes talking a bit more on that relationship here, but that's just something that also for the panel discussion later on, a point that I'd like to make, and an observation that we should dive in a little bit deeper. And that motivates actually going for other foundation models and pre-training where we have better scalable commodities. And lastly, the question remains, will we eventually attain true intelligence by mere scaling? And there's evidence on either side. There's been evidence that large language models can actually, or that you observe actually emergence and emergent properties in large language models. But it's also, and I guess that's at the core of this workshop, when you're interested really in a physical grounded, physical based model, there's a huge gap between this empirical, this inductive approach that I sketched at the beginning, that machine learning approaches typically take, and the physical first order principle based representation that you would love to have if you want to have something which is fully interpretable. So there's the gap. And the last bit to this bitter lesson 2.0 is this question here. Will true intelligence really emerge by scaling, or don't we actually need, like we've seen all over the place in biology and evolution, finite resources? Because it turns out that, well, I mean, last time I checked, our brains haven't grown over the last 200,000 years. And way back then, we were dealing with this, sticks and stones. I mean, this thing was called Stone Age for a reason, right? And now with the same cortical capacity, we're operating very complicated machines. It turns out that out there in the real world, in evolution and so on, this finite resources, as tricky as we typically find them, were a key motivation for us to actually develop intelligence. And we're doing the same thing in machine learning as well, right? We utilize bottleneck architecture, something that forces us to go for abstraction, and only that way we eventually see generalization happening. When we develop stable diffusion, as you know, like this Latin representation is kind of, again, another realization of what you see there. So, two observations. 2D image data, video data, I see being more prevalent than especially curated 3D urban data. So the question is really, how can we utilize already trained foundation models where a lot of money went in and utilize them as inductive bias for the task that we're looking at in this workshop? And secondly, if we already have these models that have been trained for that much money, how can we, I mean, I assume not everybody here has infinite resources. How can we get the efficiency that we need to also scale up these approaches to lots of people using them, and to add the control that you need if you really want to have a model that is interpretable and has some grounding? And for that, we need efficient, controllable approaches to repurpose, so far for the title of this talk, or translate these models that have already been trained to novel domains and novel tasks. So let's see how that works out. Let's say you have a generative model here, which you have trained on a lot of data and from which you can reproduce your data distribution as it's generative. I'll very briefly in this talk now show a few examples of what you can actually be doing with these models. For one, for instance, repurpose them to different modalities. These models have been trained on just generating RGB flat images. And I'll show you some recent work of ours where we've been taking these models to then draw samples from the third dimension to essentially estimate depth of scenes. We've been working on, or have a paper at this conference where we take the image models and have them reason about the textual domain. And lastly, although these models have been built to generate images, can we utilize them for also extracting representations that allow us to establish relationships between scenes, doing the final analysis that we're really interested in. I will also briefly, time permitting, talk a little bit about recent work in the direction of Gaussian splatting and how we can make that more efficient as well. So, repurposing text to image models. The first thing that comes probably to everybody's mind are adapter approaches. Adapter approaches where you take this model that has already been trained, and it's potentially a conditional model where you say like, hey, give me a high quality detailed scene of whatever you want there. And as an adapter approach, you can fix certain aspects of the scene so that you can change the conditioning in these aspects that you want to fix, over which you want to have control. They stay put, as you see down here. Now, that sounds great, right? And great promise of an adapter to give you additional control like we've seen beforehand. But there is an invisible divide there in terms of the different control signals that you can inject into this adapter. It turns out that there's not one adapter approach to rule them all. It turns out that there are certain control signals, especially when you want to control the spatial structure, a detailed and fine-grained pixel level sort of signal there, that you need particular adapters for that. And when you want to control the overall gist of the scene, the overall style of things and so on, you need different adapters for that. There is a divide between these, and there's not one adapter to tackle both problems. Now, for that reason, we're proposing an approach which combines both of these. Vertical axis here is the local, the fine-grained spatial structure. On the horizontal axis, you see the overall context of the scene. And our approach, as you see here, top right, gives you essentially control over both. At the same time, this approach is efficient. It's very flexible, and you can, because it's model agnostic, slap it onto whatever, not just stable diffusion, on top of whatever generative model that you actually want. Lastly, it's also in terms of the size that you see here, significantly smaller in terms of parameter, making it very effective to actually train this model. Now, I mentioned already low-rank adaptations, and that's the direction that I'm going. Low-rank adaptations, as most of you probably know, you take a generative model, you create a bypass to this model, an encoder-decoder architecture, which, however, you typically need to train for the particular condition signal that you have, for the particular control that you want to inject into this generative approach. Problem with that is, if you want to have a different conditioning, you need to retrain this, and you need to retrain, and so on. Now, our idea here was to utilize the low-rank adaptation for good. If this is low rank and with that low dimensional in representation, why always retrain the encoder-decoder architecture? We are here proposing an affine transformation right in there, green, this green box, right in the low rank, in this low dimensional feature space. And this affine transformation, we're now controlling by means of two neural networks, one taking care of the overall gist of the scene and the other of the local detail. And with that, you actually get a zero-shot conditioning there. You can on the fly alter the conditioning input here, and moreover, it can be different modalities that you condition actually on without having to retrain the remainder of your adapter. And with that, you get an adapter which you can feed with structure, with style. You can create this image, or you can alter the style conditioning there, or you can get something in between, between these two. And lastly, it works for all kinds of conditioning signals, be it style, depth, edge maps, postures, or whatever you want. That approach here, I'm just showing this because for us, it turned out to be a very effective workhorse. We utilized it also for video, for 3D, you name it, in our work here because of this zero-shot conditioning that we're having and not needing to retrain it whenever we have new modalities come in. So can only recommend it because we're using it ourselves very actively. Second direction is that we're not using generative models just for the purpose of generation, but that they have been already widely used for the purpose of representing the world. Understand this is exactly what we're looking at here. You want to take a lot of data, learn a representation of the world, to establish relationships between different scenes and learn about their details and so on. when we had proposed Stable Diffusion very quickly after, people observed that you can take arbitrary layers out of Stable Diffusion or whatever generative model you have there, and they're not just good for rendering scenes, but they're also good as a feature representation of the scene. So you can take local details there and you get a feature representation, you take another image, and you can relate the features that you extracted from one image with the other, and essentially get semantic features, pretty high up, high level representation of that scene. And if you do a comparison against other feature representations, it turns out that these generative emergent features, which are trained in a self-supervised manner, not as a fully supervised or handcrafted feature, but in a self-supervised manner, that they outperform other features. But in particular, they're complementary. So if you combine them with something like Dino, you get a significant extra performance boost. And a representation of the scene of our world that you can utilize then on a semantic level to relate different scenes against another. Sounds great, right? But there are issues with these emergent generative features. For that, I'm just using a video here and extract the feature over and over again. And as you can see, there's quite a bit of flickering going on. On the left-hand side, I show some examples. If you establish correspondences between a bunch of images, as long as they're semantically close, it's kind of okay. But the moment that you have something which is a bit further away, you see at the bottom that you get a different correspondence. Why is that the case? Problem one and problem two. Problem one, if we are utilizing a diffusion process to actually extract features from this world, how does that work? Well, you take an image, as you see there, top left. You take this image here and you add noise. This noise gives you a noisy image, which you're seeing here. And then you have the diffusion model to eventually get you as close as possible to the original scene. And you take a feature from that. The problem, however, is that the best performing feature is typically not the feature at zero noise, but it actually significantly deviates from that. That means the best performing feature is a feature where I actually have a crappy, noisy input. And with that, signal lost. Doesn't sound too good, right? Problem two, there is not one single best noise level for all the tasks at hand, but the noise level differs depending on what you actually want to do, which task you want to solve, and also like what type of scene you're looking at. How do we fix these two problems? Well, let's start with diffusion feature extraction. So again, our image, noise added, here's the diffusion model, and out come some noisy diffusion features. Features that are useful, but where we have not a single feature, different time points, and evidently no noise-free features, but significant noise in there. The naive solution would be you simply kick out the noise at the beginning, then you have no noisy features. But again, I mean, there is no noise in there, but the features in that case aren't useful. Why? Because the diffusion process needs, as we've seen beforehand, the noise. With zero noise, it's not working as well. You need a significant amount of noise to actually get really the diffusion features to the level where you actually would want them to have. But there's a very critical observation that we made in this process. If you have the diffusion process and you look at the features that come out, you see that the features are actually the features of your noise-free image, here in green, features of the noise-free image with X0, plus, so an addition, an additive process of the features from the noise process. And that got us wondering, like, isn't there a way to actually eliminate just the additive noise component here to retain the clean features? And for that, we propose to just copy the model that we have at the top and keep that here, or adjust this model here by minimizing the loss between the final noisy features that we have, or the performance that we attain by means of these features. And these features here at the bottom, which have this feature extractor here, sees only the clean image, no noise being added. Minimize the loss between these two. The benefit in that case is these features here at the bottom see clean, noise-free input. So these are clean features, and you minimize here the gap between those and the useful features at the top. Problem still is that you have the T parameter going in here, so you're not having a single feature, but multiple features depending on what your time point actually is. For that, we injected here a projection layer that now takes the time point, but the network itself has no time point anymore. We train it on all different noise levels, essentially, this projection layer, to get the ensemble of all of these different noise degradations in there and essentially pick the best of all of these together. And with that, you get a feature extractor, which is noise-free. It sees the clean image here. The feature extractor itself has no free T parameter that you need to adjust. During training, it has seen all the different levels, and it gives you with that significantly more powerful features. Here, as example, left, the original diffusion features. On the right, the significantly cleaner and significantly, over time, more consistent features extracted by CleanDiff. The approach has been trained just 30 minutes on a single A100. The correspondences that you get are significantly better. See on the right-hand side, semantic correspondences are matching, and it works with all kind of diffusion feature methods, left-hand side, and it works on all kind of backbones, not just stable diffusion, but whatever other approach that you're going for, and achieves a significant gain there. If you're interested to learn more on that, it's going to be an oral this Friday in the morning session, and the poster presentation evidently then right afterwards. So with that, I want to transition to this question of how we can actually utilize static 2D image models as an inductive bias to learn more about our three-dimensional world. And for that, learning 3D world as a proxy, we here learn, because we've trained on flat images, we try to utilize a model that's only been trained on flat images and reason about the depth of the scene. So monocular depth estimation, but we want to do this fast using a generative approach. And in that case, I'm going to show you competitive state-of-the-art performance. Depth estimation so far, I know that latest and greatest, depth anything, and V2 and so on, typically like discriminative approaches. We're proposing here a generative approach because this, in addition to that, gives you also estimates of the uncertainty of the scene. You see bottom right here, gives you confidence estimates by essentially being able to sample from this stochastic ensemble there. So not just a single estimate, but also the confidence estimates. Discriminative approaches are great, but they're typically somewhat coarse. That's another way where generative approaches have a benefit. After proposing stable diffusion, there were other approaches using that, like Marigold and so on, using diffusion models to actually learn depth. But they typically start with a random noise and then turn that into, by means of denoising, into a depth estimate of the scene. So you see the process here, starting from pure noise and moving over to a depth estimate of the scene. In this work here, we're proposing utilizing flow matching. Flow matching has significantly more straightened trajectories. And with that, you're not starting from pure noise, but just a noised version of the image. And I hope you can see that that makes the trajectory significantly shorter. Shorter trajectory means significantly faster inference, significantly faster depth estimation at low NFVs, in that case, number of function estimations, evaluations. So more efficient inference. And here you see comparisons against Marigold, where also in terms of performance at lower NFV is quite favorable. So let's now go to the core of our theme. We want to utilize a 2D trained image model to reason about the 3D world, be it urban scenes or whatever else that is. How can we do that? Well, let's take stable diffusion or whatever generative model you're having there. You take an image, you pump it through its latent encoder, and you get the latent image representation. Great, and that's what stable diffusion is doing all along. If we now have, then we take the latent decoder of this 2D image model, has never seen depth, yeah? but it turns out this is fairly versatile. If I had a latent encoding of depth, I could just pump it through the latent decoder of Stable Diffusion and get a representation of the depth map. Problem is, I need to fill this gap in between, right? I need to somehow turn the latent image representation into a latent depth representation. Now, what we're utilizing for that are just a few synthetic images. In contrast to all of these discriminatively trained models, this is here trained solely on pairs of synthetic scenes with their depth estimate. For this image, I therefore have a single depth map. I pump this depth map again through my latent encoder, and what I get is a latent depth map, which corresponds exactly to the one that my decoder needs to decode it back into an image. That part is straightforward. Now, the problem is we need to fill this gap between the latent image encoding and latent depth map that we need to learn. And the issue with that is it's ill-posed. There are two directions here where it's tricky. First, several images can have the same depth map. Yeah, change of appearance. If I wear a different shirt, that does not change my body posture and form. That is clear. That we can solve fairly easily. I just augment my image there. That does not change the depth map that I can get going. The opposite direction is significantly more tricky. I can have translucent objects, reflections, and so on. And in that case, the same image actually corresponds to several other plausible depth maps. This was many to one. The more tricky problem is one to many. How do I get training samples for one to many if I just have pairs of image and depth on my synthetic data? There is no straightforward way to get that unless I had a depth model already trained. Our solution to that is just taking the first step, this many to one, several times, and eventually you will find a blue and a red image, which are in their augmentation so close that they're almost interchangeable, but then these purple images there in the middle, they come from different images, therefore they have different depth maps, but their augmentations are close, so you get twice the same purple point, but corresponding to different depth maps. One to many. Many to one to many. Now we're done. Now we can utilize flow matching to bridge the gap between the 2D image model, trained solely Stable Diffusion, only trained on images, fixed, frozen, not using that anymore, and the depth representation, translating image latents into depth latents. How do we do that? Well, you provide it as conditioning, the latent image map, and in addition to that, you're adding noise on that and utilizing that for the denoising process. Essentially add noise to the latent image representation, denoise that as we typically do, but now with target, not a noise-free latent image representation, but the noise-free latent depth estimation that you have on your training data. Yeah, so the flow matching approach does the transition from latent image to depth. It performs favorably well in terms of quantitative analysis. The approach, horizontal axis is time. You see it significantly faster, especially in low NFE regimen than the Marigold and other diffusion model-based approaches because of it being rectified flow. In terms of discriminative approaches, omni data and so on, favorable in terms of delta 1 accuracy and size of disk, because it is such a compact approach, only trained on synthetic data, 63,000 instead of millions of data points for omni data. So several orders of magnitude, almost 3 orders of magnitude smaller there. And with that, the foundation model essentially gives you the transition, this repurposing, this translation from 2D images to 3D. It's a generative approach, predicts also confidence maps. It's fast, 10 FPS, accurate and detailed. And lastly, you get fairly easy training there on only synthetic training samples. And with that, let me transition to the last fairly recent work that we've been doing, and that is on utilizing Gaussian or improving on Gaussian splatting, making it faster, high quality, and doing this all by an embarrassingly simple approach, which essentially affects the initialization. For that, let's briefly look at some issues that 3D Gaussian splatting, as great as it is, but typically has. Gaussian splatting. You start with structure from motion as an initialization, giving you some Gaussians. You do a projection, run this through a differential rasterizer and project it onto the image plane. You compare it against your ground truth image, see an arrow backprop through the differential rasterizer in your projection, and then you alter the Gaussians that you have. And you go back and forth, do the optimization, or replace the Gaussians at different places. Until you notice that things suck, you cannot move any forward because you're having too little Gaussians, and you need to essentially inject additional Gaussians. You need to do a further densification. And that is where things get tricky. We have inbuilt this iterative densification, which first off sounds nice, yeah, based on some L1, SM, whatever losses. You look at the Gaussians where they're actually placed in the scene, and then you clone, split them to actually add additional ones. And you see it here in high frequency parts, especially in the scene, that you never have sufficient number of Gaussians. Now, what's the underlying problem there? The underlying problem is that after you initialize, you have an image like the one that you see bottom left here, each pixel being somewhat different. And nevertheless, in the initialization, you put one splat over all of these pixels. Different pixels now drag on the same Gaussian. And then the Gaussian splatting approach does a lot of optimization, but there is no way to actually break this tie. So you're essentially wasting a lot of iterations because you're simply having incorrect number and incorrectly initialized Gaussian splats. In contrast to that, we're proposing what you see here on the right, a significantly better initialization for the Gaussian splats, close to the final solution, essentially. So a spot-on initialization, which you want, which if you want so, which essentially eliminates densification. We played around with different approaches. It turns out there's great dense matching and triangulation approaches like Roma, but you can also utilize the other two that you see here. You should only not go for like optical flow, like Raft and so on. That's built for different purposes, but the others give you almost comparable approaches. And with that, we get this 3D localization close to where it eventually needs to go. We can take these match points and the camera rays to then initialize the Gaussian splats. We can take as color, simply an averaging over the matched points color. And with that, you get Gaussians initialized near the final location where they actually need to go. The Gaussians don't need to travel further. Yeah, in blue, you see the travel distance that you typically get from 3D Gaussian splatting. Orange, you see where we need to go, or here. X-axis is the distance that you typically travel. Orange, you see like several orders of magnitude less traveling happening. And that actually equates or means that we get the same quality of reconstruction significantly faster. Bottom right, our approach, and you see in the middle, standard structure from motion initialization for Gaussian splats. And you see that we have significantly more structure there. You can measure that. X-axis is time. Horizontal, the vertical axis here is the performance in terms of LPIP score. And you see our orange curve is typically south, meaning significantly better in performance, or left, which means significantly faster than all the baseline approaches. And what you can see here also in the demo is this is still the initialization phase. Right is our approach here. And you see how it is significantly faster. We're talking here about like almost like half the time and still having significantly better quality in terms of results. Go to our Hugging Face page. There's a demo. Can play out with your own data. Just inject it and create 3D reconstructions here. And again, like that's half the time. And you've seen on the left-hand side, projector is a bit wonky here on my screen. You can see significantly more details on the right. Significantly more details, especially in the high resolution cases. So let me wrap this part up. We eliminated the need for iterative densification by going for a direct triangulation of the dense 2D key points onto the 3D Gaussian splats that you're looking for. The Gaussians being initialized close to where they actually need to go saves you a lot of travel distance there, reduces the number of necessary parameter updates, and with that improves convergence speeds, improves the reconstruction fidelity that you get, and outperforms speed and outperforms quality optimized 3D Gaussian splat approaches. 6 times fewer optimization, significantly fewer Gaussian splats needed. So let me wrap up. First off, when we want to utilize generative models as an inductive approach to actually reason about 3D world, 3D scenes out there, be it urban or whatever it is, I think we first need to figure out where we stand on this bitter lesson 2.0, whether we're closer in the Vapnik world there or closer to Rich Sutton's approach. In the latter of the two, just scaling it up and it's going to solve all your problems. In the other case, make sure that you're not solving an intermediate problem, which is more complicated than the one that you need to go for. We've seen effective approaches for boosting the efficiency and the control of models that have already been trained in domains where you have significantly more data than in the 3D world. Conditional LoRa adapters here as an efficient, flexible approach, which is model agnostic to give you zero-shot control. Clean diff as an approach to give you clean features without having any noise in there. Depth FM as an approach, how you can recycle 2D image representations for the 3D world. And lastly, a very easy approach to eliminate the densification and with that speed up 3D Gaussian splatting. With that, I'd like to thank my wonderful team that made all of this work possible. And thank you for your attention. If you have any questions, I guess we have a lot of panel discussion and everything later on. Thank you.
Okay, thank
you.
Yes.
Okay, just
Yeah, just pull them out. We'll swap this back to. Thank you again. Really appreciate you jumping in.
Of course.
All right. We're gonna do it part of the.
Where? No.
Zoom, can you hear us? Zoom?
Now, yes.
Yay. So the organizers and the keynote speakers on the Zoom, if you can turn on your cameras, maybe, because we can see you right now. Yeah,
Can you actually like stream from the audience or something? Because it's pretty depressing to see black screen.
well, you can see me right now. Hi.
Yes.
But we maybe Jack or Rushan, whoever is connected to Zoom, can you put one? Yeah, just open the camera and point it to everyone that we have here. So yeah, another laptop is coming to show you everything. Okay. Yay, that's the room. That's half of the room. Cool.
Oh, now it's way better.
Do we have other speakers that are coming on Zoom? Okay.
It's pinging. Okay, cool. Welcome everyone to our interactive session. So this has been like a tradition to every year that we are trying to do, either in this workshop or other workshops that I or my colleagues organize. This is not a Q&A session. This is how we, all of us, not just you, us speakers, etc., without any any level of contribution to the workshop, how can we work all together in future? How can we shape the future of our research area, of our domain? Feel free to just talk as however you want. It's not just like a formal meeting that we have things as a structure, and I will try to moderate as much as possible. Okay, cool. So we also have for everyone here and on the Zoom, we also have this link. I can't show it right now, but it's actually bit.ly/USM3D panel. So if you don't want to speak here for some reason and send it anonymously, I'm also collecting questions from there, which we have one question there, but not others. So you can also use that. It's bit.ly USM3D panel. Okay, cool. So as an icebreaker question, as a I know you have questions. I know we all have questions. As an icebreaker question, maybe I will start with what Jack asked during the challenge presentation. He asked okay, we organize this workshop, we organize this competition, we release all of these data sets, we put so much prize money on it, etc. What else can we do to make it more attractive, to invite and sparkle more interest in our domain and in topics that we are trying to solve, right? And I know this is a question that is a little bit biased to get answers from this crowd, because if you are here, it means that you are interested. So why your friends are not interested is the question, I guess. So maybe I will start with the keynotes about how we can spark more maybe interdisciplinary collaborations in this domain, because there is so much that is going on, but maybe there's still some disconnect between different research areas. So what do you think about this? Does this move? Yeah. Nice. Cool.
All right, thank you. Okay, so perhaps one aspect, so I've been going to some conferences which are not computer vision, they exist, right? And so the urban world expands many fields outside of computer vision. Perhaps one way is to make this more aware to people that are not hardcore computer vision, so more interdisciplinary collaborations. Would be one way to expand interest if we want to focus urban. Otherwise, it becomes 3D reconstruction, 2D reconstruction, which is very mainstream, and then you're competing with 9,900 other people. So maybe bringing in more of other aspects of urban connection. Maybe it's traffic, maybe it's pollution. Yes, those applications, but they're important ones. That would be one suggestion.
I guess the applications are also what matters, like you mentioned interdisciplinary there. And we can here in the room talk a lot about how we can represent actually the world that's out there. But I guess it becomes truly interdisciplinary and reaches out to a lot of other communities if you talk about what you think can do with this representation, what it tells you about various other application areas. And in that case, more specific, I guess you'll reach out really to individual application areas and talk about individual tasks that you can solve there. But there's not one size fits all approach to that.
So just a counter question, and the question is, what is the unique challenge of urban data, and are we not seeing a trend towards more general models, so that a lot of the work that works on very specific data and specific domains, maybe I feel it gets de-emphasized, and a lot of people, rather than, let's say, working on urban reconstruction, we just want to work on general reconstruction. To say, I'll improve 3D Gaussian splatting, maybe I get 100 citations per year. I improve 3D Gaussian splatting for urban trees, and got 2 citations per year. So I feel like I see this trend of people working more on the general topics, and also the trend that these big models are just so powerful at solving the general problem that it often becomes hard to come up with a specific solution that is actually better than the general one. So I see these as challenges. I mean, I actually wanted to pose it as a question, if what others think about that.
So what do you guys think? Should we go more general or is it specific to?
Very appreciated the organization because I actually attended the last year and I'll present here this year again because I saw these topics every year. You guys pay the efforts to trying to make the community beneficial to the community and inspire the community. So one of my experience, sorry. So one of my comments here, because I'm mostly focused on application parts for what people can inspire from 3D reconstruction generation. So what kind of that downstream tasks. So for me, one of my questions here, that urban like reconstruction, does it also include any like most likely people will think about is natural and seeing very large scale, seeing, I mean, when I talk about large scale, which means urban size scales, instead of probably the smaller scales, seeing these kind of scenarios. I will say both of them was for a bunch of variety of applications like autonomous vehicle driving and these kind of different things, both AI things. So one of the things I want to talk about, as also Professor Daniel Aliaga mentioned, probably traffic, these kind of different people who interact, who are interested in 3D things. So I think this kind of downstream applications are also very, very important. Who utilize 3D things, 3D data, and also this kind of mappings.
So coming back to the point here on right hand side. I think the applications of create like a new problems, right? To formulate a new problem. And I think if we just apply the existing methods, the new problem doesn't work. That's why we can't overcome it. I mean, the issue of applying the standard method, say Gaussian splatting, and then we apply it on the whatever urban model. So I think we need to come up with a metric that really shows us that it's a different problem that we have here, the urban modeling.
Yeah, and just extending on that, you know, Gaussian splatting, all this stuff, we have novel view synthesis, we have general 3D reconstruction, but this generally gives us pretty unstructured representations. So do we think that structured reconstruction is enough of a different problem that it's still general and interesting to work on, but not too specific, whereas, you know, in application?
Well, first off, I wanted to follow up on your point, which is a very important one, right? We're talking about generative models, and me as a Gen AI guy, it was a miracle that computer vision was ever able to move into that particular field. But because for years we've basically been absorbed with discriminative tasks. Why? Because they're easy to benchmark, easy to evaluate, right? And then you have this 100-meter dash, 100-yard dash, and everybody does exactly the same thing. You can just count which one is better than which other approach. And moving in a generative world, which is notoriously tricky to evaluate, again, like, was a miracle, but I mean, it was good for us to have a fresh start, and everybody could try out something new and say, like, yeah, my approach works better than yours, right? And then we had weird metrics like SM and so on, and FID, and yeah, we're all stuck there that it's still a bit tricky to evaluate, regardless of everything that's been done there in the past. The moment that you move in application areas, downstream tasks, there is an entirely different story, right? But with that, I'm totally on your end there. When you propose a new novel task that goes together with novel data that you have there, and then typically should go together with novel benchmark data sets and novel metrics that you actually have there. And then all of these problems are off, right? But that goes back to this question like niche or not. Yes, in that case, you become a little bit more niche because you're focusing on this particular benchmark task, but so that you get something which at least on this task is good and easy to evaluate. You might utilize the site information that you have there, physical priors and whatever expert knowledge that you have for this task, which is not so good in the general scenario because this might be a bit more sort of applicable to whatever your task is. But there I see a lot of benefits. Yeah.
So yeah, thanks for all the talks and this nice workshop. I want to add one thing. I think this also brings us back to this waffling discussion maybe a little bit. So first I want to add waffling was wrong in many aspects of machine learning. And this is why we need a better statistical learning field right now, because this book doesn't work for any of the empirical data that we have right now. Second, I think him being wrong translates to this quote being wrong. So, well, we should not maybe solve more complex tasks, but we also understood that with each task comes more data. So it's a little bit of more information for the model at hand. And certain tasks, I think these were old, CVPR-based papers, certain tasks are actually reinforcing each other rather than making them bad. So the question is rather, how can we choose a subset of general tasks that are eventually informing, these applications that we try to solve, rather than trying to go really, just to solve this one urban task that I have, because let's be real, there is never a single task. Usually we want to solve many tasks at the same time, but which of these are informing one another, which of these are creating, let's say, synergy, and because with synergy comes, I would say emergence, and with emergence, you can start to solve more interesting things, and even the specific task better, simply because you are informed. Basically, you have more information in there rather than the task itself. And as such, I remain confused. I mean, we can continue this discussion, but I also have another question on your.
I think
so, yeah, exactly.
Yeah, I have actually some comment here is that probably weird for me as like I'm all my life I'm proponent of the benchmarks and challenges and Kaggle and everything, but maybe actually we should there was this Andrew Davidson quote that we should not go for table with bold numbers, we should go for a demo, which means that there is like new thing which didn't exist. And basically, like all the super popular stuff and like super impactful, and in our area, let's say Colmap, Gaussian splatting, stable diffusion, they not like cool because they are cool on the PSNR thing, but they enable things which normal people, not researchers, can do and can play. And there's like this Luma stuff and other things. So maybe actually the answer is what we can do is to enable people to use our work or like challenge to like, yeah, basically make demos or products or whatever you talk them, which would do new things as opposed to improving numbers, which are also is important, but maybe it's like there are too many benchmarks and too many competition. If you go to Kaggle or if you go things like every week there is a paper with new benchmark, and like every month there are many competition, and people just distracted to everything this. Maybe we should actually go into another direction.
I have a question regarding this workshop. We have two challenges. We have two data sets, which is a small data set. For instance, in building 3D, we train well on building 3D. If we test on another data set from another country, from South America, from China, the algorithm doesn't go well. So now we are trying to build a large model or foundation model, for 3D urban modeling, for 3D modeling. So my question is, how large is 3D, this data set should be? Now building 3D is 50,000 buildings. 50,000 buildings. I don't know the image space that the whole data set is 25,000.
I would add to that by merging in some prior comments. Maybe thinking about reconstructing buildings in the 1960s, thought of you see the building, you want to reconstruct the exterior shell, is rather old. So in the urban case, and maybe in other areas as well, it's a deeper thing. You want to know more than just the shell. You want to know what's underneath the cushion, what's behind the chair, what's behind the wall, right? There is see more than you can see type of aspect. So it's not just reconstruct the exterior surface, it's more than that. So I think, and that is of use in the urban world. If you talk with people, say, about heating and air conditioning, you tell them, I have my perfect geometry of the exterior of the building, they're like, big whoopee, I want to know the insulation factor, I want to know other features that are different than what's exactly visible. And you can repeat this argument for the interior, for building, for plants, for more than just the exterior geometry. So maybe the challenge should be obtaining more information than what you can see, more than just the old-fashioned building envelope and the exterior. That would be interesting. And there, I think, is where Gen AI has an advantage, because you cannot see the interior of the walls and inside the cushion of the chairs, right? So therefore you have to generate the answer based on some other knowledge you might have. I think that's an interesting area, and it is computer vision relevant.
I think if any of you were here last year, Noah sort of pitched this vision. Noah Snake pitched this vision very beautifully. I'd also say the you know, in terms of what Togo was saying, what Dimitro was saying is, you know, you're saying, okay, we need to enable some totally new capability, but what about the case where we're asking people to enable a new capability, but still, like, our challenge is pretty hard. People aren't like that close to solving it. So how do we make incremental progress when the quality isn't at this like, it's magic, this is obviously amazing stage, and we still need to kind of like keep climbing on something that we believe will work, but doesn't fully work yet.
Thank you for the workshop. So with respect to urban city modeling, I think there are two aspects. One is outdoors and other is indoors. And I think the pinnacle of outdoors urban city modeling would be if we can do like city planning using that. And I think we still have data sets that are describing roads and buildings, but we need to it to be more granular, like where are the schools, how are the sewer lines, how are the power grids, and maybe that would help this cross kind of involvement of other you know, parties as well. And yeah, I don't know if it's related to the reconstruction process, but I think there are other modalities of data sets that we can include along with the current data sets that can move us in the direction of like scene planning or city planning.
I don't want to be too often, but years ago, I was in a project which wasn't my project, but it helped, where they tried to make the interior of buildings from only seeing the exterior. So that's like definitely more than what you can see.
Right? There are like Wi-Fi signals and everything, and I think those can also be used for some sort of reconstruction. Like I think different AT&T and different providers provide you with signals kind of plotting or mapping your whole indoor place, and maybe that can be useful for mapping you know, places where the cameras cannot reach, but like phone towers are everything. So
that actually reminds me, so there was a National Academy of Engineering Symposium, I think last year, or it was last year. And that, like, in those symposiums, they are like very interdisciplinary. They invite like they invite like four types of very different scientific or engineering fields. And in that one area was digital twins, and one completely different area was energy and pollution, something like that. I don't remember. It was not my domain, so I don't remember. But The solutions that they were doing for building ventilation or like water pollution or like finding those different things in the sense of engineering actually somewhat overlapped so well with the digital twins track. So that was a super nice cross-pollination of these like seemingly different research domains, and there was some ideas that I sparked in that symposium. So maybe actually looking at these different domains, different applications, different like talking with different researchers and finding that, oh, we are actually trying to we are looking at the same thing, but we want to understand different things. So how can we actually help each other? That would be a nice one. So changing the topic a little bit, and it's not super different topic, but I want to ask a more general question and maybe go a little bit more technical innovation space. So either in the short term, like, I don't know, like next month or in 5 years, I know I'm giving like a huge span of time for you. What is the most exciting thing that you are either working on and want to share, or you want someone to work on and solve it?
So I think this also nicely connects with Leon's other points, where there was a paradigm shift being needed, right? So I think we would be very excited to see a paradigm shift in the upcoming years. But now I remain a little confused. So is this paradigm shift related to any type of algorithmic development, or are we really talking about, for example, some kind of a quantum computing that would actually change the way we compute things? Well, the computation is done itself, or the hardware changes, and we are just writing the same kind of software for, so essentially for our community, not much changes. But you know, physics people do something interesting. And well, and is this a paradigm that we are talking about that I would be very excited to see, or are we talking about another paradigm shift? Because we started from this broad vision of paradigm shift and then transitioned to, you know, speaking of LoRa. And to me, this is, well, I mean, LoRa is not a paradigm shift. So, you know, I'm expecting, yeah, I was stuck on that point, you know, where all this is going.
I had several keynotes today, and I could unfold a bit more on these here. We can cover other parts. Two things. Of course, we need to solve our own problems there. We cannot rely on others just doing that by scaling up compute infinitely and then getting things done. So I guess that should be clear there. And then the two parts that you're referring there to. When I mentioned paradigm shifts, I'm thinking about us over the last 20, 30 years, having seen a lot of architectures come and architectures go. We had kernel methods, then we had deep learning, MLPs being replaced by CNNs and so on, and transformers coming, diffusion models, of course. And the question is, have we already found the ultimate architecture? Is it the transformer approach, for instance, or diffusion model for that matter? Or are we still waiting for another approach there? And I guess we all know about the issues that these generative models have in their respective domains. And I guess we're looking still for something which scales better there, which does not have the complexity issues that transformers are having. So that's where I'm talking about the paradigm shifts there. Then, as we are waiting for the ultimate architecture, like when we're developing stable diffusion, I think it was like, okay, either we're just waiting for somehow as a miracle, there comes a new approach which has different abilities, or like we did back in the day, then go for a two-stage design. Mix and match the best that we have, the convolutional approaches against the diffusion models, say like, hey, the diffusion models are great, like powerful likelihood models and establishing long-range interactions, but they're a bit of a bazooka when it comes down to modeling like local pixel-level interactions. Their convolutional approaches are better there. Mix and match. That's not the ultimate best approach, but that's the best thing that we can do with architectures that are presently available. And then the last part is what I showed with LoRa's and so on. That was going in the direction, how can we repurpose approaches that have been trained at a lot of costs? Like, should we throw them away and just retrain again everything from scratch if we have a different modality? If we need to move with a model that's just been trained on 2D RGB images, and now I want to talk about depth, or I want to talk about 3D world and so on. And there the question was, isn't there a better way to recycle these models for these different modalities? And rather than waiting for a paradigm shift and just another model coming about and then having to retrain that. Yeah, but no, do it in our vision domain, hoping for better algorithms or working all on better algorithms that we're having there. And while part of our community is working on the better ones and the others don't have that, mix and match, do the best with the approaches that are actually there.
It's also work for actually these 3D representations. So 5D representations, they still come living.
Yeah.
Just appreciate a lot of discussions around that because I actually in the 3D community, I also notice people are more appreciate about what is the ultimate goal of the representation 3D foundation models. One thing I just go back to the host's questions. For me, or for general like researchers in this domain, I think for example in short term we want to see, I think the key question is here, do we actually have enough data? And I feel actually in this space less people appreciate how valuable data sets is. Because when people are working in this domain, people are looking for what is CNN and transformers and what we see happen in large language model and probably video models. They definitely have a bunch of beneficial from GPUs as well as data source. So one question in terms to 3D domain from my personal perspective, I will say, is it a possible way for us, either real scene data or synthetic data will be helpful for us to do improvements for understanding what is the approaching to the 3D foundation models, as well as what kind of representation finally we can find, and as well as can we bridge the gap between reconstruction and generation? Can we leverage different informations here? So for me, I would say I pretty much valuable nice data sets as well as more scalable things in the domain in the 3D space. Yeah.
I guess just to maybe summarize your question back to what this morning in the talk was, will the models learn physics, learn 3D, learn everything, or do we need to explicitly put those things into our modeling decisions? Discuss.
So there's this movement, physically based AI and all those words, and I think that's exactly the question, right? Is there any physics or is it just more data and training? And I would say going back to procedural modeling past, when there was the concept of rules, and then there was rules, I don't know if people have decided what physically based AI means. Otherwise, it's just puff and puff, I think. So, all right. I want to answer a different question that was asked about future work. So I would say that a lot of very interesting work that at least I think about, it may not be directly in the area of urban modeling, but it is kind of inspired by urban modeling. And I think there are many things you see that are very specific. So the one thing I would claim is that the image and video and 3D generative models are very good at, let's say 90% quality, but they really, really struggle with keeping exact constraints and exact requirements. So, for example, you wanna generate a kitchen or so, let's say a layout. They don't care that the kitchen sink needs to be close to the where the water is, and then maybe you can't have the dishwasher very far from the kitchen sink because architecturally that wouldn't work, or there's space too small, like maybe the door can't fully open. And there's a lot of constraints that an architectural plan needs to get correct. There's like laws about, fire exits and all of that, which I would say, or the laws about elevator access, how far can the elevator be from any apartment in the building? There are laws about, like UK lights, right to light, how much, sunlight can be blocked. And, all of these things, I doubt that the generative model actually can pick up. And so there's like a lot of details that are actually required to make plans architecturally viable. And so I think that's one thing. And I think that's similar to the real physics constraints for video models, that the video models don't pick up correctly, at least I would argue so. And the other thing you see for this, also inspired, if you think about this convention center, how hard it is to actually generate the whole convention center with a generative model. So if we start the video model here and we walk out of this room, and let's say we do a 10-minute walk through the convention center, which a person can do, the video model, I don't think can do anything that is coherent, and it will drift way, way, way off. You can't really have the video model generate the convention center. And there's, I think, this long range, really generating large scenes with generative models is a big issue that is very exciting. It seems that we can say, okay, we just need more data, but it seems to be almost impossible to get the right amount of data. So it kind of maybe forces people to think about how can we do this with very little data in a data efficient manner.
Just before going goes, let me see if the hands. Does that sound like a data problem or a post problem? Well, here, let's do hands. Who thinks data problem?
But it doesn't have to be two of those. There's like, I mean,
it could be something else, sure. Okay. And who thinks rules? Okay, interesting. Wow, okay, cool. Okay, please go ahead.
Okay. At the beginning of my talk, I tried to speak to this particular aspect, right? And it showed that what we're actually doing, and that was a good point, that we're following an inductive approach, not a deductive approach, deductive reasoning approach, but with these machine learning approaches, this is essentially inductive approach where we take a lot of data. And with that, we can only in a statistical perspective say where we stand on average. But in contrast to a deductive approach where you have first order principles, which are just right, these are atomic, and that's what you found all your wisdom on. We do it based on the data. And as I showed, like that depends also on the quality and the scale of the data that you have. But even if you increase that, you're just statistically right. You're fitting a model to this finite amount of data that you have there, and then holy grail of machine learning, generalization performance to things that you haven't seen beforehand. Now, when you look at the generative models that are around, what I find striking is like when we were training stable diffusion, for instance, for the first time, I've seen a model that learned things that we did not tell them all. After fitting or throwing enough data in there, we saw emergent properties. This thing showing shadows, is showing that it had picked up a concept that we would call reflection. I'd say like this model has learned reflection, but it was able to mimic something like reflections, shadows. And at the same time, like a week ago, I was giving a keynote and I just tried ChatGPT and asked it how many R's are there in strawberry and get it right. I did this for a bunch of other words and I asked how about raspberries and I got it awfully wrong. And if this model had understood really anything about the concept of R's and concept of counting, of course it should be able from strawberry to transport this over to raspberry, right? Which apparently is not the case. Now this makes you wonder, right? And these models are really great when it comes down to a whole lot of tasks and really outperform us on those. And then they show the ability even on some of the data samples, but they aren't even able to generalize in the most simplistic case that you can actually imagine. And with that, you're on your side, and we all know the way out, right? You then have them switch over to a different sort of mode of operation and create a Python program and just count certain characters. But this is just circumventing, right? I mean, it's not that the model itself gets it right. We see that they're really great at fabricating something. I mean, don't want to say hallucinate, but generate something essentially. And But when it comes down to the exactness, we have this image domain. When it comes down to something which is pixel perfect, that's just not what they're built for.
Why is
That-
everything Python programming circumvented it?
The question is, like, when you're in the camp of really the generative model, the question is like, how can you further improve the generative model to fix the issues that it presently shows? Now, I can, of course, sidestep this problem by kicking in other modeling approaches to solve this problem. And from an application perspective, I'm totally fine, right? If I'm a company, that's exactly the direction that I'm going. But when I'm a purist, I'm saying like, I'm dealing with diffusion models. And I want the diffusion process to, in that case, not just give me the breadth, but give me also the accurateness there. Then I'm presently having problems.
But as a generative model, if I decide on my own to write a Python program for this and answer your question based upon that, then it's completely fine, right?
But that's not happening, right? You have reinforcement learning telling you, in this case, you better shut up and use the other model. And I mean, that's a quick fix for a problem, but that's not a deeper solution.
Because, I mean, in these counting like problems, right, we know that we are asking the model to explicitly do something. Like, it's a difficult thing for it to do so. Even as humans, by the way, we first developed the algorithm, counting. And then we solve the problem.
Yeah, but this goes further, right? I don't want to come up with like number of fingers and so on image, right? But you see, whenever it goes in the direction of being spatially more accurate, that these models, as great as they are in you take View 3 and so on, as great as they are in other domains, that becomes an issue. The moment that it comes down to control in editing images, these things start to edit whatever arbitrary other aspects, right? As great as they are, turning your text prompt into something, the moment that you try to make it more accurate and you reduce the ability for this model to wander off, performance also starts to decline.
I think this hand example is actually way more appealing to me than because the R's thing, tokenization, there's like that. But the hands thing always confused me because, like, okay, there's the VA, there's this problem, but we don't see 6-fingered hands in the data set. So like, why am I seeing them on the model?
Well, I see this more as a feature than a bug, right? For a long time, we've been having computer vision algorithms and AI algorithms for that matter, which were great if you were totally exact, right? I mean, then computers work. You still remember the day and age where you needed to write in printed letters very accurately so that computers could understand you. And computers for a long time have been much better when it comes down to exact processing. Now with generative AI, for the first time, we have the computer venturing over into our fuzzy world and being able to handle that. And now it kind of went a bit too far and understood, like in a lot of situations, I have self-occlusion. I don't see all 5 fingers, right? I just see 4 or 3. In certain situations, 2 hands might be closed, and then I get something which looks more like 6 and 7. And this thing gets to the point like, oh yeah, maybe the world is so fuzzy, the number of fingers doesn't really matter because it actually does not matter, right? It changes. It's only in a certain few situations you transition via this uncanny valley, and then we notice, but the machine just thinks like, yeah.
I will go to the one question that is in our form, so that we don't forget it. So this is a longish question. I will just read it. Referring to Dr. Peter Wonka's last slide during your keynote, teach physics to the model or learn the physics from the model. It seems to me to be a chicken and the egg situation, but there were eggs way before chickens, just as there were laws of physics before any video model. So it might be easier to teach physics rules than to learn them. From this point of view, the question becomes, is it better to embed physics in the training data, for example, RGB plus XYZ coordinates in the model design, for example, multi-branch models, or in the training objective? What are other possible options? I think this is very relevant to what you were just talking, so I want to just slide the question. Anyone can jump in, it's not just the speakers.
Opinions about adding other side signals? So you're a rules guy. Let's you have an opinion on this? Why rules, and what's the relationship between rules and this adding side?
So I'll first say that I only came in on the last session because it looked like an interesting topic, so not my area, but I'm generally a more application kind of guy, and so I just want to get things done, so that's why I'm a rules first kind of person. So.
So did I ask the question? Okay. So what I was thinking about is the fact that, as the example that we just saw with the number of fingers, we know how some stuff is supposed to be, and we don't have to necessarily have a model, understand it, or kind of deduct it automatically from the data. We could make it easier for the model to understand some stuff. Now, I understand that using rules directly will go back to expert systems, and that's not ideal because their set of rules becomes too big. But we could use some kind of proxy for that. Might that be a different training objective? Might that be something completely different? Might that be something that's different from gradient descent? Maybe that's going too far, but it may require something else.
Well, you brought up this point, like the set of rules being too large, right? And that would be the point of deductive reasoning, right? If you just need a few first order principles there and the rest you would just deduct, ideally online. If that takes too long, right? You might save this, but like what we are in machine learning, we're more like in this inductive camp, right? We take a lot of data and then we just fit something to that. We don't have these first order principles. And I guess that is what this question is all about. Should we actually throw this in there? I mean, certain things you don't need to learn that or learn. You don't need to correlate that or fit some model representation, be it parametric or non-parametric, to the data. You just write this in there. And of course, I mean, if I just care about the application, why have this been figured out from the data if I know it already in the first place? Like the machine learning vision researcher in me says like, oh, how cool, right? I mean, at least I have something that I can easily evaluate because I know that F equals N times A or whatever, right? And then finally I have something that I can actually benchmark, but I mean, that depends on where you stand on the applications.
I want to comment / ask my neighbor here a question. So you mentioned how cavemen have the same amount of the same computer size, right, as we do now. We seem to be able to do more. So is that related to this question here, some kind of compartmentalization, or other word is a hierarchy building? So you have some boxes that you build up that have rules, have knowledge, and then we made new boxes on top of that. So the caveman had very small boxes. Now we have a big complicated hierarchy because we learn many more things and compartmentalized rules. And then, so is maybe a third option is not just inductive deductive, it is hierarchical knowledge. So we found the pre-trained model, the pre-trained physics engine, which is a huge word, right? Really has smaller boxes that we learn, and then we use those and make bigger pieces. So we don't have to say F equals MA anymore. We know that's the case. It's trained in this space models. Does it make sense?
Yeah. What I know from cognitive science is that it's another answer, right? And that's the entire part of learning, right? In that case, it's not our hardwiring that we have in the brain, but essentially the sociological part to that you have parents, that you had peers, that you had school, and so on. And you grew up essentially in a different society than the cavemen did. Since we had printing press and so on, intelligence as we were using it had also spiked again. Intelligence, the actively used intelligence had spiked up since man discovered fire, because you can have longer waking hours and do something. And once you have knowledge and you can actually push this into writing, and you don't need to rememorize that all along, you can send it over and share it. In that case, we also had spikes of actively used intelligence without our brains ever changing. And in processing data, developing better teaching models, making it easier to digest, we also had these spikes up. And these are all helpers. This is a bit like a post-it, right? Your memory is kind of finite and limited, but then you push it to the outside on a post-it or in a database these days, and that actually helps us, although our cognitive system has not improved itself.
I just want to be respectful of the speaker's time for 15 minutes over. This is a wonderful, wonderful discussion. Maybe
Maybe I'm with the question on the screen because I said I will cue it in.
so let's do that, and then anyone who wants to continue discussing, let's go stand outside, and if you would like, we could all stand outside and talk together, and if not, then, you know, wonderful discussion.
Okay, the last question that came from Zoom is that, I will just turn it for a second. Okay. If you wanted to create a better neural network architecture than diffusion models or transformers, what limitations in current models come to mind first? What would be your initial intuition? And this is a little bit more general question than what we have for USM3D, but I think all of our intuition about how we can bring it back to our urban world or like the 3D construction world, etc., with embedded systematic rules or physics or other structural rules, etc., may also be some kind of answer to this.
And the question went in the direction of diffusion and transformer architectures. Like first off, it depends on your particular scenario. When we're in the video domain, autoregressive seems fairly natural, right? Because you can't like take everything into memory and you kind of need this going in. And with that, we're still having issues, and we see now autoregressive models making a step forward. But so far, it was like once we had brought out stable diffusion, people took our UNet encoder, made it 3D, essentially stacking a bunch of frames, but that only goes so far, right? You can create 10 frame long videos or whatever with that, right? And now that we're seeing especially work on much longer models like autoregressive being interesting there, and transformer architecture being great in how it scales, but the complexity issue that I mentioned being definitely something where I would love people sort of dedicating more time on and looking at efficient modeling of long-range context, be it in the spatial or temporal domain. Efficient modeling there being one of the pressing problems that we have. And then these two-stage designs that we have, that was a crutch that we went for because we didn't have anything better, right? But ideally you would want, you know, I'm still looking for a model that does everything out of one. You throw the pixels in, and you don't have to develop a first stage and a second stage.
So I'm not a quantum computing expert, but I play one on TV, so to speak. I think thinking what would a neural network for the quantum computer that thinks about these simultaneous states and the different way that parallelism occurs in quantum computers, that would be interesting. If we just answer that question, would be very interesting. And that's assuming that quantum computers will become more mainstream at some point, which might happen. Everything might.
The state of quantum computers are in a quantum state. So, yeah,
You go ahead, and then I'll say one last thing.
okay. So I think, yeah, to get it in a little bit of time. So thank you for everyone for participating in our workshop. You see here, there is some feedback form that if you want to fill in about what we can do better next year, don't expect more prizes. We reach the top of the prizes and you won everything, okay? So, no, I'm just kidding. But and also if you have sponsors, there are always more sponsors. Oh my God, such a bad talk. We thank all of our keynote speakers for being here, for their talks, for their panel, for sharing all their research. We thank all of you for participating in our challenges, our competitions, etc. We thank all of the organizers, Jack here, Vishak there, Tolga there, Dimitro on the Zoom, and many others that also participate. Thanks to all the organizers, and we'll see you next year.
Thank you. Really appreciate you. I'm gonna go stand outside. If anyone wants to keep chatting, I'll be there. And thank you.